Hope you are visualizing me. I think screen sharing is not coming. Yeah, coming now. Yeah. Now, I would like to share this one also. Whether are you visualizing this Hukum Chandra's profile?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah.
Yes, yes.
Now, it's my proud privilege to invite Professor Hukum Chandra, a national fellow and principal scientist, Indian Council for Agricultural Research, and Indian Agricultural Statistics Research Institute, Library Revenue at USA. And Hukum Chandra has over 23 years of experience in research, teaching, training, and consultancy in statistics. At present, he is ICAR National Fellow and Principal Scientist at ICAR Indian Agricultural Statistics Research Institute, New Delhi. He did his PhD in social statistics from the University of Southampton, United Kingdom, and postdoctorate research from University of Wollongong, Australia. He works on diverse areas of methodological and applied problems in statistics, including survey design and estimation methods, small area estimation, bootstrap methods, disaggregate level estimation, and analysis of agricultural, socio-economic, and health indicators, spatial models for survey data, and statistical methods for improvement in agricultural and livestock statistics. He has contributed to nearly 25 research projects with the primary focus on developing efficient small area estimation methodologies and further applying the established methodologies in actual data from various sources such as socio-economic, health, and agricultural surveys. He has published more than 120 research papers and 4 books, several technical bulletins, project reports, book chapters, working papers, and training and teaching reference manuals. He has delivered a number of invited talks in many national and international platforms of repute worldwide. He has supervised 4 PhD students. He is also contributing the volunteer academic activities like associate editor, guest editors, and reviewers of the various scientific journals, member of scientific committee, and convener of different national and international conferences. He has worked as consultant of FAO of the United Nations in Sri Lanka, Ethiopia, Myanmar, and Italy to strengthen the agricultural statistics system. He has worked as expert member in various committees in different institutions and ministries in India. Dr. Hukum Chandra is elected member of International Statistical Institute, Netherlands, the Fellow of National Academy of Agricultural Sciences, India, and Fellow of Indian Society of Agricultural Statistics. He has worked as Council Member of International Association of Survey Statisticians and Joint Secretary of Indian Society of Agricultural Statistics, New Delhi. He is Joint Secretary of the Society of Statistics, Computers and Applications, India. He is a recipient of National Award in Statistics by Ministry of Statistics and Program Implementation, Government of India, and Cochrane Hanson Award by International Association of Survey Statisticians, ICAR National Fellow Award, Young Research or Student Award of the American Statistical Association, Lal Bahadur Shastri Outstanding Young Scientist Award of ICAR, Recognition Award of the National Academy of Agriculture Sciences, Professor P.V. Sukatne Gold Medal Award, and Dr. D.N. Lal Memorial Award of Indian Society of Agriculture Statistics. He is a recipient of Commonwealth Scholarship offered by Commonwealth Scholarships Commission in United Kingdom. So really very admiring profile, and within a young age period, he has contributed a lot. It shows his vibrant and terrible, magnificent academic talents. So really, it is our privilege to invite this type of high-profile speakers for our conference, and really we are humble to him, sir. Welcome to you to deliver your talk. Today's we are going to have his talk is on small area prediction of survey weighted count under spatial models. Now I request Professor Hukum Chandra to share his talk.
Thank you. Thank you very much, sir, and good morning to all. It's my privilege to be one of the speaker of this great conference, and I really would like to say thank you to Professor Tripati Rao and University of Pondicherry for organizing such a nice utilizing this pandemic situation very excellently. And if you see the list, actually we have got so many eminent statisticians from India and abroad. Actually, have given the platform to gather in one place virtually. Thank you very much.
Globe,
and
globe become a small home.
Slide.
Sir, globe become a small home now.
Yes, sir. And you have actually really used pandemic situation in very excellent way. We are using this platform like if you see in a physical conference we never get so huge group of statisticians, but even in this virtual we are getting a good number. Thank you very much actually for your initiative and really efforts. Thank you, sir. And I like to share my slide first. Okay, I'll just share.
Yeah, you can make it.
Are we able to see my slide?
Yes, sir. Yes, sir. You are able to see. You are visible. You are audible. Everything is perfect.
Okay. Okay. Once again, good morning to all. Today I like to talk on a small area prediction of survey weighted count under a spatial model. And I have set my slide like this. First, I'll give, because this is small area estimation is a new topic for many of the audience. That's why I'll give some background about this small area estimation technique itself. Then I'll introduce generalized linear mixed model and in small area prediction based on this model. And then I'll give the spatial extension of generalized linear mixed model, and then again small area prediction on under this model, a description of data which has been used for the application, and then empirical result followed by few concluding remarks. Small area estimation, as I told, like many of us in an audience, they are well aware, but for the sake of continuity, I'll go very slow to describe it. You know that most of the national survey is conducted by NSSO or the National Family Health Surveys. They are generally planned to produce reliable and representative estimates of population parameters of interest, but mainly at higher geographic level. For example, it may be state, national, or regional level. What we can refer them as a larger domain, or they are the planned domain in the survey. And our surveys is planned in such a way that sample size is decided in such a way that direct estimator, which is estimator defined using domain-specific sample data, they are reliable and no issue at all. But for many practical purposes, for many policy intervention, nowadays sustainable development goals in the picture, we need many disaggregated level information. We need information estimate for many domains actually which has not been planned in the survey. Then what happened, the sample size for such domains, because they are not planned in the survey, becomes very small. Sometimes there is no observation in domain when we go the disaggregation of the domain. Then as a result, the direct estimate, which usually sample data specifically from the domain of area of interest, when sample size in such domain or areas are small, standard error become very high. Then our estimate is very unstable for any practical purpose. Second problem is sometimes there is no sample data in such a domain. Then it becomes impossible to produce estimate for such a domain. That small area term is then used to describe a domain which sample size is not large enough to produce sufficiently precise estimate for such domain. Here, small area we refer to the domain where we have got the problem of sample size. This small area and domain has nothing to do with the geographical size. They can be sometimes state as well. And increasing sample size is also not always possible because budget constraint, time frame, and manpower, and even we cannot alter the sampling design because such domain, as I mentioned, that they are unplanned. Such a domain actually comes in a picture. It's a need based. When some policy planner, government department, they ask. That's why even we cannot modify the sampling design of the survey to meet such requirement. Then solution is we need a special technique for producing the estimate for such a domain from the existing survey data. And the topic is referred as a small area estimation technique in a survey literature, which address the problem of small sample size. This methodology of small area estimation, which address the problem of sample sizes, borrow the strength, means use the data from other sources and hence increase the effective sample size. Idea here is to link, use some statistical model and to link the variable of interest with the auxiliary variable. We have got the survey data on one side, but we can have got the plenty of auxiliary information coming from census and different administrative data sources. Those can be combined and linked to produce the reliable estimate. And other thing is because we are using the model, this small area estimation technique is a model based method, and generally mixed effect model is widely used in a small area estimation technique. And you know that in a mixed effect model we have got the random effect term, and in when we use this mixed effect model in a small area context, this random effect term is referred as area effect, which captures the dissimilarities between the area. That's play very major role. Now here I will be talking about the proportion. That's why I just motivate the generalized linear mixed model first. When variable of interest is not continuous, we know that, for example, binary or count, generalized linear mixed model is commonly used. If variable of interest is particularly binary, then GLM, generalized linear mixed model, I will refer as GLM hereafter, with the logistic link function is adopted. And the other issue here is in many small area estimation problem, it may not be possible to use a unit level model because of sometimes unit level data is not accessible due to data confidentiality and other issues. When only aggregate level or information is available, then area level model is often used in a small area. Area level is the model which is fitted using aggregate level data, which is a unique in a small area estimation term. In the theory. Here I'll discuss about this GLM under area level model when we use the aggregated level data. I'll introduce some notation for the sake of continuity. Whenever I'll use the index I, it means I'm referring to area or domain D, I, and we have got the total D domain. I stand for ith domain. Small ni and capital Ni respectively denote the sample size and population size for area I, and small s and r refer to sample and non-sample part of the population. And I denote observation actually. Yi is my variable of interest for unit j in area I. For example, if I j is 1, if household j in area I is poor. For example, if household j in a district I is poor, then it takes value 1, 0 otherwise. And with this, my aim is to estimate the small area population count, or alternatively, we can generally estimate small area proportions. That is my variable of interest. With this, if I have got the survey data where I have this Wij is my survey weight, for attached to household J means unit J in district I or area I, let's say, then traditional survey direct estimate, which is a weight estimate, which uses the area specific information, is given like this. Is a direct estimate. This is a traditional weighted estimate. And what happens when the sample size is small? This estimator is very unstable. And if we have got zero sample size, we cannot produce this estimate. And now I'll introduce this generalized linear mixed model at area level, which has got the form like this. If pi logit function of probability pi, which also refers to probability of success, which if we have got the, let's say, vector of auxiliary information, we can write this logistic linear mixed model. Here uy, this first term xi beta is a fixed effect part, and the second term is a random area effect term, which captures the dissimilarity between the areas. And under this model, a plug-in empirical predictor for a small area proportion in area I is defined like this: sample sum and predicted non-sample sum. This is a proportion. When we'll talk about the probability, this is a probability ratio, like that. But here, this predictor, and under this model, I will be talking about two extensions. Here, this model is built up on the assumption that this is based on unweighted sample count. Model is unweighted sample count. We are not using the survey weight, which assume that sampling within area is non-informative. But when we are using survey data, we cannot use the unweighted sample count. Rather, we have got the weighted sample count. But when we use the weighted sample count, we have got two problem here. If I'll talk about the weighted sample count, this sum of wi, yi, that may not be following the binomial distribution. If yi is a binary, sum of yi is a binomial, but wi, yi may not be the binomial. And the second thing, variance of this weighted count may not again follow the binomial property. This means this model may not be very good. I address this problem by using effective sample size. I replace the sample size and the sample count by effective sample count and effective sample size, and which take care of this survey design used in the survey data. That is the concept we have used here, and I'll not go in much detail given the time. And the other aspect here in this model, if you see here, this random area effect, which follow normal with zero mean and fixed variance, is IID. This means this model assumes that different areas are independent. If I'll talk about the district, it's assumed that different districts are independent, which in a real life, in a practical situation, is not true. Here we model in the second direction. We will assume that this IID assumption is not true, but this area effect is have some spatial dependence. In particular, I have used SAR structure, simultaneous autoregressive error process, for modeling this correlation between different areas, which has got this form. It's a very well-known form. I think many of might be knowing. Here, follow this autoregressive term. Here we have got the term like L. L is a d by d proxy matrix, actually, which account for the distance between I and J area, like that. It's a function of a distance, and rho is a correlation, autocorrelation, which measure the association between different areas. This form has been introduced, and then my this logistic model, which is a logistic model with SAR error process, look like this, where this term is not independent now. We have extended to this logistic linear mixed model in two directions, and then accordingly my empirical best predictor for the small area proportions has been defined. And parameter estimation again has, because it's based on aggregated level data and it's a non-linear model. You know that GLM, one of the very commonly used methods of penalized quasi maximum likely estimation method, which has been adopted here for the parameter estimation. And we have used three different structure for this spatial weight matrix L. First one is when we L1, L2, L3. Three has been considered. L1 is when we take the value 1 when age of two districts or two areas touch, 0 otherwise. In a second case, actually, we have given the element of matrix L, Lij as inverse of distance. This means areas nearer have got the more weight, and the second is element is a defined exponential form of distance matrix has been used. 3 different form has been used, and a mean square error estimation for both EP, the empirical predictor, and the GLM, and spatial empirical predictor, the spatial GLM has been is already available in the paper. I have not given the description. In my application, which I will show you, I have used these predictor. Direct is direct survey weighted estimate. EP is empirical predictor, and a 3 spatial empirical predictor, which are based on 3 different type of spatial matrix, which I have referred as L1, L2, and L3. And I have used this in application. The data set which I have given you is household consumer expenditure data, which is the latest round of data collected by Government of India under Ministry of Statistics and Program Implementation. That was collected in 2011 and 12. And we have for auxiliary information we used population census data, and analysis is restricted in state of Uttar Pradesh, in particular for the rural areas only, but methodology is applicable for any state, any data. And sampling data design for this household consumer expenditure data is very complex, which uses the stratified multi-state sampling. Sample size is total 5,916 household from 71 district. At that time, the state was having 71 district. Now it has got the 75 district, and the sample sizes varies from very small 32 household to 128. And district sample count, which is a number of poor household, is ranged from 1 to 48. Which sampling fraction is very small, 0.002. And with this sample size and sampling fraction, it's difficult to produce reliable district level survey estimate with the associated standard error. Which I have used this small area estimation technique here. Here, variable of interest is a binary, whether house is poor or not. Poverty line has been used, which has been defined by Planning Commission, Government of India, which is a rupee 768. Any household, if monthly per capita expenditure is below, this means poor, otherwise not. And target here is to estimate the proportion of poor household at a district level, which is also called the poverty incidence. And small area is different districts of Uttar Pradesh. Auxiliary variable, which has been taken from census, and but there are a range of.
Hukum Chandra, sorry for disturbance.
Yes,
friends, you just make on your cameras because we are recording. Hello.
Yes, sir.
You on your camera so that we are unable to see your camera, your image, because it's recording now.
Yes.
Yeah,
Yes.
you make it.
Okay.
And you share it again. Oh,
yeah.
Now you can. Right.
Yeah.
Thank you.
For the auxiliary variable, I have used the census 2011. There is a range of auxiliary variable available in the census, but for any particular application, we need to identify the appropriate auxiliary variable. But here, what I did, using several auxiliary variable, we have developed some index, which is referred as S1, S2, and S3. For example, S1 is based on the literacy rate by gender and proportion of worker population by gender. Likewise, other indicators has been developed, and they has been used as a auxiliary variable in this small area estimation application. And in my past slide, actually, I have been mentioning that effect of survey weight in the data. To explore that, first we plotted the weighted and unweighted direct estimate of poverty incident. Here we can see that survey weight has some impact, because if we ignore the survey weight, if we direct estimate or underestimating. In next plot, I have plotted the effective sample size versus sample size, effective sample size versus effective sample size and effective sample count versus observed sample size and sample count. Here again, we can observe that sampling design is informative. This means we cannot ignore the sampling design while doing the small area estimation technique. That's why the introduced methods is useful for this data. And when we apply the small area estimation technique, we generated the estimate. There are certain diagnostic procedures as well. There are two groups of diagnostic procedures that need to be applied. One is called the model diagnostic, which is applied to explore, to examine whether this random area effect to follow the normal distribution or not. Here, I have not presented the result, but my diagnostic clearly indicated that this random area term in this poverty data is quite follow the normality. And second set of diagnostic is to see whether my small area estimates are reliable and valid or not. They are explored through a set of diagnostics, for example, diagnostic, which is used to explore whether my model-based small area estimate developed through using small area estimation technique are consistent with the direct survey estimate or not. A coefficient of variation is used to see the reliability, actually, how good my small area estimate is as compared to direct estimate. Same is for the 95 confidence interval. But we also use the aggregation or benchmarking property to explore whether my small area estimation aggregate to higher level or not. Here in this data, if you see the summary of coefficient of variation, if for the different method which has been applied here, if you see the summary statistic, we can see that the direct survey estimate minimum coefficient of variation varies from around 13% to 99%. 99 and the average is 35%. You can easily see that the direct survey estimates are so unstable. They are not of no use in many areas. For example, 99, 47% of CV. But if we apply the small area estimation technique, the first one, it reduces again up 49 become 43. Still not so good. But when I use the spatial information in the small area estimation technique, we can see that the maximum CG reduces, and in average CV is from 36 to, goes down to 23% on average. This means the small area estimation technique is giving a good result, and estimate generated for this poverty estimation can be useful. If you see the district-wise CV for the different method here, if you see that among the spatial, this one is the best one, and if the where we have used the spatial distance metric, which is a exponential form. Here, if you plot the CV, we can see that this direct estimation is very unstable in most of the areas. This CV is more than 30%, which is not acceptable. Official government cannot accept such estimate when CV is more than 30%, but the small area is giving reliable and representative estimate because the CV is reasonably good. And here we'll plot the confidence interval. We can see that this blue line direct survey estimate. We can see that blue line direct survey estimate is so wide, and even in many district lower bound is invalid. Actually, it's like a negative, which cannot be, because it's like a proportion. It should vary between 0 to 1. But a small area estimation is giving quite a reasonable confidence interval as well. When we'll talk about aggregation, because official statistics ministry also want, if we have got the two set of data, one is from the direct survey estimate, one from the small area estimate. When we'll talk about a higher level, let's say state level poverty or regional level, even when we'll derive it from the small area estimate, it need to be the same. When we'll see the aggregated level estimate, state level poverty 26, whether we are from the direct survey estimate and also from the small area estimate. This means method is also following this aggregation property is good in that term as well. Finally, once we have got the direct estimate, district level poverty estimate, we can produce the poverty mapping, which like this when we consider, although average poverty at state level is like 26, but you'll see the district level poverty is vary from 6% to around 50%. With this mapping, policy planner can identify, visualize the district where they need more policy intervention. Here in this map, we can clearly see east and west divide in the state of Uttar Pradesh. These are the western Uttar Pradesh, which is known to be with have a smaller poverty. And to conclude with this talk, I have seen two aspects. One is a spatial extension of area level generalized in a mixed model, and consider the small area estimation of survey weighted proportion. This means how to incorporate the survey weight in a small area estimation and how to incorporate the spatial information. Then we applied the method for estimating the poverty incident in the state of Uttar Pradesh and produced the map. Result clearly showed that the advantage of using the small area estimation to address the problem of small sample size to produce a reliable and representative estimate and confidence interval. It is expected that this estimate will be useful and for identifying the district region with higher and low level of poverty incidence and to attract the attention of policy planner. Thank you very much. The method applied here can be used for any other data and for any other survey as well. Thank you very much. Now I'll welcome the question, comment, suggestions. Yes, sir.
Sir, please unmute, sir. Sir, please Rao, sir. Please unmute.
Professor Rao, sir, please unmute yourself.
Thank you, sir. Thank you for your nice presentation and covering a very specialized areas. I think I have seen so many terms mostly newly coined. I'm not having much exposure to the sampling theory. So anyway, your ideas at small area estimation is most wanted, or what we can say, it is a most required tool for these all surveys, survey related. Very nice presentation. And now I request the audience, if you wish to interact, please make it.
Professor Rao, sir, Lakshman Rao, sir, please unmute yourself. Yes.
Lakshman Rao, you are supposed you unmute and speak, sir. Okay, Viswanathan, you please.
Sir, in your estimates comparing the confidence intervals, okay, you can see improvement in the upper bound. Upper bound is sufficiently getting reduced while you compare that direct EP, SEP 1, 2, 3. But the lower bound, okay, it remains almost equal. Can you say why it is so? Because when we say there is some improvement, means we should be crunched from both ends. But we can see here upper bound coming accurately, sufficiently less, but the lower bound is not. It's almost remains same. Why it's happening? Any idea?
I think when we'll compare the confidence interval, generally we don't compare the lower and upper bound. Rather, we compare the width of confidence interval, because the width of confidence interval is directly, you know, that 4 times standard error. We cannot compare the lower and upper bound, but when we'll compare in terms of standard error, when standard or let's say CB, confidence coefficient of variation, we see that when we have got the lower CB, it is better to compare in terms of CB, coefficient of variation. Lower CB means both small area and direct survey estimate are reasonably good. Those are the those districts are areas where we have got sufficiently good sample size. When sample size is a good, our direct survey estimate itself is good. We don't need a small area in those district or areas. A small area estimate is required in those districts or areas where we have got the problem of sample size. That's why it is expected that when we have got the smaller CB, let's say 12% or 13% in particular in this district, both the direct and small area estimate will be at par, because a small area addresses the problem of sample size.
One more quick question, sir. So with
Yes,
regards
yes.
to the weights, okay, you say that incorporating the weights in say SC1, SCP1, 2, and 3, are you using different auxiliary information as weights, or the normal distance that we supposed to be used in something like Moran's I or Gary's C spatial statistics?
Okay, weight actually, just to clarify that, I have used the weight twice. One is the survey weight, which is different, but S1, SEP1, 2, 3, they are based on a spatial model. Here we are talking about the spatial weight matrix. For example, if I say in this particular application, this spatial weight matrix is 71 by 71 weight matrix, where element is a distance between two districts. And here three distances, like first one was simple contiguity matrix, which take value 1 when a district boundary touch. And in second case, it was an inverse of distance. Element of that matrix is if distance of two inverse is, let's say 10,000 kilometers, for example, although when compute is different, this means 1 by 10,000. And the third weight matrix was element is exponential, actually Gaussian form of function of distance matrix.
Okay, Professor. Thanks for your time and explanation.
Now I am going to request our Professor Shashikant Mishra from BHU Department of Mathematics.
Yes, sir. Just a minute.
Yeah, Professor Shashikant Mishra, please.
Yeah.
I'm just going to present about you.
So my screen is visible, Professor?
Yeah, I received and I make it, sir. Please,
Okay.
please.
Okay.
No, sir. Don't share by you. I'm sharing. Okay.
Okay.
Now, is it visible, Professor Mishra's? Hello.
Yes, this is visual, sir. Visual.
Yeah.
Yes,
Yeah,
sir.
now it's my privilege to introduce one of the vibrant mathematics professors from another vibrant university from Banaras Hindu University, Varanasi, Professor S.K. Mishra. And Professor S.K. Mishra did his PhD and DSc and he now Department of Mathematics, Institute of Science, Banaras Hindu University, Varanasi. With over 20 years of teaching experience, he has authored 7 books, including textbooks and monographs, and has been editorial board of several journals of international repute. He has guest edited special issues of Journal of Global Optimization and Optimization Letters, both from Springer, and both are scientific citation indexed. And Optimization, it is published by Taylors and Francis. Again, it is also SCI. And INSA Teacher Awardee. Recently, I was awarded with INSA, Indian National Science Academy Teachers Awardee, a DST Fast Track Fellow during 2001-2002. Professor Mishra has published over 150 research articles and supervised 18 PhD students. He has visited more than 15 institutes or universities of different countries such as France, Canada, Italy, Spain, Japan, Taiwan, China, Singapore, Vietnam, and Kuwait. Today he is going to talk about Newton method for unconstrained multi-objective optimization problems. Now I request Professor Mishra to make his presentation. Over to Mishra.
Okay, sir.
Yeah, I'm stop sharing, sir. Please.
Okay.
Yes, sir. It is visible.
Just a second, sir. Just a second. Yeah. So
Sir,
I will
again
be.
it was disappeared. Now it is coming. It's coming.
It is coming.
Yeah,
Now,
it's coming now.
actually, what I will do today is I will give you some idea about unconstrained methods, little bit of background of Newton method, and then we will go to some new techniques like Q calculus when the objective function is non-differentiable, then how to handle it. That is something new nowadays going on. So first of all, well, I know that I'm out of the box here because most of you are from statistics, but well, optimization problem means minimize some function I'm taking from Rn to R, the very easy stuff, and the it is called objective function or cost function or profit function or utility function. Many names are there in economics for this function, but we say only objective function. And the vector x, we will take like column vectors x1, x2, xn in R, in Rn, that is the constant for the time being. And the components x1, x2, xn, they are all called decision variables. And the set omega is called the constant set or feasible set. And there are two types of optimization problems mainly. Unconstant, if you take this set omega as the entire space Rn, then the problem is unconstant. That means there is no boundation or no condition imposed on the variable x. And if omega is a subset of Rn, then it is called a constant optimization problem. They both have completely different way of solution and methods and everything. Now, first of all, I would say that what is a local minimizer? Then I will go to global minimizer. For f from Rn, from omega to R, a point x star is a local minimizer of the function f over the set omega if there exists some epsilon positive such that the value of the function at x star is always less than or equal to value of the function at every other x in the set omega. And the distance between x and x star, if you are in Rn, it's norm less than omega. That is local. If we free from this one, the neighborhood of x star, then it is a global minimizer. For example, this is a local minimizer, strict local minimizer, because it is like this. Global minimizer, if you consider the function is only this much, and from this line to this line, supposing this line is straight, it is local minimizer in certain neighborhood. Well, the tools are being used in constant or unconstant optimization. For the classical case, that is derivative in several variable case. If the function is from Rn to R, x has several variables, I mean several components x1, x2, xn, then the derivative is written like this. And if you take the gradient of this, that is called the gradient of the function f at a point x. And second derivative, that is also known as the Hessian. It is like you take this first component over f upon over x1 and again differentiate with respect to x1, with respect to x2, and with respect to xn. This is the Hessian matrix, and it plays a very important role in calculus of several variables, single variable, everywhere, in deciding function is convex or not. One simple example for if students are there, if your function is like 5x1 plus 8x2 plus x1 x2 minus x1 square minus 2x2, then the gradient is you take this one, differentiate it partially with respect to x1, that means 5 plus x2 minus 2x1. Again, you take the same function, differentiate this time partially with respect to x2. So it's 8 plus x1 minus 4x2. And the Hessian is, you take the first element and differentiate it with respect to x1, so it's minus 2. Again, you take the same, differentiate this time with respect to x2, it's 1. Similarly for the second one. Well, if you're in constant optimization, unconstant basically, if the minimizer lies on the interior, in the interior or on the boundary, there are two different problems. How to deal with them? In the case when it lies on the boundary, we need a concept that is called feasible direction. Feasible direction approach is, what is a feasible direction? Any vector d in Rn, non-zero vector, is a feasible direction at point x in the domain omega if there exists some scalar positive such that x plus alpha times this vector is back in omega up to certain alpha from 0 to this alpha naught. Like if you are inside in the interior of omega, this is omega I have taken, then every direction is feasible direction. But if your x is on the boundary, direction is feasible direction because x plus alpha d is inside here. They all are feasible direction as long as you travel certain distance in omega. But as soon as you go out, that direction is not a feasible direction. These all are not feasible directions. Now, we need directional derivative concept, and out of that, we have derived several other generalized derivatives, and Q derivative is one of them. Okay, f from Rn to R is a real valued function. D is a feasible direction at point x in omega. The directional derivative of f in the direction d, okay, at point x is this limit. Limit alpha going to 0 from positive side, f from x, f at x plus alpha d minus fx upon alpha. This is the directional derivative of f in the direction d at point x. So you note that everything is fixed. This d is fixed, x is fixed. So only variable is alpha over here. So there are easy way to calculate rather than taking limit every time. So since x and d are given, that means they are fixed. So fx plus alpha d is a function of alpha only. And then we use the chain rule, directional derivative of f at x in the direction d, as since it is only variable of alpha, so we'll differentiate ordinary derivative with respect to alpha, and then we take the alpha at 0. So if you differentiate this, since it is several variable, so you will get the gradient of this, and by chain rule, once you differentiate x plus alpha d, you will get d over here. So in order to calculate means directional derivative, you don't need to take the limit. You only compute the directional derivative, I mean gradient, and then the direction, inner product of the gradient and the direction in which you are asked to. One simple example over here is, suppose your function is from R3 to R, function is simple enough, x1, x2, x3. Then the directional derivative of this function at any general point x in the direction d is, you take the gradient. Gradient is what? You will take this, differentiate with respect to x1, then partially differentiate with respect to x2, then partially differentiate with respect to x3, and then the inner product with the direction d. So this is the directional derivative of this function at a point x, general point, in this direction. Now, the first order condition for a local minimizer is, suppose omega is a subset of Rn, f is continuously differentiable real valued function on omega Now, if x star is a local minimizer of this function over omega, then for any feasible direction d at x star, we will always have that directional derivative of f at x star is always positive, greater than or equal to 0. Okay. If the point is in the interior, if x star is in the interior, then this is only gradient is equal to 0. You don't need to calculate the directional derivative at x star. Okay. The proof is very easy, so I'm just leaving it because otherwise I will not be able to complete. Okay. Then for getting the sufficient condition over here, you need at least the function f should be convex, at least convex. But we are going for the numerical approach, so I'm not going to impose any other condition on the function f other than it is continuous differentiable, or it is differentiable, or it is non-differentiable. Like I'm not going to consider function is convex or generalized convex or anything like that. That will be a completely different approach of nonlinear constant optimization problem. Now, we know, most of we know that the gradient acts in a direction in which the function increases more than in any other direction. From calculus, we have learned this. Therefore, the direction opposite to the increase, that means we take the negative direction, that will be the good direction to search if you are looking for the minimizer of the function. So, if x naught is any starting point, we consider the point x naught minus some alpha positive and gradient of f at x is x naught. Okay. I'm expecting that this will be the next improvement point when you are looking for minimizer of the function f. So how to deal with this? We define a new function phi alpha in terms of f of x naught minus alpha gradient f x naught. And of course, you can see that when alpha is equal to 0, this is only fx naught. So I will use the not Taylor's theorem, rather only Maclaurin's theorem for phi alpha, expand it around 0. So it's phi 0 plus alpha phi prime 0 plus other higher order terms, because we are taking that function is class C1. I am not going for second derivative. Okay. So phi alpha is nothing but f x naught minus alpha gradient of x naught, and f0 phi 0 is f at x0. I'm taking to the left side, so we are left with only this much. Alpha times, we know that gradient of f at phi alpha at alpha equal to 0 will be this much. Once we calculate, we will get this much, I mean gradient of f at x naught, and then by chain rule we will get a minus alpha, okay, I mean minus of gradient of x naught plus other higher order terms. Okay, so this is just the norm of gradient of f at x naught. Okay, alpha is positive and this is norm whole square, so that is also positive. Okay, that simply means f x naught minus alpha gradient, I mean at this point, f at this new point minus f at this point is negative. And if it is negative, that means the value of the function at this new point is less than the value of the function at the starting point. So this is an improvement point over x naught when you are looking for minimum of the function f. So finally, in general, out of this notation, we can write an iterative formula like xk plus 1 is equal to xk minus alpha k gradient at previous iterate. The problem is to find out alpha k, that means at which alpha k this function gives the minimum argument. That may be a new problem which we deal with line search method. And this algorithm makes steepest descent algorithm. The first algorithm to deal with unconstrained optimization problem. Okay. And it is very interesting. Some of its properties like xk plus 1 minus xk, and at the next iterate xk plus 2 minus xk plus 1, they both are orthogonal. Orthogonal means, suppose if it is a starting point, then x1 can be obtained going perpendicularly to this, then x2 is obtained going perpendicular to this, and so on. This is the way it reaches to the optimal solution. It has been proved. It's not new, so I'm not going to this. Okay. Another thing is, the way we just discovered the algorithm, it takes guarantee that if xk is a steepest xk is a sequence of steepest descent algorithm for a function from Rn to R with gradient not zero at xk, then every new obtained solution is value of the function at this one is always less than the value of the function at previous iterate, as long as your gradient is non-zero. So stopping point is when gradient at new iterate is 0, then we will stop only. For quadratic case, it is very nice. If your function is quadratic, it's very nice. As many as variable you will have, it will solve your solution. It will get the optimal solution in that many iterates. Okay. These are some calculus for several variable, how we use the product rule, etc., etc. Nothing, very easy stuff. Okay. So I'm not going to deal with this any further. Okay. I'm going to go to a Newton algorithm, Newton method. This is one example for steepest descent. Well, the steepest descent uses only first derivative. Okay. The use of hard derivative may result in better performance. Okay. So using that idea that we go for higher order derivative, the Newton algorithm is there. We take here the function to be twice continuously differentiable, and then again use Maclaurin expansion, and finally, rather than getting the minimizer of this function, we take this function, this quadratic function, and we deal with this only because it is almost similar to this one, and we get the okay. The first order necessary condition, since x star x naught is interior point, so we take the gradient equal to 0, and gradient equal to 0, that means we will take only this, okay, this and this one equal to 0, and out of this we need to find out a formula for x. So we make a subject, like in ninth class, we make x the subject of the formula. So what we do is we keep this over here, send this on the other side, and to send this one on the other side means it's a Hessian matrix. You will take the inverse of this matrix and send it over there, and then x is x naught minus the Hessian at x naught inverse and the gradient of f at x naught, and this gives you the Newton iterative formula. Rather than x, we write xk plus 1 is equal to xk, that means solution at previous iterate, minus the Hessian at point at previous iterate inverse, and so on, and the gradient of f at x naught. And that is the Newton iterative formula for finding the minimizer of several variable function, unconstrained problem. Very interestingly, Newton method does is, for any quadratic function, it gives you the optimal solution only in one iterate. Guarantee is over here. you take any initial point, the Newton algorithm does is over here x1 is equal to x naught minus the Hessian at x naught inverse and the gradient g I have taken like gradient. And for quadratic, the gradient is only qx minus b, so it's qx naught minus b. Once we open this up, it is this one. So x naught is cancelled over here, this q inverse b. And q inverse b is nothing but the solution of, okay, qx is equal to b. Okay? So you got the optimal solution only in one iterate in Newton method. The problem is every time you need to calculate the inverse of the Hessian, there may be problem. His inverse may not exist, then you are in trouble. And moreover, another problem when you deal with it computationally, when your initial point is far from the actual optimal solution, the Newton algorithm, rather than converging to optimal solution, it goes away from the solution. That is the problem with Newton method. One simple example I have given how you can deal with, good for students. In general, the convergence rate of Newton method is very good, provided you take the starting point sufficiently close to the actual solution. Then its rate of convergence is of order at least 2, which is very good. Okay. But as I said, it has serious demerit. If your x naught is not sufficiently close, it may not converge. Another point is at every iterate you have to compute the inverse of the Hessian. So computationally it is expensive, and it may be that inverse does not exist. I mean, Hessian may be singular. Then you are in trouble. The Newton method fails. Then several other methods arrive, which I am not going to deal with because that will give me a lot of time, take a lot of time. These materials and further Newton methods are available in these two books. This book, The Introduction to Optimization by K.P. Chang, deals with MATLAB codes. So we have prepared this one with R codes, which is freely available to everyone. And moreover, the proofs are simple because I am not a very good student. So I have written this for a student like me. Everybody can understand, whether he is from mathematics or from statistics. Little bit of calculus is enough to read this book, and codes are written very simply. You can handle this. There are several other methods. Now, the point comes, why Q derivative? Okay, Q derivative is, this Q calculus was given in 1909, more than 100 years ago, but it was not very applicable in optimization before 2016 or so, because only this Q derivative was available to us, like Hessian was not available, so it was not useful in optimization, but nowadays it is very useful. Now the Q derivative is of a function from R to R. Suppose it is fx minus fqx, 1 minus qx. Q is something between 0, 1, x is non-zero. Okay, so this is the Q derivative concept. It was given by Jackson in Transactions Trial Society of Edinburgh in 1909. Okay. Then exploiting this Q derivative, there are, entire Q calculus is there. So exploiting this Q derivative, what we have done is, we have given the extensions of steepest descent, Cauchy Newton.
Lakshman Rao, you stop the sharing.
Okay.
You have interrupted.
Okay, I'm going to stop.
No, Lakshman Rao has interrupted. You just start, sir. You continue.
Is it visible, Professor Rao? Tirupati ji.
Continue, sir. You continue. Some
Okay.
interrupted your presentation.
Okay.
You can carry on now.
Now, so Q derivative for unconstant optimization.
Present it.
We have explored, like Q partial derivatives are also available. They were available, quite late, 2005.
Sir,
And then
Statistical, sir,
yes, sir.
sorry for interruption. Your PPT is not visible. You please make it a presentation again.
Somebody is presented, sir, intermediately, so that
Professor Lakshman disturbed this one.
Stop the sharing and I just 1 second share, sir.
Stop sharing and 1 second share, sir.
I just remove the sharing, just 1 second sharing, sir. Yeah. You just share now, sir.
Is it visible now?
Give instruction to all participants, sir. Don't share in the intermediately.
Yeah, now
Okay. So Q partial derivative were available in 2005. Q gradient were available in 2016. And therefore, we were able to handle the unconstant optimization problems with Q calculus. This is all I'm trying to tell you. And those existing methods for ordinary calculus, I mean smooth calculus, they have been extended and we are extending. And one of my student is dealing with this. So these are examples how to calculate Q gradient and etc. And then we extend the Newton algorithm for unconstant optimization problem. And the algorithm is finally, this is part of our paper. So we are not going to deal with this. Algorithm is, this is entire paper he has loaded over here. Just a minute. Yes, this is the Q Newton unconstant multi-objective algorithm we have derived, and we have tested this on several functions, around 30 functions or so, and it was working faster than Newton method and better in the sense that when function is not only a smooth derivative, then even we can handle the unconstant Newton method algorithm. We have also derived, Cauchy Newton, BFGS method, etc., etc. So this is what I'm telling. I was trying to tell. I finish over here, Professor Tirupati Raoji.
thank you, sir. Thank you. A very nice presentation. And the Q optimization, it means quadratic, sir. Q.
No. It is Q calculus.
Q calculus. Okay.
Yeah, it's a different kind of calculus. So we are only replacing the previous calculus in unconstant optimization.
Oh, nice. Very nice contribution, sir, for multi-objective problems, for unconstrained optimization problems. Very interesting. And using Q calculus is also another area where first time I am just getting familiar.
Yeah.
Okay, and now it is also open for 1 or 2 questions. Please, if anybody, sir, you can stop share, sir. Yeah. Now, if anybody have question, Vishwanathan, do you wish to make?
Yes, sir. Yeah, but I don't want to interrupt others because if there may be repeatedly I am disturbing someone else's slot. That is what I am thinking about.
Give it, we will make it.
Yeah, I will make it brief, sir.
Series of questions, sir. So you try to make one question.
Yeah, sure, only one. Sir, whether this quantum calculus or Q calculus you are talking about has any advantage of catching the global minimum rather than the local minimum?
Yeah, we can find global minimum, no problem.
But when the search is trapped within a particular point in the neighborhood of the local minimum, is there a way to get out of that trap?
Well, we have not discussed with theoretical aspect of general optimization problem. We are only till now confined with computational methods only. So in general, we go from global to local. This algorithm goes from global to local. That is one thing.
But not the other way.
I agree with. Other way, I don't know yet. Viswanathan ji, I
Yeah.
don't know yet.
Thank you, Professor. Thanks for your explanation.
Okay.
Thank you. Thank you, sir. Any Shivasamy sir? Do you would
Yes.
like? Yeah.
I want to ask only one question.
Yes, sir. Carry on.
Professor Mishra,
Yes, sir.
when the conventional Newton method itself is so powerful, why we should go for Q Newton?
Which is so powerful?
On a
Karmanga,
conventional Newton.
Newton, the original Newton method.
Simple algorithms
Yeah. The simple Newton method is powerful, but when it is smooth. Suppose you are dealing with a non-differentiable function, then what we will do?
Oh, very
Because
good answer.
if function is non-differentiable, Newton method is of no use.
Okay, thank you.
Yeah.
Thank you.
Thank you, sir. Thank you, Professor Shivasamy and Viswanathan, for your active interaction. Now, I thank on behalf of organizing committee to Professor Sishkant Mishra for sparing his valuable time and sharing his valuable contributions that Q Newton method for unconstrained multi-objective problems. Thank you very much, sir, for your nice presentation. And now the next speaker is Professor Dr. S.C. Malik. Now Suresh Chandra Malik is from Department of Statistics, Maharshi Dayanand University of MD University, Rohtak. I would like to share now. Now your screen. Before that, I had to open. Share now. Sir, Malik sir,
Yeah, I'm sitting.
you have to stop.
I have to stop?
Yeah. You have to stop. I have to introduce you.
Okay.
Okay. Now, yeah. Is it visible, Professor Malik sir?
Yes, good.
Yeah.
Again.
So it is Dr. Professor Suresh Chandra Malik, Professor and Head, Department of Statistics, Maharshi Dayanand University. Malik presently working as Professor and Head, Department of Statistics, Rohtak, Haryana. His field of research specializations are reliability theory, sampling, and applied statistics. He has teaching interests in the fields of real analysis, measure theory, optimization techniques, complex analysis, probability theory, statistical methods, reliability theory, and stochastic processes. He has published 3 books in the field of real and complex analysis, and 193 research papers are into his credit. He has supervised 40 PhDs and 28 MPhil students in the subject of statistics. Dr. Malik has been invited by various academic institutions to deliver talks and to present research papers at the conferences, seminars, symposia, and abroad like UK, US, UK, Portugal, Singapore, Germany, Hong Kong, France, Spain, Netherlands, Belgium, Australia, Italy, Japan, Switzerland, and Nepal. He is a reviewer of various journals, specifically for the journals of the reliability, operational research, and statistics. Professor Malik has been a member or a life member of various academic forums. He is a founder president of Indian Association of Reliability and Statistics, and also chief editor of UGC listed journals IJSRE. Now it is being published by IARS, and he has worked as an elected member of the section Mathematical Sciences of Indian Science Congress Association. He has been associated with several universities in India as an outside expert in Board of Studies at the Ports, Academic Council, etc. He has also organized various academic activities in the form of workshops, seminars, conferences at the national and international level. He has been appointed by the UGC as a member of advisory committee for SAP. Recently, he completed UGC MRP on reliability modeling of computer systems. He is working as coordinator of UGC SAP DRS level 2 of his department. With this brief introduction to the speaker, now I would like to request Professor Malik sir. His topic is on reliability evaluation of transformed parallel series system of MNI order. Now I request Professor Malik sir to present his talk.
Thank you very much, Professor Tripati Rao, for giving a nice introduction to me. First, a very good morning to all of you.
Yes.
And we hope that, we are enjoying the academic session since last 2 or 3 days. There. So really, India is going to take some more challenges in the coming years or in the coming days.
Yes.
So, doing something in the fields of the research academics. So really, I'm very grateful to all of you for giving me a chance to interact with the professors of high dignity. Like Professor Mishra has suggested a new method, in which he tried to provide the solution of the optimization problems with objective functions having non-divisibility. But I'm going to discuss something else. But sometimes we need to use the optimization techniques to concrete solution of the problems. So here today, I'm going to discuss reliability evaluation of a transformed parallel series system of MNI order. Of this talk, the purpose of this talk is also to provide or to suggest a method that can be used or that can help the system designers and reliability engineers to develop or to evaluate the reliability of the modified systems. There is no doubt that today we have several structures of the components in a system. Some well-known structures are series, parallel, series, K out of N, and also we have non-series parallel structure of the components in a system. But we have the methods to determine the reliability of these systems. But sometimes we need to transform the systems by adding or removing the components in the existing systems. In that situation, there is no need to evaluate the reliability of the transformed system as a fresh, but we can determine the reliability of the transformed system with the help of the reliability of the original systems and reliability of the adding or removing systems. So through this talk, we are going to present a method which can help in this direction. Yes, we shall cover the introduction and motivation. Then we have defined some notations. Reliability evaluation of the transformed series system. We are considering it as a motivational study. And then before that, we need to determine the variation in reliability due to addition of components. Then we determine variation in reliability due to the removal of components. Finally, we shall discuss the case of reliability evaluation of a transformed parallel series system. Then that can be determined with the help of the variation in reliability due to addition of components and due to removal of components. Then we have some illustration, application, and conclusion and references. Now, over the years, a lot of efforts have been made by the system designers and reliability engineers to produce systems with considerable reliability. There is no doubt in it that large amount of cost is involved to produce a reliable system, and therefore it becomes necessary on the part of the producers or the developer to make an optimal balance between reliability and manufacturing cost or some other cost also. Accordingly, researchers have recently suggested some reliability improvement techniques, including structure of the components, method of redundancy, and use of good quality component. But sometimes we are not having good quality components, and in that situation, sometimes we need to consider the cost of the components also. In that situation, we have the method to improve the reliability of the system, that is the configurations of the components is mandatory to improve the system reliability. So we shall make use of the structural of the components method to improve the reliability of the system. The structure of the components has been given priority while developing a system with desirable performance and improved reliability. It is also proved that parallel structure of the components is better than that of the series structure of the components so far as reliability is concerned. All these studies have already been carried out and available in the literature of reliability. We have some other structures of components such as series parallel series, and K out of N that are being used frequently in the development of the complex systems while maintaining the optimal balance between reliability and costs. Wang et al. Developed redundancy allocation models for a parallel series system through reliability maximization and cost minimization. As in that situation, we need the help of Professor S.K. Mishra, because Professor S.K. Mishra is a well-known professor of optimization techniques. Then definitely we will interact with Professor Mishra to study all such types of combination of the components where optimization techniques are being required. So Yellowing et al. Suggested a new dynamic programming method for reliability and redundancy allocation in a parallel series method. Prasad used combinatorial approach for increasing the system reliability for assigning the components to different positions in parallel series and series parallel system. They also developed heuristic method to obtain the exact solution of the problem of selecting n number of components from available m components. Levtin et al. Obtained reliability measures of non-repairable systems with configurations of the components in series parallel and parallel series. They suggested the algorithm for obtaining reliability of these systems and pointed out that reliability of non-repairable systems increase with the increase in the number of parallel paths, while their reliability keep on decline with the increase of number of components. Chauhan et al. Developed or discussed reliability of a parallel series and series parallel system for arbitrary value of the parameters using exponential distribution. Now, in this talk, we suggest a method that can help the system designers and reliability engineers to obtain the reliability of transformed system in terms of the reliability of the original system and reliability of the additional or removed system. It means there is no need to calculate the reliability of the transformed system afresh. Only we need the reliability of the original system and reliability of the added or removed system for obtaining the reliability of the transformed system. So a method is suggested here. Let's consider a case of parallel series system of MNI order. M means number of subsystems, Ni means number of components in the ith subsystems. Ni. Suppose we are considering the first subsystems, then first subsystem, then in the first subsystem we are considering here n1 number of components in series. In the second subsystem we are considering here n2 number of components in series. Continue like this. So we have m subsystems which are connected in parallel, and in each subsystems we have n1, n2, n3. Continue like this, nm number of components connected in series. That's why we are called it as a parallel series structure of the components. And the same structure is transformed. Sometimes we need to reduce the number of components, but sometimes we need to add some more components in the system, that we call it as the updated version of the system. For in that situation, we need to determine the reliability of the updated, or you can say transformed system. So a method is suggested here. So how we are transforming the system is considered which is transformed into new one by adding or removing L number of components in the K parallel paths. If we need to remove R components from the P parallel paths. So the transformed system is obtained by adding or removing the number of components from the parallel paths, or you can say subsystems. Then change in reliability, called variation of the original system, can be obtained. The variation may because of the addition of the components, or may because of the removal of the arbitrary number of components from the arbitrary number of subsystems, or you can say parallel paths. So change in reliability is obtained. That is called variation in reliability. The effect, then we determine the effect of failure rate of the components, number of parallel paths with addition or removal of components, and the number of components added or removed to and from the original system on the variation in reliability is examined using linear regression approach by assuming exponential failure laws. The values of R square and adjusted R square are used to see the goodness of fit for the variation in reliability data with respect to the particular values of A, K, R, P. A means number of parallel paths, number of additional components in the K number of parallel paths. R is the removal components from the parallel paths. The results are shown in the graphs also. So for developing this theory, we need to define some notations. So we are considering here T, the operating type, the components, M and I, the order of, this is the order of the parallel series systems with M parallel subsystems, or you can see path, and each subsystem has Ni number of components in series, and then the subsystems are M number. So P, the number of parallel paths from which components are removed. K, the number of parallel paths in which components are added. Ri, the number of components removed from the ith path. Alpha I, number of components added in the ith path. Pit, we are considering here the reliability of the ith component in a simple series system. And Pijt, reliability of the jth component in ith subsystem in a parallel series system. J from 1 to Ni and I from 1 to M. And Cij, we are giving the notation for the jth component in the ith subsystems. RSLT gives the reliability of the original system, or you can say the fundamental system or the basic system. Then we take RSFT, the reliability of the transformed system. RIT, reliability of the ith parallel path in the original system. RI-T, reliability of the ith parallel path in the transformed system. Similarly, we have the notation for other significance. So now, first we are considering a very simple case to determine reliability of a transformed series system. You all might be knowing that in a series system, a series structure, components are connected in such a way that the system can collapse at the collapse of a single components. So we are considering here a series system of M order, having M components. Then it is a well-known result that the series structure has the following reliability, that is the product of the reliability of the components. But if our interest is to add some components in this system, suppose we add A components in the original system, then the system will have total number of components M plus A components. Then the reliability will be the product of all M plus A number of components. Then but our interest is to determine how much reliability is changed. That is variation in reliability. Then variation in reliability, because it is a series system, by adding a component, there is a decline in the reliability of the entire system. So we are considering variation in reliability as SLT minus RSFT. It means the reliability of the original system minus reliability of the transformed system. By using all the expressions we can say that change in reliability by adding a number of components is given by reliability of the original system into unreliability of the added system, because we have the results for reliability of the original system, and we also know the results for unreliability of the edit system. Because if we have the reliability of the edit system, because it is edit system is also a series system, we can obtain or we can have the reliability of the edit system. Then we can determine the unreliability, that is 1 minus the reliability of the system, edit system, that is unreliability. So the variation in reliability in that situation will be the product of the reliability of the original system and unreliability of the edit system. Unreliability of the edit system is given by this product of the reliability of the edit components. So then we need to determine the reliability of the transformed system. So if by transforming the expressions, we have reliability of the transformed system in a series system will be reliability of the original system into reliability of the edit system. We can obtain as expression 5. Similarly, sometimes we need to remove the number of components, may because of some redundant or may because of some faults. Some faults may occur in the components of the given system. In that situation, there is a need to remove the components. So how many components are required to remove? Suppose we remove R number of components from the original system. Then the system will have total number of components will be, because originally the system was having M number of components, and we removed R components. The total number of components are M minus R components. Then in that situation, reliability of the transformed system will be, that is having only M minus R components. That is the product of the reliability of the M minus R components. Then we need to determine that how much reliability changed. So variation reliability can be obtained by simple mathematical expression. So after removing this can be obtained as, in case of removing, that will be given by reliability of the original system into unreliability of the removed system divided by reliability of the removed system. So there is no need to calculate reliability of the transformed system as a phrase. It also avoids the lot of computational efforts. So we can have the reliability of the transformed system as, that is a very simple method with the help of the calculation, and by simplifying the results, we have reliability of the transformed system will be reliability of the original system divided by reliability of the removed system. So we have a very simple method to calculate the reliability of the transformed system as given by expression 9. Now we shall discuss reliability evaluation of the transformed parallel system. It means we are extended. Sometimes we don't have simple series or parallel structures in the component. May have parallel series structure of the components in the system. In that situation, sometimes we need how many components are required to be removed and how many we can add, and in which subsystem we should add, or in which system we should remove the number of components, so that the reliability remain intact. But suppose we are considering the case of the parallel series structure. Suppose the first case is before that we need to determine the variation in reliability due to addition of components. Let's consider the case of MNI order as shown in the figure. Here, this is the first subsystem in which number of components are N1. In the second subsystem, we have number of components N2 continue like this, because we have M number of subsystems. We are considering here NM number of components, maybe 10, 20, 30, maybe 100, 200, 1 lakh, 2 lakhs, maybe at any number of time of in general, the system can have any number of components. So no need to calculate the reliability as a phrase. So we have suggested a method that we can obtain the reliability of the system as. So we need to determine the reliability of the entire system because it is a parallel series system. For a parallel series system, we all might be knowing the reliability of that type of systems. We have already the results present in the literature. So the reliability of the original system will be 1 minus product I from 1 to M, 1 minus RIT. RIT is the reliability of the ith subsystem. So we can use reliability of the ith because each subsystem components are connected in parallel. So how many components are there? Ni number of components. Then in a series system, it becomes product again. So this is the reliability of the original system. Now we make some transformation here in the structure of the original system. Suppose we add AI number of components. AI number of components in the ith parallel paths in the original system, then the transformed system will be this, and then we can determine the reliability of the transformed system by simple mathematical expression, and we can have the results that reliability of the original system is this much, then variation reliability given by RS1T minus R reliability of the transformed system. So we can determine by the following formula. after calculation or simplification of the expressions, we have unreliability of the transform system is equal to unreliability of the original system into product of the k number of terms, 1 plus reliability of the original ith path into unreliability of the changed system in ith path divided by unreliability of the original ith path. All these values are known. All these terms are known, and therefore we can determine the reliability of the transformed system. No need to calculate the reliability of the transformed as a phrase. So given as expression 18. So now we can obtain reliability of the transformed system as equal to this much. Yeah, as this expression given by 19, that is reliability of the transformed system, reliability of the original system minus n reliability of the original system into k number of the terms, 1 plus reliability of original ith path into unreliability of the changed system in ith path divided by unreliability of the ith path minus 1. So we can obtain the reliability of the transformed system. Yes, similarly, suppose we have, sometimes we need to remove the number of components. In case of removal, the structure becomes this, as shown in this figure 4. So then we can obtain the reliability of the transformed system as a mathematical expression like this. So we can have the following. So after this, we can obtain reliability of the original system and reliability of the transformed system. That reliability of the transformed system, that is, first need to determine the how much reliability is varied from by making such type of transformation in the components, or you can say by removing the so and so number of components from the system. Then determine reliability variation. Then reliability variation is given by unreliability of the original system into 1 minus product of p number of parallel paths in which components are removed of the product of the terms, 1 minus reliability of the original ith path into unreliability of the change in ith path divided by this exercise given in 25. So we can determine the reliability of the transformed system. RSF equal to RSQ plus delta RT. So which is equal to reliability of the original system plus unreliability of the original system, 1 minus this. So as given in 26. So no need to calculate. Suppose our interest is, so we are justifying this theory with the help of some short example, short systems. So we are considering here an illustration. Suppose consider an original system of 2 components only, just a parallel series system of, we can say it as a 2-1 order, simple parallel, or sometimes we call it as a simple parallel system. In the simple parallel system, you might be knowing that the reliability is given by this 1 minus product, because we have only 2 components. So J from 1 to 2, 1 minus RIT, and each subsidy, there is a 2 system. Actually, there are 2 systems there. First this and second is this. But it is a simple parallel system also. So, but reliability is given by this because R1 minus RIT is the product. This product is 2 times. So we can have 1 minus RIT square. If we consider the component failure as a exponential failure, then the reliability is a well-known result, that is e raised power minus lambda IT. If the components are identical in nature, then when we can have the reliability of the original system will be 1 minus e raised power lambda T whole square. Lambda is the failure rate of the component, T is the operating time. So we can have, but suppose if our interest is to add some components in this system, suppose we add a number of identical components which follow exponentially large and are added in k different parallel paths. Sometimes we need to add a component number of components in a single path, or in 2 paths, or in 3 paths, or in 4 paths. So we are considering here k different paths where number of components, so 20 components are required to add, or 30 components are required to add, and then there is a need to determine how many components are to be added in the first subsystem, in the second subsystem, like this. So we can have to optimize or to make the management accordingly. So with failure rate this. Suppose we are considering here operating time P, operating time T is equal to 5 units, then the variation reliability can be obtained for arbitrary values of the failure rate of the component lambda and number of parallel paths in which components added and number of components added in a path. The results are shown in for particular values of this. What we say that k is the number of that is the first path, k is the 2 is the second path. Suppose in the first path we add 1 component and the failure rate increase from point 1 to point 2, then definitely there is an increase in the reliability by adding the number of components. Suppose we add two components in the first, then we add 3 components, then we can have the variation reliability. This is not the reliability. This is the variation reliability. Variation reliability goes on increasing with the increase of the number, with the increase of the failure rate of the components. It also increases with the increase of the number of components in the variation will also increase with the increase of the number of components in the subsystems. Continue like this, so we can have the particular situation, and the variation is shown in the figure. Then what we conclude that the reliability of the original system can be maintained by structuring the transformed system involving minimum number of parallel paths of added components. So what does it mean? In that situation, we need to make the changes with minimum number of parallel paths and maximum number of added components. In that situation, regression analysis technique is used only to see the authentication of the variation in reliability, whether the change or variation in reliability is authentic or not. So regression approach is used on the basis of the R square value, adjusted R square value. We can say that the variation in reliability as calculated is authenticated to determine the reliability of the. So we have, in this case, the value of the R square is 0.949 and adjusted R square is 0.892. So with the help of this, we can determine the reliability of the transformed system as. Suppose we are considering one more extensive example. Suppose we have initially a parallel series system of 2 or 2 for order. In that situation, reliability is, we have well-known formula to determine the reliability of this system, then which is given by 1 minus, if the failure rate of the components follows exponential very large, then it is equal to RS1T is equal to 1 minus e power minus 4 lambda t whole square. This is the reliability of this system. Then suppose our interest is to remove some number of components removed from the p different parallel paths or the original system with constant failure rate lambda, and we are considering the same operating time 5 units, then the variation reliability is given by this expression. So we can draw some conclusion on the basis of the particular values of the parameters in reliability. Then what we conclude here, that reliability of the original system can be improved by structuring the transformed system involving maximum number of parallel paths P with minimum number of removed components R. With the help of the regression approach, by using the value of the R square and R square, we can say that the value variation in reliability as calculated is authenticated to determine the reliability of the transformed system. So this is the area where the present study has direct application. Generally, the present study has a lot of application in power distribution systems. Power distribution system from solar on the basis of solar panels. Then we need to use a charge controller and to convert the solar energy in the form of the batteries. Then there is a need to use an inverter so that the electricity to the house may be supplied properly. So this is the case where we can have the direct application of the present study. But in this, sometimes one battery is not sufficient to restore the energy. In that situation, we need to add some more batteries to restore or to generate more energy so that proper electricity to the farm or the house or any institution may be supplied properly. So this is the case of additional battery. In that situation, we have developed the systems by adding some though and determine the reliability of the transformed systems that provides the better way to determine the reliability of the. What we conclude, it is observed that reliability variation increases either by increasing the parallel paths in which components are added or by adding more components in the paths. The second, what we conclude, variation in reliability is not uniform. This is not uniform with increase of failure rate of the components. It depends on the number of parallel paths and number of components also. There is a decline in the reliability of the original system with the addition of the components. Reliability of the original system can be restored up to an extent by adding all the components in a single parallel path. There is no need to disturb all the parallel paths. There is a need only adding the components in a single path, rather than to add these components in different parallel paths. Reliability of the original system can be improved by removing the components from maximum number of parallel paths. If there is a need to remove the components, then there is a need to remove the component from maximum number of paths, not as from a single path. If our interest is to restore or to improve the reliability of the system, rather than remove the components from a single parallel path. The reliability of the original system can be maintained by configuring the transform system using minimum number of parallel paths and maximum number of added components. Reliability of the original system can also be improved by configuring the transform system using maximum number of parallel paths and minimum number of removed components. So, future scope, the proposed method can also be applicable to other systems like series, parallel, non-series parallel system. This would help in determining directly the reliability of the transformed complex systems by avoiding cumbersome computations. So this is the all about the talk, and we have some references which are being motivational force to develop the theory in this area. Yes, thank you.
Thank you, sir. Thank you very much for your nice presentation. Now,
Yes, please, any question?
hello.
Yeah, any question, please? Suggestion, question?
Sir, stop sharing, sir. Yeah.
Yes.
Any one or two questions from audience, please.
Good morning, sir.
Yeah.
Good morning, sir.
Good morning.
Sivaswamy, do you would like to, sir?
Yes.
Yeah, make it, sir. Make it.
Professor Malik,
Yeah.
very good morning.
Yeah, good morning, Swami. Good morning.
When the experimental units are machines,
Okay.
you talk about reliability.
Yeah.
When the experimental units are human beings,
Yeah.
you don't talk about parallel or series parallel, but about mean time to failure. Why so?
Actually, this talk is different as you are thinking. If we consider the human body, then definitely human body is made of several components, maybe kidney, maybe lungs, maybe some other components also. So there is a need. God has already developed our body systematically. If there is a systematic arrangement of the components, then definitely we cannot work fruitfully.
Okay, thank you.
Yeah.
Sir, I have one question.
Yeah, please.
Sir, can we apply this for the multi-component system?
Yes, we can apply this. Actually, what we are considering here, M is the number of subsystems, or you can say parallel paths. Ni is the number of components in each subsystem. This is the multi. Yes, definitely. We can apply this method.
Okay, sir.
No need to calculate the reliability as a phrase. This is a method on the basis of which everyone can use to determine reliability of the transformed system.
Okay.
Oh, nice.
Thank you, sir. Thank you for your nice questions.
Thank you, Professor Tripati Rao. Giving
Thank
chance.
you for sparing valuable time, sir. Now we are running around 20 minutes lagging. Now, sorry to Professor GN Singh. Now I request Professor GN Singh to be there. I will share my screen to introduce Professor GN Singh, Dhanbad ISM. Yeah. Hope my screen is coming. Yes. Now, okay. I would like to show Professor Singh. Is it visible?
Yes, yes.
Yeah. Yeah, Dr. Garibnath Singh, now currently professor and HOD, Department of Mathematics and Computing, Indian Institute of Technology, Indian School of Mines, Dhanbad, Jharkhand. He did BSc, MSc Statistics, BSc Statistics, PhD Statistics, and his teaching experience are around 30 years experience, worked as faculty member in Punjab University, Chandigarh, and Kurukshetra University since July 10, 1993, working as faculty member at IIT ISM Dhanbad. He had 33 years of experience, published 201 research papers in Indian and foreign reputed journals, 17 PhD being awarded, and for which 15 as direct guide and 2 as co-guide. Of course, he guided 4 MPhils also, 5 research projects already completed. One is with the DST project under progress. 7 PhD students are working under his supervision so far. 2 projects are submitted under evaluation process. More than 30 dissertations of MSc and integrated MTech have been supervised. Academic contributions to other institutes has worked as PhD thesis examiner and paper setter of many other universities such as BHU, Utkal University, BIT Mishra, IGNOU, Agra University, St. Joseph College, among others. Worked as administrative experiences, worked as hostel warden for 7 years, chief hostel warden for 3 years, and associate dean HM for more than 2 years. Member of Senate IIT ISM and exam board since 2008 October 12, working as HOD of the department now. See, he is going to present a talk on some randomized response models for estimation of population parameters of sensitive characteristics in sample survey. Now, it's my privilege to request Professor G.N. Singh to make his presentation. Over to Professor G.N. Singh, sir.
Okay, thank you, Professor Rao. Just I will share my screen then.
Yes, sir. Yes.
Yeah, I think screen is visible to all of you.
Now, still to come, sir. Still to come.
Oh, the screen is not visible.
Now coming, sir. Coming.
Okay, okay, okay.
Yeah, it's okay now.
Okay, so before I start off my talk, I would like to thank Professor Rao who invited me for this lecture. And this lecture is being organized on the occasion of completing the 100th years of Professor Rao, Professor C.R. Rao. So which is also a privilege for us to be here in this August gathering. So though it is online, but I think we have heard about the many statistics experts who are here already. So actually here, the title of my talk is some randomized response models for estimation of population parameters of sensitive characteristics in sample surveys. Actually, basically, I am a survey expert, though I am also working in the area of data analytics and all these things. We are running a program in our department, MTech in data analytics. So just I started this program 2 years back, and which seems to be quite a successful program. So actually, as you know, in a sample surveys, non-response is a common problem. And no matter how much precision you are taking in conducting the survey, non-response will be always there. And survey statistician need to devise a different methodology to reduce the magnitude of non-response, because if the magnitude of non-response is more and more, the sample size will reduce, and whatever estimate will produce, that will be liable to question. So actually, so there are many sources of non-response, but in this paper, we are going to discuss the non-response which is occurring due to the sensitive nature of characteristics. So whenever a survey is being conducted based for the sensitive nature of characteristics, respondent will not like to give the direct answer, or even if they are answering, that will be the misleading answer. So either they will hide the correct situation, or they will give the misleading answer, and that will lead to the a poor estimate of the parameters which we are interested to estimate. So actually in this problem, we are proposing two different models. So actually these models are the partial work which has been already published in the Journal of Statistics and Journal of one is very prestigious journal. Two models I will like to discuss over here, and where the population is a cluster type actually, and we want to estimate the mean number of persons in a population who are possessing a sensitive characteristic. So this is the purpose. And recently we have worked a number of papers in this area, and which are published, actually more than 100 papers which we have published in a Q1, Q2, Q3 journals, and which are already available in the literature. So here actually, as you know that actually the dealing with the non-response, actually normally economists, psychologists, sociologists, they are having many reasons for asking the personal questions. Similarly, in a biometric sample surveys, many personal informations need to be collected, which may be stigmatized or which may be sensitive for the individuals, and individuals will not like to disclose it publicly. For example, suppose that here are some examples: highly sensitive issues such as sexual behavior, domestic violence, sex offender, HIV infection status, drug addiction, extramarital affairs. So these are some sensitive questions, and if we are going to ask the direct question on these issues, people will not like to disclose it because due to the social stigma, and they will always like to hide it. And either they will not give the actual answer, or even if they are answering, that will be the misleading actually. So this is the problem, and this is the challenge. This was actually challenge before the survey statistician before the 1960 actually. So actually this problem, the problem of non-response was first time handled by the Warner in the paper. This paper was published in a JASA, which is a classic paper in the year 1965. Actually, S.L. Warner was a social scientist in the US, and during the last 50s and early 60s, the US were suffering due to the problem of drug, and the US government wanted to know that how many individuals are consuming drugs and all these things. So at that point of time, this Warner in 1965 introduced a technique where the privacy of the individual was also protected, and he got more or less reliable answer from the individual, and he was able to estimate the proportion of individuals who are consuming the drugs and etc. So this detail is available in the paper by Warner in the year 1965. So just here quickly, I will revisit his technique. So actually what he did actually, he introduced a randomized response technique, or actually he introduced a randomized experiment where it has two outcomes. And the nature of the outcomes, that means the chances of getting a particular outcome in the randomized device was known because it was device was fabricated by the sampler itself. For example, they suppose that there is a spin, and this P is the probability. Suppose that this is the chances that individual is possessing a sensitive characteristic, and 1 minus P are the chance that individual is not possessing the sensitive characteristic. That means actually the outcomes were determined into the two category, and here actually, so this is how it was performed. So if the population, suppose that just it is the revisit, I will take a couple of minutes time. So if there is a finite population, and if A is a sensitive characteristic, and we are interested to estimate the proportion of individual in the population who are possessing the sensitive characteristics, then As per the Warner technique, a sample of size small n was drawn by the method of SRS WR, and these n individuals were provided a randomized device where the randomized device had only two outcomes, the A and suppose that the first outcome is saying A and another outcome is A complement, or means that suppose that in the one outcome it is mentioned A, and in on the another outcome it is mentioned A complement, and the individuals were asked to perform the random experiment which was not accessible to the person who is conducting the survey, and they were to reply only either yes or no answer. So there was two situation where the answer could be yes. If in the population, suppose that if the individual is possessing a sensitive characteristic, and if the outcome of the device is also coming in, so which is matching with the individual characteristics, so in this type of the situation, individual will give the yes answer, otherwise no answer. In the similar way, suppose that if individual do not possess the sensitive characteristic, and if the outcome of the device is A complement, or I do not belong to group A, then again the answer will be yes. So in these two situations, the individual will give the yes answer, right? So the probability of yes answer. So this is the probability of yes answer in the population, and suppose that in the sample, n1 individual after performing this experiment, n1 individual are giving the yes answer, and n minus n1 individual are giving the no answer, then it is very much obvious that the probability of yes answer in the population will be p pi, because in either in this situation there will be a yes answer, or in this situation there will be a yes answer. So these two are the mutually exclusive events. So the probability of this will be by the addition rule. As you know, the theta w is the probability of yes answer in the population. So from this equation, because we are interested to know pi is the proportion of individuals who are suffering in the population or who are possessing the sensitive characteristic in which you are interested. So theta w is the probability of yes answer, and this p is known because it is the probability of getting A, and 1 minus p is the probability of getting A complement in the randomized device, which is known to us. This because the device has been prepared by the sampler itself. The nature of the device is completely known, so p is known to us. So here, if you are solving it, so the solution of pi is coming here. I am putting w because it was given by the Warner. Then now it will come theta w 1 minus p 2p minus 1, but theta w is the probability of yes answer, which will be replaced by the probability of yes answer which we have obtained in the sample, because this is an unbiased estimate of the theta w. So this was the Warner technique which was introduced in the year 1965. So here we have to put a restriction that our device should be such that p should not be taken as a 0.5, otherwise it will not exist. So here, and its variance is obtained like this. So this was the technique which was introduced by Warner in the year 1965. Now, further, this technique was introduced by Greenberg et al. 1969. This is also called the Simon unrelated characteristic, Simon unrelated device actually. So what he said actually, what was the thought by them? The thought was like this: in the Warner, the two outcome was there in the randomized device. One was either A and A complement. One outcome was A and the second outcome was A complement. So they thought that if only either A or A complement, so what they have modified in the thinking that at the place of A complement, if some unrelated and non-sensitive characteristics introduced in the device, so then this will enhance the confidence of the respondents. So this was the thought actually at this point of time. So just they have made a simple modification in the randomized device. They have put the outcome A here, where A is a sensitive characteristic, where I belong to group Y is a non-sensitive unrelated characteristic. Okay, so here Y is a non-sensitive, for example, whether you play the game of cricket or whether you born in the month of April, something like that. This Y may be like this, and which is completely non-sensitive in nature. So this was the modification which was done. So again, so the same situation was performed. So in this case, the probability of yes answer here, pi y is the proportion of individual who are having the characteristic y, which is non-sensitive in nature, and pi is the proportion of individual who are having the sensitive characteristic, and our purpose is to estimate the pi. So again, in the Greenberg model, the probability of yes answer was like this. Again, on the similar line, we can have it. Now, so after solving it here, because now there may be two situations here. Suppose that the proportion of individual who are possessing the non-sensitive characteristic y, this pi y may be known or may not be known. So both the cases has been described just in a couple of minutes time here. So in this type of the situation, the probability of yes answer will be like this here. The probability of yes, theta g is the probability of yes answer, and after solving this equation, because we are interested to estimate here pi, we want to estimate pi because it is the proportion of sensitive characteristic, and whose estimate g is for the Greenberg, whose estimate will be like this, and theta g hat is the probability of yes answer which has been obtained in the sample. So theta g was replaced by theta g hat. So now this problem has been rectified, because in case of a Warner, there was a restriction that p should not be equal to 0.5. But in the Greenberg model, this problem has been sorted out. Now, further, what happens? So now, when the proportion of unrelated characteristic is known, that means in this type of the situation, there will be two unknown. So in the previous case, pi y, where pi y is the proportion of individual who are possessing the non-sensitive characteristic y, and pi is the proportion of individual who are possessing the sensitive characteristic in the population. But our interest is to estimate the pi. And here pi y, now if pi y is not known to us, then what has to be done? Whatever sample was selected from the population, that will be splitted into the two sub samples of size n1 and n2, and the n1 individuals will be given a randomized device which are having the different probability of A, and this is the P1 is the probability in the randomized device for the sensitive characteristic, and 1 minus P1 is the probability for the Y for the non-sensitive characteristics. But the two different devices were given. Why? The purpose was to form two different equations, because two unknowns are here. So if for the first device, the probability of yes answer is obtained like this. For the second device, the probability of yes answer, it is like this. And because we are interested to get the solution of pi z, where pi z means it is for the Greenberg, after solving these two equations, the solution of pi z has been obtained like this, and which is the proportion of individual who will possess the sensitive characteristics. And here actually the theta 1 hat is the probability of that is the probability of yes answer. That means out of n1 one individual answered the yes in the subsample of size n1, and n2 one individuals answered the yes answer in the subsample of size n2. So these are the estimate of theta 1 and theta 2. So it is very much trivial, and this can be replaced. Now the question was that out of n, what should be the size of n1 and n2 so that we are getting the maximum precision in the estimate. So it has been solved. All the things are available in a standard book. So because the ratio of n1, if we are having the ratio of n1 and n2 like this, which is equal to this, so in this type of the situation, we are going to have the maximum precision in the estimate pi z hat. Okay, so here now what in fact we are doing here. Now this is the proposed model. Our model is that here. So this work has been already published in the journal Statistics, and because since the time was simply given half an hour, so it was not possible to give many things. So just I will be presenting a partial work of this paper. So recently we have published two interesting models. So one model is just in the year 2019, which is with my PhD student. And this paper has been published in the journal Statistics recently. So the model one is the part of that paper. So actually here, so what in fact here we are interested to estimate. So in the earlier cases, the people who were interested to estimate the proportion of individuals who are possessing the sensitive characteristics. Now here we are interested to estimate the mean number of individuals, the mean number of on average how many of individuals are possessing the characteristic in the possessing the sensitive characteristic in the population. So, and this problem has been discussed for a cluster population, and we have introduced a two-stage. So actually in the previous work, only the randomized device was used only in the one stage, but here we have made a modification. The first modification is that the population is a cluster type. So this is the n. So this is the population which is having the n clusters. And here in the first phase, first of all, we are introducing a sampling scheme PPSWR, probability proportional to size sampling with replacement. So here, first of all, we are drawing a sample of small n clusters, where by the method of PPSWR, and then again from the selected clusters, we are drawing the samples from, for example, from M1, we are drawing a sample, subsample small m1, from M2, small m2, and so on, by the using method of SRSWR. So this is the sampling scheme which we are doing in this work. So here, using the PPSWR, we are drawing a clusters of, we are drawing n clusters, and then from every clusters, we are drawing a subsample of size M1, M2 by using the SRSWR. Now here, so this is the situation. So now here we are interested because we are going to apply the Poisson approximation. So here we are going to assume this is for the rare sensitive characteristics. And once again, we will also assume that the information on, we are also making the use of information on the characteristic which is non-sensitive in nature, but which is rare, So these two information, just like in a Greenberg, A and Y was used. So for example, these are some examples of a rare sensitive attributes: so number of AIDS patients who continue having affairs with strangers, number of girls raped by their own relatives, number of persons who are told by their doctors that they will not survive due to gastric disease, and so on. And there is a rare non-sensitive unrelated sensitive attributes we are introducing. For example, the number of persons born on 29th February, and this character is non-sensitive, but it's not a frequent. Whether you married on 29th February, whether you born as a twin baby, and so on. So these are the characteristics which are not very frequent, but they are also, and they are under the category of rare. Now, so this is our model. What in fact, so here we are introducing two randomized device. Here we are introducing the two randomized device, so that's why it is our two-stage model. We are not introducing, used only one randomized device or only one time randomized device. So here, so now the first situation is that suppose that when the rare non-sensitive unrelated attribute is known, that means suppose that just like in a Greenberg, suppose that the information is already available. Readily available in the population regarding the characteristics which is unrelated and non-sensitive in nature. So this is the case one we are doing that when the rare non-sensitive unrelated attribute is known. So this is our first stage. We are from the population. First of all, we have selected n cluster, small n clusters, and then from every selected n clusters, we are selecting the subsample by the method of SRSWR. And the individuals who are selected in the subsample are being given two different type of the randomized device in two stages. So in a first stage, the randomized device consists only two outcomes. Do you have a rare sensitivity A, or go to randomized device R2? Suppose that we are having two different cards. On one set of cards, which is mentioned that do you have a sensitive attribute A, or there are and in the remaining cards, it has been mentioned that go to the randomized device R2. R2 means the device which will be given in the second stage. And these outcomes are presented with the probability Ti and 1 minus Ti. Suppose if an individual is getting the outcome, go to randomized device R2, then he will be given the second device. Only if he is getting the outcome A, no problem. But if he is getting the outcome R2, then he has to go for the second device, and the second device is consisting 3 outcome, and these are presented with the quality P1i, P2i, and P3i. So do you have a rare sensitive attribute A? Do you have a rare non-sensitive attribute P2i? And a blank card. This is the first time we introduce a blank card, means that blank card. Now suppose that if a student, if a respondent in the second stage, if he's getting A, fine. If he's getting B, fine. B is the non-sensitive attribute and A is the sensitive attribute. We are interested for A. And suppose that if he's also getting the blank card, because 3 different types of the cards, some of the cards are having A, some of the cards are having B, some of the cards are blanks. Nothing is mentioned, and these cards are presented with quality P1i, P2i, and P3i, and these qualities are known to us. Now, if an individual is getting blank card, then he will always say no. His answer will be always no. Whenever he will get a blank card, his answer will be always no. So this is the modification which we have made in our recent RRT models, which is already published in the Statistical journal, and we have introduced a blank card. Now the quality of yes answer, now the situations here we are getting, so this is the quality of yes answer, theta I, ti, pi, I1, 1 minus ti. So this is the quality of yes answer using these 3 stages. The quality of yes answer will be like this. And our interest is, and here, now we are interested here, actually, here we are interested to estimate pi I1, actually. We are interested to estimate the pi I1 is the proportion, it is the proportion, and this is for the ith cluster. We are having different clusters. So this is the quality of yes answer in the ith cluster. It will be like this here, actually. So here, now here the, why we are using the assumption of a Poisson approximation. Now already we have assumed that A and B are the very rare attributes. That means that these pi I1 and pi I2 and theta I0, these are the very small probabilities. And if the sample size, sub-samples are, if the sub-samples are appreciably large, then mi theta I0 using the Poisson approximation, we can have lambda I0. And theta I0 means if the theta I0 is very small, because we have already assumed the characteristic is rare in nature. Now here, so now suppose that here, if we are assuming that here, suppose that from this assumption, suppose that these are the random samples that yi1, yi2. Now suppose that the responses of the individuals are being denoted by yi1, yi2, yimi. So it is very much obvious that because using the Poisson approximation, what will happen if we are multiplying both sides mi? If we are multiplying both sides mi, so this will become lambda I0 mi, this will become lambda I1, and so on. So this will happen here, actually here. So this will happen lambda I0 is like this. So this is the average number of individuals who are possessing the who are having the sensitive characteristic in the ith cluster. And from here, if you are solving it, for the, because our interest is lambda I1, we want to estimate the lambda I1. So lambda I1 will be like this, and lambda I0 will be estimated from this data. And we know that in a sample mean is the best estimate for lambda in case of a Poisson distribution. So this is the estimate. So this is the estimate of individual who are, this is the estimate of number of individuals who are possessing the sensitive characteristic in the ith cluster, and then the final estimator will be like this. So this is the final estimator. This is the final estimator because for different clusters. So for every cluster we can find, and then using the PPS here, PI is the quality of selecting ith cluster from the population. So finally our estimator is coming like this. And this estimator is an unbiased estimator, and the variance of this estimator has been derived like this here. So this is the situation here. We have proposed the estimator, and its detailed properties have been studied in the paper. Now in the second case, now when the proportion of non-sensitive unrelated attribute is unknown. In the previous case, we said that it is known, but when it is not known, the same process which was adopted by the Greenberg, these subsamples will be broken into the 2 subsamples, and the units in the two different subsamples will be different. The different devices. So here the first. So these are the different devices which will be given. So for the samples M11, M21, M31, MI1 will be given the different devices, and M12, M22, M32, something like this. That the device has been already explained here. So these are the this is the structure of the device, where the first sample of a subsample, the responded in the first sample of a subsample will be given this device, and responded the respondent in the subsample of a second sample will be given this device, and the statement is exactly the similar, which I have explained already. Now here, so why we have taken, because we have to formulate the two equations, just like the concept of a Greenberg. So these are the probability of yes answer for the first sample. These are the probability of yes answer for the second sample, and again we'll follow for the large MI1, MI2, and small theta I1, theta I2. So because these are already small, we have already assumed that the characteristics are rare. So in that type of the situation, these are the two estimates. So this will provide you the number of individuals who are possessing the sensitive characteristic in the ith cluster, and this is the number of individuals who are possessing the non-sensitive characteristic in the ith cluster. And here our final sample again in the similar way has been, the final estimator has been proposed. So this is because we are interested only for the sensitive characteristics. So this is the estimator for estimating the number of individuals in the population who are possessing the sensitive characteristic. And its properties are, this estimator is also unbiased. Their variances are here derived, and all these things. Now the second model, proposed model. So here just a simple modifications, and this paper is recently appeared in Journal of Statistical Computation and Simulation, and it's also very good journal in the Q3 rank. So it's a very good, and it's having a very good impact factor. So the proposed model, so in the second model, what in fact we are doing, exactly the same thing has been applied, what we have discussed in the model number 1, but a slight modification. Now suppose that when the rare non-sensitive unrelated attribute is known, so in the first case, now suppose that the individual who are selected in the sample, in the subsample by method of SRS WR, so there is no change here. There is no change here. It is same. Do you have a rare sensitive attribute? Go to the randomized device R2. But the change is here. Here we are making change. The second, if an individual is getting the option R2, then he has to perform the second randomized device, where again there is a 3 option. Do you have a rare sensitive attribute A? Do you have a rare non-sensitive attribute B? Blank card. But what is the interpretation? Blank card was also there. The interpretation is here. If a blank card is done by the respondent, suppose it is required to repeat the process without replacing the card. What he will do, suppose that an individual is getting the blank card, then again he has to repeat the process from here. Suppose that first time he is getting the blank card, then again he has to repeat the process from here. And if again he is, now suppose that by the way in the second time also he is getting the blank card, then he has to tell no. This is the modification. This is only the modification in the two models, the rest is same. This is the modification. That means the first time if an individual is getting the blank card, he has to say, he has to repeat the process. This option was not available in the model 1. And the second time, if by the way he is also getting the blank card, then he has to say no. So this is only the modification which has been done. And in case of the probability of yes answer, here K is the number of cards in the second randomized device. So after simplification, the probability of yes answer will be like this. And again, we will apply the Poisson approximation. And finally here, what will happen? So this is the ith number of, so lambda I0 is the number of individual in the ith cluster who will possess the sensitive characteristic will be obtained like this. And the final estimator, it is like this. This is the final estimator. This will give you the number of individuals who are possessing the sensitive characteristic in the entire population, average number of individuals. Again, in the second case, so all these things are its variance, etc., has been derived. Now, when the rare non-sensitive unrelated attribute is unknown, then what has been there, that the layout of the proposed model is exactly the similar type of the things. The same model. Here the sample has been split into the two subsamples, and two different randomized device has been provided to them. The purpose to form two different equations. So here the two different equations have been formed, just like here. Here it is like this. And again, using the Poisson approximation, the same exercise we are doing here. So this is the number of individuals in the ith cluster who will possess the sensitive characteristic, number of individuals in the ith cluster who will possess the non-sensitive characteristic, and finally our estimate is like this. This is the final our estimator, where it is the average number of individual, or we can also say mean number of individual who will possess the sensitive characteristic in the entire population, and its property has been studied. The estimators is also unbiased, so all these things are the expression. So main thing is now here a comparison of efficiency. Now one more interesting thing is that actually what happened, we have, because there is no much work is available in the literature in this area here. Actually, the Land et al. 2012 extended the Greenberg 1969 model by using the sensitive attribute. So he used the sensitive attribute, and what happened? But the technique was used which was proposed by the Greenberg himself, and only he introduced the sensitive character. The characteristic is very rare and sensitive in the nature. Similarly, the Lee et al. 2003 simply modified, and he applied it for the, but he used the simple model, the model which was proposed by Greenberg. Lee et al. 2003 extended his model using the PPS and for the cluster population, but the model was simply the Greenberg model. But what we have done, we have introduced the a two-stage model, and since there is no much work in this direction, so there was no option. So we compared our estimator with the estimator, because it was under the PPS scheme and used for the cluster sample cluster population, and the probability of yes answer for the Lee et al. 2003 was given like this, and the corresponding estimator was also derived, and the expression for his variance is like this here. So what we have done, so this is the expression for the Lee actually. Now we have compared our work. We have compared our work. So if you see that here, yeah, so we have compared our work with the work. So here we have compared our model one when the information on a non-rare and sensitive characteristic, actually the rare non-sensitive characteristic was known, that was the first case. And if you see that for the different choices of the parameters, our estimator is uniformly better. Even sometimes 700 times our estimator is better. 7 times our estimate, it is the percent relative efficiency we have calculated for the different parametric choices here. Similarly, here when it was not known, when the information on rare unrelated characteristic was known, unknown. So this is the table which we have presented here. Similarly for the model 2, for the two cases. So if you see that never in no situations our estimator is inferior than the estimator which was proposed by the estimator which was proposed by the Lee 2013. So our estimator is for almost every, because whatever parameter combination we have chosen, our estimators are beating the Lee 2013 estimator. And in this way, we can say that our proposed estimator, though this is already actually published, so there is no question. These works are already well established and well published. So actually, what we have further in the same paper, we have further extended our work for the stratified situation. And actually, these two papers are very lengthy, but this is the theme of the model which I try to explain over here. And I think that these models are very interesting and can be recommended for the practical application of the survey practitioners who are dealing with the issue of sensitive characteristics. Generally, social scientists, economists, and biometricians are using they are very much interested to collect the data on the sensitive characteristic if they are applying these models in their real life problems. So it was very interesting.
Thank you.
Okay, so this is
Thank you, Professor.
okay.
Thank you, Professor Singh sir, for your nice presentation. And I have a mind to interact with you in one conference from that. My student did his PhD under you. Am I right?
Should I stop my presentation first?
Yeah, stop, sir. Stop it.
There hang. Should I stop my presentation or?
Yeah, presentation. You stop it, sir.
Okay.
Yeah.
So yes, it is.
Professor Singh, sir, your presentation on sampling techniques is very interesting. Non-response models, randomized non-response models for estimation of population parameters, sensitive characteristics in sample survey. It's a very interesting topic. I would like to, because we are already running shortage of time of 30 minutes, almost one session time we are running late. So I request one question more specifically by anyone, please. You, Mr. Nathan, you want?
If there is nobody else.
No problem. You are the only person now. It's right now. Okay.
Okay. Sir, my question is about the sensitivity aspect of your estimator. Suppose if the factor that you consider is not that much sensitive, then will your estimator have any bias or have more mean square error?
No. It will not be. That can also be used for even the character. Actually, this is the estimator. The study has been performed in the area of RRT, actually randomized response model, and which are exclusively for the sensitive characteristics. If the characteristics are not sensitive in the nature, plenty of estimators are already available in the survey sampling.
Because in some of the estimators in the denominator, I can see P should not be equal to 0.5 in one case. And
only in one case, that was the classic paper by Warner in the year 1965. He was the first person who tackled this problem of the sensitive characteristics, and because of its mathematical structure, because in the denominator 2p minus 1 is coming, because of this the restriction was put that P should not be equal to 0.5. This was the only reason, because of its mathematical structure. But in no any other work such restriction is there. But he was the first person who addressed this issue.
Thank you, bro. Thank you.
It is a paper in a JASA journal, so it's a very classic paper.
Good, sir. What the thing is, Professor G.N. Singh has proposed models. The model construction, if you observe the pictorial presentation, that itself gives some concern on avoiding the biasness, what I understand. And
these biasness.
Yeah, no, bias, minimizing the bias or avoiding the bias.
No. Already I mentioned that whatever estimators we have proposed, we have developed all are unbiased. They are all the estimators which you have developed, they are unbiased estimators, so there is no question of the bias.
Yes, exactly. Thank you for your vibrant lecture.
Now, one request. I have actually I had a meeting from 12:30.
Sorry.
My director, so I will be leaving right now. Thank you for your.
Sir. Thank you for your sparing valuable time, sir. Thank you.
Okay. Thank you.
Now the next speaker is Dr. Ashish Kumar from Jaipur. Now I would like to share my screen and introduce the speaker. Yeah. Yes. Am I visible? My screen is visible. Hello.
Yes, sir. Visible, sir.
Sir, visible.
Visible.
It's visible, sir.
Yeah. So Dr. Ashish Kumar, right now working with the Department of Mathematics and Statistics, Manipal University, Jaipur. He is going to talk on use of GA and PSO in behavioral ability and performance optimization of physical processing units in sewage treatment plants. Regarding his academic information, Dr. Ashish Kumar currently working as assistant professor in Department of Mathematics and Statistics, Manipal University, Jaipur. He completed his MSc Statistics and MPhil Statistics from MD University, Rohtak. He got gold medal in both of the programs. Of course, he is the student of Professor Malik. He completed his PhD degree in reliability modeling and analysis from MD University Statistics Department in 2013 under Inspire Fellowship. He has published more than 80 research papers in various national and international journals and participated in more than 50 conferences in India and abroad. He is currently guided 4 PhD students and 2 students awarded PhD degrees under his guidance. His area of interest are reliability modeling and analysis, sampling theory, reliability estimation, and data analysis. With this brief introduction about Ashish Kumar, I request him to go for presentation. So I request him to make confine up to 1 o'clock. Okay?
Okay. Okay, sir.
Thank you, sir. Thank you. Now I would like to stop sharing. Right.
And thank you, sir.
Welcome, sir. Welcome.
Yes, thank you, sir, for such a nice introduction. First of all, I am very thankful to the organizers of the conference for providing me such a great platform to present my work. A very good afternoon to all present here. So, topic of my presentation is use of soft computing techniques, especially GA and PSO, in optimization of availability and performance of physical processing unit in sewage treatment plant. These are the outline of my talk, introduction, followed by literature review, some fundamental concepts. After that, system description that we studied here, assumptions, notation, state transition diagram, stochastic modeling of the system, and after that, performance optimization and numerical and graphical results and conclusion. So, as we know that from the inception of human civilization on Earth, natural resources are the key requirement for the human being as well as for all the creatures. But no one can imagine life on the Earth without these things. And since from the beginning of the 20th century, human population starts increasing rapidly, and a huge demand of these natural resources increases. At present, most of the countries faces problem due to shortage of enough drinking water, and natural resources like these have a limited stock on Earth. There are certain factors like industrialization, shrinkage, forest area, pollution. Due to these, water bodies are either in the dry state or in the state that the water is not usable condition. Due to climate change, there are many implications arise due to in the supply of drinking water, rain-fed agriculture, groundwater supply, forestry, and biodiversity. As a study, it is the fact that India accommodates 16% of the total population of the world, but water reserve in India is very limited. So, in such situations, it becomes very important that these natural resources should be handled with proper care. And the most of the issues that we are facing, they are happen due to inadequate water resource, due to inadequate faulty planning of human being and these can be rectified by putting the sincere effort in controlling such things. And one such sincere effort is that is the establishment of sewage water treatment plants for recycling the used water and utilization of that water in either agriculture and in some other area of the household. So these sewage treatment plants are helpful in fulfilling the demand of water and generate the energy in the form of gas that can be produced from the waste water. But the manufacturing and design of such plants is very complex, and it becomes necessary in that situation that we handle these systems with high reliability. And in that situation, some extra efforts we should have to put there. A lot of researchers have used many traditional approaches to obtain the or to improve the reliability and efficiency of such plants, and as well as use of soft computing is also used to handle such type of issues. However, the existing techniques, I am saying about the soft computing techniques that are used to deal the to obtain the optimum solution. They are also not so accurate. There are also some issues like poor computational speed, stuck in local optima, premature convergence are also there. So in this work, we try to develop a novel mathematical model by using the concept of redundancy, various type of redundancy as parallel, cold standby, and k out of n g type of redundancies we use here, and develop a mathematical model. After that, we take the assumption that our failure rates are the exponentially distributed while repair rates are arbitrarily distributed, and by using the supplementary variable technique and Markov birth death process, we develop the Chapman-Kolmogorov equations and simplify the model and obtain the availability and profit of the function. The availability and profit of the function plays as the role of fitness function for our genetic algorithm and particle swarm optimization, and we try to optimize the value of availability and profit performance of physical processing units. The data related to this study has been collected with the help of the plant personals, and we also share the output with them. My student visited many times to the sewage treatment plants situated in Jaipur, and the whole layout of that plant we discussed there. And at the end, we found that results obtained from particle swarm optimization performs better in comparison to the other techniques. A lot of studies has been carried out in this direction in the field of the soft computing techniques, in the field of reliability modeling, as well as some authors like Zhang et al., Veldkamp, Zhang et al., Lu et al. These persons proposed some motivational methodologies that how we can use wastewater in the household and by establishing the sewage treatment plants. And in the direction of reliability theory, in the development of stochastic models, Kumar and Malik and Agarwal et al., and Garg, Chaudhary et al., Daya et al., Saini and Kumar, they developed a lot of stochastic models and use the approaches to find under different set of assumptions to find the reliability, availability, and profit of the systems. While Kumar and Komal and Kumar, Ibling, Khanduja, Garg and Rani, they developed many soft computing techniques like ant colony optimization, so PSO, GA, fuzzy set theory also they proposed and used in the to optimize the reliability of the process industrial systems. Now these are the some fundamental concepts that we use in our study, and these concepts are already discussed a lot of times. Like reliability is the probability that a system performs its intended function adequately in a given specific period of time without any failure, and failure is that a system fails to behave its required function and accordingly in its prescribed conditions. Similarly, availability also defined as the probability, and maintainability is the probability that system will be re-established to operational adequately within a specified system configurations. System configuration can define as a device with which contains several units or system, expecting their reliabilities are that can help to anticipate the reliability of the entire framework. My supervisor, Professor S. Malik, already lecture on this redundancy techniques, and various type of techniques are already explained in his lecture. So I skip a situation like these, and after that we have some soft computing techniques. One is genetic algorithm and other one is particle swarm optimization. So this is a famous optimization techniques, and it improve the ability of an organism to is the evolutionary computation, which is inspired from biological evaluation process, and Goldberg explained in it detail. In this process, survival of individuals depend on the fitness computation, which is expressed with the help of the decision parameter. This evolutionary computation try to find out the optimum solution for a given problem from a problem space by finding out the best value of the fitness function. The whole procedure of the genetic algorithm is as follows: that at the first stage we give the initial value to the parameter. After that, we generate initial random population, we calculate the fitness of each individual, and then we check the stopping criteria. If our stopping criteria is satisfied, that is, we obtain the optimum value, then we end the process. Otherwise, we select the parents, we apply the genetic operators. Here in genetic algorithm, we have the choice that we can use to select the new offsprings. We can use one genetic operator, either crossover, either mutation, or we can choose the both, and then we calculate the fitness of each individual, and then go back to stopping criteria and check that criteria is satisfied and not, and this process is going on. So these are the steps we already discussed in the flowchart. After that, we have two genetic operators. One is crossover and other one is mutation. This crossover just tells us that when this crossover provide that how the gene, after selecting the pair of chromosome, are exchanged for reproducing new offsprings. And the process of gene exchange can be done in several ways: one-point crossover, two-point crossover, and uniform crossover. In one-point crossover, the chromosome are divided into two parts by specifying a crossover point, whereas in case of two-point crossover, we divide into three parts with two crossover points, and in case of uniform crossover, the crossover points are uniformly distributed in random fashion. In our work, we choose the one-point crossover and divide the whole set of crossover into halves. And mutation allows how new genetic material to the chromosome by replacing with the newer one randomly. There are two famous methods of mutation: uniform and non-uniform. In uniform mutation, existing chromosome is replaced by random one, and which is generated within space. Whereas in case of non-uniform mutation, the selection of gene for mutation are not uniformly distributed. Here we choose the uniform mutation for the purpose of reproduction. Applications of genetic control, design, rescheduling, robotic learning, signal processing, playing, combinatorial and optimization, and some persons in these days are using the genetic algorithm for and particles for estimating the value of the parameters for various probabilities probability distributions. Now, particle is another matter, and this is inspired from social behavior of birds when they are endeavoring for searching of a destination, and this is based on the particle swarm theory developed by Albert and Candy. Swarming consists of several individuals which coordinates themselves for finding out the solution. Individuals of the problem space are termed as particle and population refers as swarm. And for achieving optimal solution, particles change their position at a specified speed known as velocity. In searching of optimum solution, particles adjust their position based on personal as well as the global best. And we can say that they can start, it can be said that they learn from their own experience as well as others particles experience also. And this algorithm iterates the position adjustment until the convergence criteria is satisfied or maximum iteration are reached. At the end of every iteration, the position and velocity of each particle is updated, and these are the formulas given in equation number star and double star are used for finding the position of the particle at t time and used for finding the velocity of the particles. And this is the flow chart of performing the particle swarm optimization. We randomly initialize swarm for the particle, start the iteration. If maximum iteration reach, then we end the process. If maximum iteration not reach, then we initialize the population position and particle in the swarm. We evaluate the fitness function, the global and personal best of each particle, then stopping criteria is checked, satisfied, then output is the best solution. Otherwise, we go back, we update the position and velocity of each particle, we start the new iteration, we again check that maximum iteration is reached or not, and we continue in this way. So this is the basic concepts. Now I have included here a basic description of the plant, sewage treatment plant. As a broad sense, this can be divided into 4 subsystems. First is physical processing unit, second is biological and chemical processing unit, sludge digestion unit, and power generation processing unit. And the 4 subsystems again treated as a single system and further classified according to their units. And in our study in this talk, I consider the physical processing unit, and this system consists of 5 subsystems. And we use the concept of different type of redundancies in this and in this model. And here all these 5 units working in a series system, but there is internal redundancy is used there. The first subsystem is inlet channel, a single unit is used. Second subsystem is screen chamber, single unit is used. But third subsystem is raw sewage sump, and it works in the form of 3 out of 3 G form, and 1 cold standby unit is also used here. After that, fourth subsystem is arranged in the form of cold standby unit. 1 unit is operative, and initially 1 unit is kept in cold standby. And subsystem 5 work grit chamber is used in the form of 2 out of 2 with both the good units in good condition. Other description of other systems is also given. These are the assumptions for the development of my model, and proper repair facility for repair and replacement is available without any waiting time. Failure rate follow exponential distribution, while repair are arbitrarily distributed, and system perform as new with full capacity after the repair. These are the notations I used here. And this is my state transition diagram developed here using Markov birth death process. Initially, we are at state S0, and here this X, Y, Z, W, and U. These represent my original units, and this Z1 and W1 represent the standby units. if X unit fail, then the whole system is failed and go to S4 state, and after repair it come back. If Y unit fail, then it go to whole system fail and it go to state 6, S6, and in this way we develop this whole model, and on the basis of using supplementary variable technique and Markov birth-death process, we develop a system of mathematical equations, and these are the boundary conditions associated with the model, and the initial condition of the model is also given. So for finding the solution of this, we consider a particular case and we assume that repair rate are also exponentially distributed, and the above set of equations from 1 to 6 converted in this the set of the linear differential equation, and the initial condition is given. And for finding the long run availability, we take time t tends to infinity and dy dt becomes 0. So after simplification of this, we obtain the availability and profit of the function as given in the equation number 15 and 16. These are my fitness function for obtaining the optimal solution. Now we use the optimize meta heuristic approaches here, and the availability and performance of the system more depends on the failure and repair rate. So failure rate and repair rate of all the subsystems here play as a role of decision parameter in our meta heuristic approaches. Here we have 6 failure rate and 6 repair rates. So we define the range of these parameters, and corresponding to these parameters, we develop the GA and PSO code in MATLAB software, and then obtain the results for in different conditions. And the numerical results for GA is, first of all, in table number 2, we check the effect of population size on availability and performance of the PPU subsystem using genetic algorithm. In this case, we fix the value of mutation probability 0.1, we fix the crossover rate 0.5, and the number of evaluation is taken as 100. So when we fix this value, we also check the effect of mutation rate probability from 0 to 1. We also check the effect of crossover rate from 0 to 1, but we kept here between for these two particular values. When we vary the population size, then we find that when population size is 300, then in this case we obtain the probability 0.9403, and profit is also high. After that, we check the effect of number of evaluation on availability and profit. Here also, mutation probability and crossover rate are taken as 0.1 and 0.5, and population size here we take as 90. And we vary the value of the evolutions, and we find that at once in this case, when mutation probability is 0.1, crossover rate is 0.5, and population size is 90, at that time 160 evolution give us the maximum probability. After finding this, we find the PSO outputs, and in PSO outputs we check the effect of number of swarm on availability and profit by fixing the number of iterations 200, inertia weight as 1, inertia dumping weight ratio is 0.99, personal best is taken as 1.5, global best is taken as 2. So for this particular case, we check the effect of number of swarm, and we check it corresponding the population size. And when we run this program, then we find that at population size 135, under these conditions, we obtain the probability that is equal to 0.9919. And then we find the effect of iteration on availability and profit. And in the case of number of iteration, we fix that iteration inertia weight is 1, inertia dumping weight is 0.99, population size we take 100, personal best 1.5, global best is 2, and corresponding to this we find that we achieve the optimum probability in this case after the 30 iterations. So these are the graphical representation, and we find that here we achieve the optimum probability, optimum availability approximately after near about 100 iterations, while in PSO we obtain the optimum availability approximately after near about 40 iterations. So these are the some cases we consider I included here, and the effect of mutation probability, crossover rate, and those results we skip from here, and the results of traditional results of availability and performance are also not included in this work. So these are the graphical, and so from here we find that the system availability and profit is influenced by the failure repair rates, as well as the concept of redundancy. They directly influence these reliability characteristics. Here in this paper, we try to obtain the optimum availability of this of the physical processing unit of sewage treatment plant by using genetic algorithm and particle swarm optimization. So these results are helpful for system developers, and we find that the experimental results shows that particle swarm optimization techniques is outperform in comparison to the solution obtained by the traditional approach, as well as by the results obtained through the genetic algorithm. The availability obtained through particle swarm optimization is 0.992, and availability obtained through the genetic algorithm is 0.95. The results of this paper are also compared with the paper published by Goel et al. In 2019, and they used the RAMD approach for finding the availability. And another paper we also compared the results, and we found that in both the cases, results of our paper are better in comparison to that. These are the references that I use in this study. Thank you.
Thank you very much, Dr. Ashish, for your very, very nice presentation. And not only nice, it's a very qualitative presentation. You have considered all the exhaustive theoretical and classical concepts of stochastic processes, reliability, and all remaining things also. So very nice.
Thank you, sir.
Arriving to the transition probability matrices with X, Y, Z, U, V. Around 5 variables you considered, it seems. Am I right?
Yes, sir. Yes, sir. 5 subsystems are there.
5 subsystems.
5 subsystems are there in our model, and after that, for standby units,
model construction for making these 5 subsystems reliability systems. It's a very interesting transition probability matrix construction, boundary conditions, arriving to the differential equations, and deriving your output availability. These are all the things, very nice exploration, and it has to be considered as a wonderful discovery. Definitely your research deserves all sorts of applause. So really we are fortunate to have or sharing this qualitative research output on this platform. My hearty congratulations to you, and I am very much grateful to you for your active participation. If anybody wish to have 1 or 2 questions, it will be allowed. Please. Because now we are running shortage of time, 35 minutes we are running shortage of time. Okay. So, okay. Now, if there are no questions, I will thank Professor Ashish Kumar for his vibrant presentation. I wish him to make more outputs of this nature of research. Thank you, sir. Thank you very much.
Thank you, sir. Thank you.
And now the last speaker of the session is Professor S.K. Kadir Babu. Now I'm going to present his a brief profile. Okay, hope my presentation is visible.
Yes, sir. Visible, sir.
Yeah. So now we are going to have one more vibrant professor, sincere researcher, academician, and his profession and passion is teaching and research. I'm happy to introduce Dr. Kader Babu, Sheikh Kader Babu. He did his master's programs in statistics, mathematics, computer science and engineering, and did MPhil PhD also in statistics. Right now, he is an associate professor at Vellore University, Institute of Technology, Vellore Institute of Technology University, VIT University. Coming to his areas of specialization are advanced statistical modeling, applied regression analysis, neural networks, statistical modeling, theory of estimation and testing of hypotheses, remote sensing and applications, advanced probability distributions. Professional history is worked as assistant professor, senior for 8 years, School of Advanced Science during 2010 to 18. Working as associate professor from Department of Mathematics, School of Advanced Sciences, Vellore, VIT University from 18 onwards. Of course, his professorship is due. He is considered to be professor soon. Subjects taught during this service is statistics for engineers, applied probability, statistics and reliability, applied statistical methods, advanced statistical modeling, survey sampling and design, statistical quality control, sampling methods and its applications. And his academic achievements are, from the last 23 years, he is in teaching field out of passion. And administrative and academic positions, he made it. He is a board of studies chairman and member, Department of Mathematics, VIT Vellore, resource person for various academic programs conducted by other universities, selection committee member for PhD admissions, program coordinator for integrated MSc, computer science and data analytics at Vellore Institute of Technology, course coordinator for syllabus committee, etc. He's a research guide, and Dr. Babu guided for 4 PhD students, and at present 3 students are working under him for PhD program. Dr. Babu is currently running a sponsored project given by Space Application Center, SAC, Ahmedabad, Gujarat. Dr. Babu is principal investigator of the project funded by Space Application Center. And publications are, he has published more than 90 research publications in high impact fact journals. And he attended around more than 70 research papers presented in national and international conferences. Dr. Babu educated more than 5 PhD theses from various universities like Anna University, Krishnadeva University, Venkateswara University, Madurai Kamaraj University, Periyar University, etc. And he's having a laudable academic career, and with a passion he is doing the teaching. And now to talk on normalized inflection point methods for identification of rice crop phenological stages using SCAT-SAT1 satellite data. So with this brief introduction, I feel it's my privilege to invite Professor Kader Babu for delivering his thought-provoking and very fruitful research outputs today. Thank you. Welcome you. Now over to Professor Kader Babu.
Thank you. Thank you, sir.
Yeah, share the screen, sir.
Sir, sharing. Is it visible, sir?
I think still it is buffering. It's not coming.
Now, sir?
No. Present now option. You select that and then you go for your entire screen. Then you can select a window.
Present now only I given. Share. Is it okay, sir? Now?
No, no. Ganapati, can
Yes,
I?
sir.
Yeah.
Yes, sir.
Okay, it's coming. It's coming. It's coming. Yeah. Now you can share, sir.
Now just open that PPT, sir. Babu, sir.
Yes, yes. Open.
Yes, you just select that already opened in down, sir. I just opened.
Yes, open, sir. Open,
Yeah,
open.
it's okay.
Now
Okay.
it's
Now okay.
visible. Put it in a full screen mode. Okay.
Sir, is it okay?
Put it in a full screen mode, sir.
Sir,
Right. Now slide view mode.
yes.
Is it okay, sir?
Continue, sir. Okay.
Yes.
Sir, Tirupati Rao, sir, is it okay?
Yes, sir. Okay.
1 second, sir. 1 second. Okay, sir. Yes. First of all, I thank to Professor Tirupati Rao, sir, and his team for conducting a big conference, international conference, with effect from very vibrant situations. I am very happy to involve in this program. I am also one of the member in this conference. I am very happy, sir. Thank you to you, sir, and your team. Next, actually, this is my talk. Actually, I am going to give a talk on normalized inflection point method for identification of rice crop phenological stages using SCATSAT-1 satellite data. So here you see this. This topic is a very emerging topic. The ISRO is totally it's concentrated on do something on agriculture experiments only. So here, if you take a 1 year, so it is the seasons we are dividing. The first one is Kharif season. Then again, second one is Rabi season. Third one is summer crops. So in Kharif, usually the farmers they are putting the crops between July to October. This is a cropping season. Then again, Rabi cropping season is October to March. That's called winter. Then again, March and June are summer crops. So these are the three important seasons for making crops in India or abroad also. So actually here in my talk, the entire talk is divided into two parts. One is totally one of the applications, remote sensing applications with effect from agriculture only. So the second one is how we apply our advanced probability distributions in that topic only. So that I am going to give it. So see here first of all, here the entire rice crop I am taking either we can take it either Rabi season crop or Kharif. Usually Kharif only the preferable, it is suitable for rice crop. Here we have two types of crops. One is short-term crop, another one is long-term crop. So if you take short-term crop, so it will be 90 days, more than 90 to 110. So that is the period for short-term crop. So here I am taking a short-term crop. So in this crop here, that rice crop. So here we are dividing the entire 90 days into the different stages. That is the important thing. So one of the major problem to the ISRO is how to divide the entire data into the different types of rice crop phenological stages. That is important. That's called identification of rice crop phenological stages. So in using from different types of techniques. So that is the big problem. So here the entire data, so it is divided into 4 stages. The first one is puddling stage. The second one is transplanting stage. Third one is heading stage, and fourth one is harvesting stage. So these are the 4 stages, very very important stages. So then again here, see this, if you take a rice crop, it is a staple food crop in the world. It's growing 11% of the global cropland. Rice crop has 90 to 110 days crop cycle for short-term crop and 170 to 190 days for long-term crop. So the rice crop cycle broadly classified into 4 stages. So these stages also we're taking puddling stage, transplanting, heading, harvesting. So puddling stage means the land is ready to put the crop. So in this here we have some period. So this period the farmer he is growing the seedling in a nursery. So nursery he is making some seedlings. So finally the seedlings can be put into the land. So he will be ready to the land. Then again he put into the crop into the land. So that is going on. So the first stage is the seedlings are making, that means it is growing at nursery only. So then again here the next one is we're going to the next stage, that is called transplanting stage. So in that stage, so that seedlings are put into the crop, then again start for growing. That is the second stage. Then again third stage is when starts the crop starts the growing. So then it is moving to the different types of vegetations. So that is called third stage. So after that finally that's ready to cutting. So that means finally it is the harvesting stage. So here the entire data, that means entire period is divided into four things. One is puddling stage, then again transplanting stage, the third one is heading stage, harvesting stage. So here how to identify these stages? That is the big problem to the ISRO. So what they are doing, they are only using the traditional methods and doing that. But as a statistician, we have number of distributions. So we have so many number of, that means advanced probability distributions. We can apply the distribution, so we can give the identifications. So first 40 days, that means first 10 days, it is only the puddling stage. Then again after 15 to 30 days, it is the transplanting stage. 30 to some days, that is called heading stage. Easily we can analyze by using probability distributions. Here with effect from the inflection points. So inflection points of the probability distributions, we can find inflection point, automatically we can give the different types of stages. So that is I am going to give in this talk. Then again here see this, by using satellite we are getting some data. So that data usually the first type of data is microwave data. So in this the sensing of object from microwave region of the electromagnetic spectrum EMR is called microwave remote sensing. So microwave region is the EMR spectrum divided into 8 bands. They are Ka band, K band, Ku band, X band, C band, S band, L band and P band. So here out of all these bands we are taking into the Ku band only. So this is only the useful to pick the pixels from the agriculture lands. That means we interpret from vegetations. So vegetation is coming means if the greenery moves high, then automatically we can get the backscatter data sets. So that backscatter we have values. So that values we are using Ku band only. So then again the micro bands operates between 0.3 to 40 gigahertz frequency and 0.75 centimeters to 100 centimeters in wavelength range. So here the talk is 3 micro bands of course. So here but it is I am concentrating on SCATSAT1 scatterometer Ku band only. So in this talk I am concentrating only the SCATSAT1 scatterometer Ku band data only. So that is I am going to give. Then again next optical data. So here optical sensors collect radiation reflected from surface of the earth at optical region of EMR spectrum. So the objects on the earth's surface reflects different radiations at different wavelengths. That's important. The objects on earth surface reflects different radiations and different wavelengths. So by using this we are getting different types of backscatter values. Either the backscatter values may be positive or negative. Then again it operates in multispectral and super spectral region of the EMR spectrum. It provides sensing data in 12 bands. Then again Sentinel-2, this is the European Space Agency, they are developing different types of data sets. So that is also available. Sentinel-2 provides data at 4 different solutions. They are 10 meters, 20 and 40 and 60 meters. User can choose the data with different resolution, depends on type of study. So that means this only, it is looking only the European Space Agency. They are doing this data, that's called Sentinel data. But in Indian research organization, Indian ISRO, they are giving their giving the data from SCATSAT1 scatterometer data. So that only we are taking. So then again here, see what is a SCATSAT. So see, SCATSAT is a scatterometer satellite. So which was launched on September 26, 2016 from the first launch pad of the Satish Dhawan Space Center, Sriharikota. So and launched PSLV C-35, the first multi-band technology used by ISRO India. So in this time, so the ISRO they put into the different types of satellites in the orbit. So not only the Indian satellite, they are putting different 39 satellites are put into the orbit at that time. So out of all these things, our satellite is SCATSat-1. So this is a satellite providing, so completely it's with the motto of the aim of SCATSat-1 is to get the data and to analyze, to forecast on weather and cyclone predictions and track services to India also. So for that purpose only, they released this satellite that is called SCATSat-1. So then again, some brief specifications of this SCATSat satellite. So here SCATSat is frequency is 13.52 gigahertz, resolution 2 kilometers. See here. So here the resolution 2 kilometers radius. So if you take a fixed point, so that point that the sensor is going to that place, then again it is moving into the 2 kilometers radius. It will get the average aggregate backscatter value from that point. So if you put a particular point, we get the backscatter value. So that value is the aggregate value of entire data sets. That means entire area with 2 kilometers radius. Then again here, the sensors is called a scatterometer sensor, KU band. So then again, polarization also we are taking HH and VVV. So this is the brief specifications of the satellite. Then again, we come back to the stages. So the first initial stage is puddling stage. So in this stage, what we are doing, rice crop consumes more water from puddling stage to heading stage. So in this case, the farmer he flooding into the water into the land. So then again, it is ready to put into the seedlings in the land. So that is the thing. So puddling stage is the first non-vegetation. So non-vegetation means there is no greenery. So nothing. So just it is only the land is ready to put the crop. So then again in that case, and that stage is called as vegetation or no vegetation. So that's called no vegetation stage also. So then again we take the soil moisture active passive. That means the data used to identify puddling stage through moistures. Then again here they have some standard methods that is called anomaly method is the difference of two composite divided by the composite time. So see here they have a small technique that is called anomaly method. They are applying anomaly method. Then again the error also we are finding usually the error it goes to the 6 days only. The error found with the ground truth is 6 days only. But every time here when we start the process, in the middle of the process we'll go to the ground truth. That means we'll go to the particular point, the study area point. Then again we cut the data, collect the data. So that value is called as ground truth. So here we are taking only the days. How many days we are taking the error? That means how many days is fixed for puddling stage. In this case, the one parameter, that parameter is how many days we need to put this entire period. So what is the area, what is the total days, how many days for this puddling stage? That only we need. So that is the parameter only. Then again we go to the transplanting stage, then starts the vegetation. So then after transplanting the seedlings into the land, then start for growing. So one by one it is growing. So little bit it is going, starting to, it's moving to high vegetation. That means high greenery. So in this stage is first vegetation stage in the rice crop cycle. So in a rice crop cycle, it is the first vegetation stage. Then again here also applied a method to sigma naught to extract the transplanting stage. So here what we are doing, they are doing only the data, they are collecting the pictures. Then again picture give it to the some software, ArcGIS software, then again some softwares, then they are getting the backscatter value. So the values are converted to the backscatter values by using our standard normal variate techniques only. So our standard normal variate techniques, they are using inside in the software, that's called ArcGIS software. Then that values are called as sigma naught values. So that we are calling that values are backscatter values. Then again, in this case also we can find the error. That error is ground truth error is 4 days only. That is also the stages only we are finding. The next one is heading stage. So in this stage, this is the very important stage. So here I noted some of the people. Oja is a principal scientist. He is working in a ISRO space application center, Ahmedabad. He studied about this stage only, entire stage. Then again, Neelima Rani Chaube, he is a data scientist. He is not only the statistician, she is not a statistician, she is only the data scientist. He studied about all these things. Then she applied different types of statistical techniques and find the values. That means different types of values, trend values, like that only. Then again, Kiran Errakula, he is did PhD in IIT Kharagpur. Then again, now he is working in GKCIT West Bengal. He also did so many things on this heading stage only. So all people are studying on heading stage. Then again, we find they find so many different types of parameters in this stage. In the first stage, only one parameter, that is called how many number of days for this stage. That number only we can find. The second one also, we are finding only the number. So here heading stage, so this is the important stage. The yield is also starting. So the yield starting, then up to ending. That means up to after completion of the yield forming and everything is over. Then again vegetation starts to down. There is no vegetation at the end of the stage. So because of this only here, so every scientist is concentrating on this stage only. This is the important stage. Then again here I give some of the parameters in the next slide. So see here, the next one is harvesting stage. So here the vegetation index is very low in this stage due to decrease in chlorophyll. So then again here harvesting stage will come from 30 to 40 days from the heading stage. The crop stress is high harvesting stage. Why? Because here sometimes some insects are coming, then again some water problem. So different types of things are coming. Because of that only crop will be stressed. Then again early, then because of crop stress only, the yield is coming early, but yield may be decreased. That is also the important problem. This is one of the important problems. Yield may be decreased because of this only. So then again the error also found in this stage also mostly in the 5 days. How we are finding 5 days? We'll go to the study area and see the continuous observation. Finally we get the 5 days error. That is the important. Then again so here, so in this heading stage, we identify different types of parameters. One is biophysical parameter or rice crop growth. These are in the indicators of crop health. So here the biophysical parameters are the indicators of the crop health. If the crop is very grow, then again the biophysical parameters are very high. So then again crop yield also depends on biophysical parameters. There are 3 major biophysical parameters I am taking in this case. The first one is chlorophyll. Then again second one is leaf area index. Third one is canopy water content. So see here 3 important parameters I am taking. Chlorophyll, then again leaf area index, canopy water content. So these are the important parameters in this stage I am taking. So then again see here next this is the chlorophyll. So it is a green photosynthetic pigment in a plants. It absorbs mostly in the blue and to the lesser extent red portions of the electromagnetic spectrum. Hence it looks green color. So chlorophyll of rice ranges from 0 to 160 in the study area. Then again any study area we can take it. This is the area. So then again leaf area index. Li is also the dimensionless quantity that characterizes plant canopies. It is defined as the one-sided green leaf area per unit grounded surface area. The LAI of the rice crop in the study area ranges from 0 to 3.4. See here. So here we are observing what type of ranges are coming. So the chlorophyll ranges from 0 to 160. Then again leaf area index is coming from 0 to 3.4. Then again canopy water content. So this index is a reflectance measurement that is sensitive to increasing leaf water content. As the water content of the leaves in vegetation canopies increases, the strength of the decreases. The CWC of the rice crop is study area is 0.02 to 0.17. For health crops, the CWC will be 0 to 0.1. So here see this, I am taking study area. So actually I am running a project. So in that project, it is limited to the East and West Godavari districts. So I am taking this that area and finding all these measures. Chlorophyll 0 to 160. Then again here also leaf area index also 0 to 3.4. Then again the next one is CWC is 0 to 0.1, like that. I am taking this. These are the values in that area in the last year only. So then again here what I am going to do is, so these are the parameters in a heading stage. Then again now I am going to introduce different types of probability distributions. We have plenty of probability distributions. Then again the distributions are, let us suppose you see the distributions were dividing into 3 parts. The first one is discrete probability distributions. Second one is continuous probability distributions. Third one is exact sampling distributions. So these are the three important distributions in a statistics. So under this also, especially we are concentrating on continuous probability distributions. So in continuous probability distributions, so here what we are doing, so the distribution should satisfy our statistical assumptions. So the first assumption is the probability is always lie between 0 to 1. That means 0 less than or equal to f of x less than or equal to 1. So that is the initial assumption. The second one is the total probability. So integral minus infinity to plus infinity, f of x dx equal to 1. So what is the meaning of this? Here, whatever values we can take it. So if you take f of x is a normal distribution, that means the probability density function of the normal distribution. So we can take entire any value, that means minus infinity to plus infinity. It ranges from minus infinity to plus infinity. Then we can find different types of probabilities. Exponential also we can take so this much range also. Then again, if you take a uniform distribution, see here I am taking some distributions. So that is one of the distribution is the first one is uniform probability distribution. So in this distribution here we are defining a random variable x. So random variable means what? A real valued function is defined on a sample space. So we are already taking a sample space, then again we are defining a real valued function. So that means what? So we need a two sets. Then again, every element in the first set should connected with any element in the second set. So that means what? We are taking all inputs. Then again, finally we are giving output. So that what is the meaning of this? We are taking all inputs. Then again, finally we are giving output means so that output having some special characteristics. So that values are called as a parameters in a distribution we are calling. So let us suppose I am taking uniform probability distribution. So let us suppose this is the f of x equal to 1 by b minus a. So a ranges from 0 to x ranges from 0 to a to b. Let us suppose a is the smallest value in the variable, can assume. B is the largest value in the variable, can assume. Then again here, if you want the expected value, that means the mean value a plus b by 2. Then again variance is b minus a whole square by 12. So we can apply here. So if you want to find expected value simply by using different types of techniques, okay, we'll get it. But so in this study, this is the study that means the backscatter values, it is coming onto the entire area. It covered 2 by 2. That means 2 by 2 means 4 kilometer area it covered. That means 2 kilometers radius. So because of this, if we take direct average, okay, it's not a problem. But so here we have a beautiful topics in our study is called maximum likelihood method of estimation, MLE methods. So the MLE method, what we are doing, every function we are taking multiplication. Phi equal to 1 to n, f of xi we are taking. So by taking all these things, we are getting the different types of parameter. So by using maximum likelihood method of estimation, then again method of movements, we are getting different types of parameters. So that method only we are using in this case. Then again, so see here, next I am taking normal distribution. So in normal also, sigma and mu are the parameters. So it also follows bell-shaped curve. Then again, I am going to one more. So this is called exponential probability distribution. So in this distribution, so what I am taking here, the property of the exponential is that the mean and standard deviation are equal. So the exponential distribution is skewed to the right. Its skewness measure is 2. Then again, these are the some distribution probability distribution. Then again, cumulative probabilities also is called 1 minus e power minus x naught by mu we are taking. So x naught is some specific value of x only. So why I am taking x? So x is where the satellite is giving only the backscatter value. So nothing to give it. So for that value only, for example, minus 9.6, minus 9.5, minus 9.4, minus 9.3, like that only, all of the negative values only it will give. So because of this only we are doing. So see here, I am going to conclude this. So here our concept is inflection points. So what is the inflection point I am taking in this case? So see here, curve have a variety of features that can be classified and categorized. One item pertaining to curve that we can consider is whether the graph of a function is increasing or decreasing. So see here. So entire data I am put into the graph. So I just take days on the x-axis, then again backscatter values on the y-axis, then I draw a frequency curve. So then again see what happening. So another feature pertains to something known as concavity. So here I am observing the entire curves into concavity. So where the concavity ends, I can cut the point. So that point is called as inflection point. So each distribution having more than one inflection points, not only one, not only two. Why? Because f double dash x is less than or equal to 0. So because of that, where it happens, all points are called as inflection points. So these can roughly be thought of as the direction that a portion of the curve faces. More formally, concavity is the direction of the curvature. So the portion of the curve is said to be concave up if it is shaped like the letter U. That is the concavity. The portion of the curve is concave down. It is shaped like the following called intersection symbol. So it is easy to remember what this looks like if we think about a cave opening either upward or concave up or downward for concave down. So an inflection point is where the curve changes concavity. So that curve changes concavity ending point, we can take it. So that point cuts the stage. So the starting to, usually we can take it. So where is concavity ends? So that's called one stage. So next concavity is second stage. Next concavity. So here, so the values are negative. That means all are so many inflection points we are getting, but we are taking the maximum negative value. So that value identifies the portion where it cuts. So that is called inflection point method. So before that also, if the values are minus 9.6, minus 9.5, so these values are sometimes it's difficult to study. So in this case, the all values are converted into 0 to 1 by using normalization procedure. That means x minus minimum by max minus min. So we can apply this procedure. All values are keep into the values between 0 to 1 only. So that is called inflection point structure. So here you see this, the last I'm going to see, sir, 1 minute. So in this calculus, the derivative is a tool that is used in variety of ways. While the most well-known use of derivative is to be determine the slope of the line tangent to the curve at a given point. There are other applications. One of these applications has to do with finding inflection points of the graph of the function. See here, one more point. If the graph of y equal to f of x has an inflection point at x equal to a, then the second derivative of f evaluated at a is 0. So see here, a is 0 means sometimes it may be having two values only. But if we take less than or equal to 0, we have more values. We write this in mathematical notation as f double dash of a is equal to 0. If the second derivative of a function is 0 at a point, this does not automatically imply that we have found an inflection point. However, we can look for potential inflection points by seeing where the second derivative is 0. We will use this method to determine the location of the inflection points of the normal distribution. Not only normal distribution, any distribution we can take it. So see here. So this is the procedure for normal distribution. We can take it. This is procedure inflection point procedure for the normal distributions. So that is the procedure we can differentiate. So that means you can differentiate the different types of Rice-Krafft phrenological stages using for SCATSAT scatterometer data by using normalized inflection point technique. So here I am giving some references. So that is called, these are only the my publications only. So this first paper is published in Environment Science and Pollution Research. Then again, second paper, it is also published in Journal of Indian Journal of Ecology recently. So these are the recent publications only. Then again, one more publication. So Kiran Errakula, he published the paper in 2018, study on paddy phenomics, ecosystem and yield estimation using space-borne multi-sensor remote sensing data. So this also published in Journal of Agromateriology. So these are the some standard references for my slides. That means I given slides. So this is my presentation in this talk.
Thank you, sir. Thank you, Professor Kalan, for your
thank you, sir.
vibrant presentation, and moreover, the very happy phenomena that you have shared your research work, which was done in a project work. Am I right?
Yes, sir. That's my research only. ISRO.
One data.
Yes, sir.
Developing the models.
Yes.
And these are mostly suitable for uniform distribution, exponential, and normal distributions.
Yes,
and exploring the parameters out of the data. This is a very novel approach, and where statisticians are supposed to explore different parameters that can measure the population behavior. So really, it's a wonderful work, and having knowledge of theory is some aspect, and applying the theory knowledge to the context, where particularly you did your thing for agricultural context.
Yes, sir.
Probably you are studying with for output maximization related, am I right?
Yes, sir. Yes, sir. Output only.
Agricultural output related,
Yes.
and you
Yes.
have considered three variables like chlorophyll
Yes.
formation and
Yes, sir.
leaf
Yes.
leaf measurements or something
Leap
like
year index. Leap year index.
yeah. So
Yes.
these are all very interesting parameters that are supposed to influence, might be hidden
Yes.
to
Yes, sir.
affect the output. Okay, very interesting that applying probability distribution theory for
Yes.
exploring the agricultural products, and through, but that too it is a project work you have completed with what is that project funded by whom?
ISRO, sir. SAC Ahmedabad. Space
Yes.
Applicant Center, Ahmedabad.
Space Authority, no? Okay.
Yes, sir. ISRO.
ISRO. Okay. Space Research Organization.
Yes, sir. Space Research Organization.
So very
Space Applicant Center, Ahmedabad.
very commendable work you have done. And
Actually,
we are lucky. Our conference delegates are lucky to listen your presentation.
Thank you, sir. Thank you so
Definitely,
much.
it is thought provoking and much productive. I hope the total session is fruitful. And I have considered that today's session we have 6 speakers. All
Yes.
speakers have made a very nice presentations, and participants will get the benefit out of it. And thank you, Professor Kader Babu, for sparing your valuable time
Thank you,
and
sir.
sharing your valuable work.
Sir,
So,
one word.
yes.
So because of you only, I am growing. Why? Because you are my inspiration.
Okay.
So
Thank you.
even though I have so many teachers,
Yeah.
but I don't know. I cannot say anything. So but because of your
We will speak.
motivation.
We will speak on the dashboard. Okay.
Yes, sir. Yes, sir. Yes, sir. Anyway.
Other people may not be. That
Yes.
Okay.
Yes.
We will.
Thank you, sir. Thank you so much, sir. Thank you. Okay, sir.
So you have good appreciations from the chat box also.
Thank you,
Participants, Maria, Jija, Paratur, Vincent.
Yes, sir.
Very informative presentation, sir. Dr. Kumar. Okay, if anybody wish to interact with Kader Babu, one question will be allowed. Okay.
Sir, can I, sir?
Yes. Tripura Sundari, madam.
Yes, sir. Can I,
Dr. Tripura Sundari is a quantitative from Please, madam.
Yes.
sir, can I ask, sir? Am I clear? Sir,
Yes, ma'am.
Kader, sir, it was a wonderful presentation. There were so many, so many branches within it. So I was trying to observe everything. I have only two doubts. Two doubts I have.
Yes.
First one, I want to know that anomaly method you're using for the budding stage only, sir.
Yes, madam. Yes, ma'am.
Only for budding stage you're using
Only-
the anomaly
yes,
method. Is it
only-
true, sir?
Yes, madam. Yes.
Second one is you said the data has been collected and they are using for prediction and forecasting. So is the data collected, this forecasted data, did it work well? I want to know that, sir.
No, madam. The data is collected from SCATSAT satellite data.
Yes, the satellite data you said is collected.
Yes. The data is available in SAC Ahmedabad website. So you go to the Space Applicant Center Ahmedabad. They give the data every day. They are giving one picture. So they cannot give any data. They give one picture. That picture will put into the software, ArcGIS software. Then we get the black scatter values. We have only one choice. So that is we can get only the black scatter values. We cannot do anything. So see here, leaf area index, chlorophyll, that and all we cannot do. So we will do only they give the black scatter values at visitations only. So it's only vegetation. If it is a granary more, we get the more backscatter. Granary less, so less only. So it is limited only for agriculture.
Okay.
You understand, madam? The software cannot give any parameters for SCATSAT 1.
Okay.
If you want to any this type of parameters, you go to the Sentinel-2 data. Yes, ma'am. Yes, thank you.
Okay, sir. Okay, sir. Thank you, sir. Thank you, sir. Thank you, sir.
Okay, thank you. If anybody is there, okay. Otherwise, we will wind up this session because we have to vacate this conference room for next session. Okay. So now next session will be started by 2 o'clock. And actually we are in the lunch time, 1 to 2. So you are all welcome to join at 2 o'clock so that we can have the next session. Right?
Okay.
Thank you once again. Thank you very much.
कैमरा बाहर आ
Hey, Manu.
Sir, please mute your mic, sir.
Manu.
Sir, chat person is not joined, sir. Please correct. Please unmute and speak, sir. Yeah.
No. నేను మాట్లాడింది వాళ్ళు వినిపిస్తాం. Welcome,
Hello.
Naveen Chandra.
Thank you, sir. Thank you, sir.
Welcome.
Thank you, sir.
So, you are now reporter now.
Yeah.
So, the change was requested to Viswanathan. Okay. I think that was
Okay.
communicated.
Yeah. I got, sir. I got.
Okay.
I got the information.
Thank you.
Yeah.
Now it is 2 o'clock. Then Viswanathan was a contact. Yeah, Viswanathan is already there.
Okay. Shall I start?
Hello, sir. Viswanathan, sir. Viswanathan, sir, are you there? I think he is online, but thing is different. Viswanathan from Presidency College. Professor Viswanathan. That session was up to 150 previous session. So he may went for lunch.
Acha.
I'll call him.
Okay, no issue.
Viswanathan, sir. See, he is in the impression from 3 to 5.
Acha.
So, but now I phoned him, he will join.
Acha.
Good afternoon, sir. Sir, this is the technical session 3, right, sir?
Yeah.
Thank you, sir. Thank you.
Jay Shankar Radhakrishna.
Yes, sir. Yes, sir. Good afternoon, sir.
From where?
Sir, actually, I am working as a mathematics teacher in Dubai.
In
in Indian high school, Dubai.
Dubai. Okay. You are interacting from Dubai now?
Yes, sir. I'm pursuing my PhD in Presidency College under guidance of Dr. Ravanan.
Okay. So your math teacher there?
Yes, sir. Yes, sir. Yeah.
Good. Welcome.
Thank you, sir.
So
I attended last December.
Now we have many comfortables that we can interact from any part of the globe.
Yeah, this is an advantage. So this is an advantage in the pandemic.
Yes.
In the pandemic situation, I could attend the conference.
Yeah.
Otherwise, all the way I have to come to India and attend. Sir, December also I attended Pondicherry conference in university.
Yeah, okay.
Very useful. Sir,
now we have to thank to the COVID pandemic situation. We are also having very positive sides also. If not, it is we may not interact physically.
With less expense, I'm able to present it.
Yeah, very expensive, time constraint. Many constraints are there.
Yeah, correct.
Physical presences. Rohit Bharadwaj. Welcome, Rohit Bharadwaj. From where you are? Rohit Bharadwaj.
Hello, sir. I am from Delhi.
You are from Delhi. Which
Yeah.
Delhi University or any?
No, I am working as an academic associate in IIM Bangalore.
Okay. You are in?
In decision science area.
Okay. So Jai Shankar Radha Krishna. So now we are able to see your face.
Thank you, sir.
Okay, good, sir. Welcome, sir. Welcome.
Thank you very much, sir.
Where you did your master's degree, sir?
In Vivekananda College, Chennai, sir.
Chennai.
Vivekananda College, Chennai, yeah.
Vivekananda College. Our Vittal Sab, PR Vittal.
Yeah, he was my MPhil co-guide in
very
Vivekananda
good.
College.
Vittal sir also participating in our conference.
Yes, sir. Yeah.
Okay. Viswanathan sir, welcome. Sir, Naveen Chandra.
Yes, sir.
Now you can start. Right.
Okay,
I'm just making chatting with you people up to your interaction.
Thank you.
Stress relieved, sir. Stress relieved now.
Yeah. So far it is informal. Now onwards formal.
Thank you, sir. Thank you.
Right.
Estimation.
You can start, sir.
I welcome the third technical session of the second day of international conference, and today this session is going to chair by the Dr. N. Viswanathan. He is Associate Professor, Department of Statistics, Presidency College, Chennai. His qualification PhD in Statistics from University of Madras. He is a qualified CSIR UGC NET and higher diploma in computer hardware and networking. He having 26 years of UG teaching as well as 25 years of PG teaching experience, and he has published 12 research paper in national journals as well as 7 papers in international journals. He having interest of publication in statistical methods, business mathematics and statistics, business forecasting, quantitative techniques, operations research, biostatistics, statistical inference, real analysis, design of experiment, sampling technique, stochastic processes. And he having also the interest of Photon, Basic, Pascal, C++ languages, and he having the research experience 3 years, served as assistant research officer in prevalence study conducted by Indian Council of Medical Research, ICMR, survival analysis in informative censoring, and he having the area of specialization in statistics, time series model building and parameter estimation and testing, discriminant and factor analysis, inference, survival analysis, general linear models, multi-dimensional scaling, non-parametric testing, and also having area of specialization in mathematics, measure theory, and integration, real and functional analysis. So with this remark and his brief about sir, I would like to invite Professor Viswanathan sir to chair this session. Professor Viswanathan sir, please welcome.
Yeah, thank you, Professor. Thank you, Professor, for those nice introduction. I don't know how far I deserve it. It's a simple thing that since Professor Tirupati Rao was asked, I was forwarded. Okay, I think this session consists of.
Thank you, sir, for
Thank you, sir,
accepting
for
the short notice.
Thank you very much, sir.
Accepting our invitation in a short notice. Thank you very much, sir. You are welcome.
Yeah, thank you, Professor. So I think let us get into the business directly because of shortage of time. So
Yeah,
I think from 2 to 5 we have say some totally how many? I think the running number is skipping. I think
I can tell you, sir. Just a minute. I think 7, 9,
13.
Yeah.
So I think if it is 13, roughly, I think you can, if you fix around 20 minutes, I think we can.
Sir,
Yeah. Yes,
13
please.
papers hello, just a moment,
Yes.
sir. There are 1 or 2 papers yesterday, due to technical issues, they were unable to present. Okay. That people are also there. Around 2 papers are there in your session.
So, sir, you go 10 to 15 minutes maximum?
10
15,
minutes,
I think.
we have made them 10 minutes, but practically it will go 11 to 12 minutes. Okay.
Yeah. On an
So
average,
therefore, make announcement as 10 minutes, sir. Then it will
10
be
minutes,
good.
sir.
Sure, Professor. So as the time constraint goes, we will fix it to 10 minutes. Every participant, okay, they can describe or highlight their main features, possibly to cover the entire thing beyond the scope of the time. So they can highlight key features and they can proceed. So 10 minutes is the 10 minutes is the time limit. And please, I call upon the first candidate, Mr. Jayakumar, R. Jayakumar, and his topic is estimation of survival probability for lung cancer patients using Kaplan-Meier approach. Whether the candidate is ready?
Good afternoon, sir. Yes, sir.
Please start.
You are welcome.
Sir, are you able to see my presentation, sir?
Yeah, no, not presentation,
No,
but
please
share,
please
sir.
share.
Yeah, sure, sir. 1 minute, sir. Sir, now?
I think there is a time lag.
No.
We will check it out. Now it's getting.
It's coming.
Is it clear, sir?
Yeah, it's clear. You can maximize and proceed.
Okay, sir. Respected professors, dear participants, good afternoon. My name is Jayshankar. I work as a mathematics teacher in Dubai, and I am pursuing my PhD in Presidency College, Chennai, under the guidance of Dr. Ravana. The title of my paper today is Estimation of Survival Probability for Lung Cancer Patients Using Kaplan-Meier Approach. The order of presentation would be abstract, introduction, materials and methods, results and discussions, conclusions, limitations, and references. Amongst all statistical procedures, survival analysis plays a vital role if the outcome variable is time. In our case, it is death. Survival analysis preferred over other regression analysis.
I think somebody needs to mute because sound is interrupting. Somebody, I
request the remaining people, please mute your mic. Please.
Yeah.
Survival analysis preferred over other regression analysis as it accommodates censoring concepts very well. This is the unique feature of survival methods. Our study consists of 168 lung cancer patients with 7 covariates. Though we have 7 covariates, in our study we have taken only 2, age and gender. In this article, the survival probability is estimated non-parametrically because the survival time do not form any distribution. Confidence interval for survival probability and median survival time are calculated. To compare the two survival groups based on gender, survival comparison test, log rank test, and Wilcoxon tests are used. In R, we also have provision for Taran-Warrior test, Peto test, Flemington and Harrington test, but we confined with only these two tests in our study. The study suggests that there is a significant difference in survival pattern of based on the gender. Survival analysis is a collection of statistical procedures for data analysis for which the outcome variable of interest is time until an event occurs. And the survival analysis not only deals with clinical trials and biological studies, it also used in engineering, and they refer as reliability analysis. Here, the event could be measure the failure time. In economics, it is referred as duration analysis, and here the time could be how long a company sustains in the market. In sociology, they refer as event history analysis. The unique feature of survival methods is censoring concept. That's how the survival method differs from ordinary regression methods. Censoring in layman's definition, it just simply don't know the survival time exactly. There are three possible reasons for censoring. The first one being the person survives until the study ends. Suppose if our study time is 3 hours, 3 years, and the patient did not experience the event, then that is considered as censored. A person lost follow-up, a person withdraws during the study. Based on this, we classify the censoring into right censored, left censored, and interval censored. There are three major goals of survival analysis: to estimate and to interpret survivor and hazard functions, to compare survivor and hazard functions, to assess the relationship between explanatory variable and the survival time. So among the three goals in our study, we emphasize only on the first two. That is, we have done estimation, interpretation, and comparison. And also, we didn't touch upon the hazard functions. In our primary study, we are done only on survivor functions. Our study data consists of 168 lung cancer patients, in which 121 patients, approximately 72% attained the event, and the remaining 47 patients are censored. The covariates, age, and gender we have taken. However, this data set contains 7 covariates. To estimate the survival probability, a non-parametric approach based on the Kaplan-Meier method is used. To find the survival patterns of male and female patients, KM Kaplan-Meier curves for two groups are drawn using Survivor, and analysis is done using survival package. To verify whether the statistical difference exists between these groups, we used hypothesis test like log rank and Wilcoxon test. This S of t indicates survival function. Basically, it is a probability of a patient surviving beyond the time t, and the range of the survival function is 0 to 1 because it's related to the probability. As t is 0, that is initially the survival probability is 1. As t is getting larger, when t tends to infinity, the survival function approximately getting to 0. The survival function is a smooth and continuous curve theoretically. In fact, we can say it is non-decreasing. In practice, the survival function will be a step function. That is, whenever there is no event between the two time interval, the graph will be horizontal to the x-axis, parallel to the x-axis. That's the reason the curve looks like a step function. Survivor data are rarely normally distributed, mostly skewed. In particular, it is right skewed. And here, the Kaplan-Meier method is also called product limit method. Here, this equation, survival of a patient surviving beyond the time ti is equal to, he has survived up to the previous time into 1 minus number of event takes place during that time divided by number of risk factors. Since we use this product of two quantities, so we sometimes call Kaplan-Meier method as product limit method. In R language, we have syntax SUR. Using that, we constructed survival table. Here, the first column indicates ordered failure time, number at risk, number of events, survival probability, standard error, and confidence interval. Now, we can interpret the first row as with 95% of the confidence, the probability of a person surviving beyond the time 5 days is 99. And the second row can be interpreted as with 95% confidence, the survival probability of a person beyond 11 days is 98. And it goes on, as we can see from the table, that the median survival time is 300 days. Also, as the days increases, the time increases, the survival probability is decreasing, but it never tends to 0, because after the observed survival time, the remaining patients are censored, so that we can see on the graph as well. Using ggplot2 in R package, we constructed this Kaplan-Meier survival curve. Here, the vertical drop indicates the event occurred, and the cross on the graph indicates censored item. The horizontal lines indicates there is no event took place between the two survival time. Also, we could see the median survival time is approximately 310 days. The graph also, the table also shows the same thing. In ggplot2, the Kaplan-Meier curve for male and female patients are constructed. This visual representation indicates that the survival time of the female patients are always much better than the male patients throughout the interval, throughout the time period. Also, we could see that the median survival time for female patient is 426 days approximately here, and that of for male patient is 286 days. Is obtained from the log rank test. It's a hypothesis test. Here the null hypothesis is there is no difference between the survival pattern. So we have the evidence to believe that, to reject the null hypothesis and state that there is a difference in survival pattern of male and female patients. R also gives risk table, and also it gives censoring. And this is my interpretation. As we know, we have the option of using different tests. This number of censoring pattern will help us to decide.
Sir, sorry to interrupt. You have one more minute
Yes,
to
sir.
proceed, so you can quickly summarize.
Oh yeah, sure, sir. Sorry, sir. So okay, sir. Then here, using the R survdiff function, we have constructed a log rank test and observed versus expected. As we can see, it's the probability is 0.013, and there is a limitation for this log rank test. It can give only there is a difference or not, but it cannot quantify how much difference is there. That is one of the limitations of. And also we have Wilcoxon test, and it's an alternate to log rank test. The difference between this Wilcoxon is Wilcoxon gives much more emphasis on initial stage, whereas the log rank test takes equal weightage throughout the interval. Conclusion. The basic concept of non-parametric model, the Kaplan-Meier outcome represents as time increases, the survival probability decreases, that we have seen in the graph. Log rank test table shows that there is a significant difference between the male and female patients, and the curve also represents the same with the p-value 0.013. The Wilcoxon test also confirms that the result at 5% level of significance with the p-value 0.009. From this, we can understand that gender plays a major role in mortality of the lung cancer patients. There are some limitations. Kaplan-Meier is not a regression model. Since it is a non-parametric, we cannot summarize the relationship between survival time and other explanatory variable. Simply, we can interpret that there is no functional form. it can only incorporate category variables and not continuous ones. These are the references. Thank you. Thank you very much, sir.
Thank you, sir. It's a good presentation. And now the floor is open to questions from the audience.
I have a question.
Yeah, please, madam.
Sir, which sensing method you use in this?
The survival data here, it's a right sensor.
Okay. Okay. Thank you.
Any other question?
Hello.
Yes.
Sir, only you choose only gender and age for your categorical variable, explanatory variable.
Yes, sir.
What is the criteria for selecting the covariate from?
Sir, actually, in the study data, I had like age also one of the covariates. Then I had weight loss, then pH cock. There are 7 covariates. Since my this is a basic presentation, so I didn't use any covariates. So only gender only we used, and we are planning to use other covariates in a pH semi-parametric Cox model.
Okay, thank you, sir.
Okay, if there is no other question, then I have one specific question. See, the problem is normally in a year we are now trying. You are trying to correlate the lifetime of cancer patients, right, to some variables, right? Some variables. So even I think some clarification for the candidate who have raised the question, why not some other variables? Okay, and even you said something with respect to age, right? So even though age is a continuous variable, you can group it into
we can also yes, sir. We can also
categorize.
categorize into we can also categorize into
in that way you can again bring them also into the ambit of log-rank test and Kaplan-Meier. That is one way. But the inbuilt or hidden disadvantage is that you can bring in any number of continuous variable after discretizing it. But the problem is we cannot deal them simultaneously. I don't know whether there is any two-dimensional Kaplan-Meier estimator, any such thing. So that may be because anyway we are dealing with groups, okay, and that groups can be, say for example, if age is divided into above 60 or below 60, something like that, and gender is defined into male or female or even transgender for that matter, we can bring in at that category. So altogether we have, say, some 6 categories, and why not the log-rank test when it operates well with any number of categories? But again, the problem is with respect to how far it captures the interaction effect and other things will be there. So to begin with, as you mentioned, this is a good beginner's work, but probably what I expected or what normally is expected is something like you should include some clinical variables associated with cancer, right? So cancer, okay, here it's age or gender, they are mostly considered as socio-demographic variable. So in that sense, if any close variable like something like BMI or other clinical variables, be whether that particular candidate have diabetic or non-diabetic, okay, what about their other, so you can search through literature what are all the features that normally clinical features or pathology of cancer that influences the, so on that basis if you are able to develop a distinction, okay, so then that will throw more light on the pathology of the disease. Of course, gender comparison and others, but if there is no difference also, we can use it as a control variable when we go for as you said, semi-parametric Kaplan-Meier proportional hazard model. Anyway, it's a good presentation. Thank you.
Thank you very much, sir. Thank you very much.
I think we can move to the second candidate. It is Mr. Kapil Kumar, and its topic is stress strength reliability estimation for inverted Pareto distribution under progressive censoring. Whether the candidate is ready?
Sir, he is not present, sir.
Okay. So then we'll move to the next one. His name is Habibur Rahman, and the topic is parametric modeling of case specific or cost specific sort function for the analysis competing risk survival data. Whether Rahman is present here?
Yes, sir. Yes, sir.
Sir, can you start now?
Yes, sir.
Time is 10 minutes. Okay, I will give an intimation by 9 minutes. With the rest of 1 minute, I think you can consolidate and complete.
Yes.
Please start.
Yes, sir. I am visible.
Yeah, you are visible, but start sharing.
Your presentation is not visible.
I started, but it is not starting.
Yeah, there will be a time lag. Let us wait for a few seconds.
You have to go present now.
Yes, sir. Yeah.
You have you open your file?
Yes, sir.
Then you go. You have time, Raman?
Yes, sir. Yes, sir.
Then shall we go to next person?
Sir, my screen is visible now.
Now visible.
Yeah, it's
now
coming
visible.
out. It's coming.
Please go.
Respected Professor, Chairperson and Organizer of the conference, good afternoon to everyone. Myself, Habibur Rahman, and I am the Research Scholar of Department of Statistics, Pondicherry University, and I am working under the supervision of Dr. Navin Chandra sir. Today, I am here to represent my research work entitled Parametric Modeling of Cause-Specific Hazard Functions for the Analysis of Computing Survival Data. The outline of the presentation are on screen. First, I start with the introduction. The situation of competence arises when an individual can experience a mutually exclusive type of event, which commonly encounter in public health, demography, actuarial sciences, and engineering applications. For example, in bone marrow transplant clinical trial, where a patient can experience time to relapse, time to chronic graft versus host disease, and time to death. The analysis of lifetime data in the presence of competing is based on two approaches. First is latent follow time approach, and second is the cause-specific quantities approach. The latent follow time approach is not get much considerable attention in survival analysis because of the independency assumption of hypothetical failure time. The two cause-specific quantities, namely cause-specific hazard function and cumulative incidence function, get the considerable attention in survival analysis. Cause-specific hazard function is nothing but the instantaneous failure rate due to a particular cause J in the presence of all other risks, which is given in equation 1. And cumulative incidence function is the cumulative probability of failure due to a particular cause J, which is given by equation 2. Since we are considering the competitors are mutually exclusive, so therefore the overall hazard function and the overall distribution function is defined by HT and FT. The heterogeneity in survival analysis are well organized by the Cox proportional hazard model and which can be extended in terms of competing setting using equation 3. The non-parametric and semi-parametric are well known for analyzing the competing survival data. The advantage of semi-parametric or non-parametric inferences are they are easy to implement and free from the assumption of underlying distribution. However, parametric models are another available approach for modeling of cause-specific hazard function. If the parametric model select correctly, then they provide the more robust and efficient estimates. Parameterization of cause-specific hazard function can be done by specifying some well-known distribution form of baseline hazard function H0JT in equation 3. Winchoi and Gale estimate the absolute cause-specific hazard function using exponential distribution. Statement Agdigmem considered the constant cause-specific hazard function. Jeong and Finn compared the viable cause-specific hazard likelihood estimates with direct likelihood approach by assuming improper Gompa distribution for cumulative function. Anjana and Sankaran assumed inverse viable reverse cause-specific hazard function. Lee considered the parametric quantile inference based on the viable cause-specific hazard function. The commonly used parametric survival models are exponential and viable, in which only monotone behavior of the hazard function can be accommodated, and they are incapable to accommodate the non-monotone behavior of the hazard function. So, the light of these issues, we consider a virtual distribution as a baseline model through equation 4. The behavior of the hazard function of the virtual distribution is initially increasing and starts slowly declining, which is given in figure 1, B figure. Survival function and cumulative cause-specific hazard function are given by the equation 5 and 6. The objective of the study, the parametric first objective is study is parametric formulation of cause-specific hazard function using Butterwell distribution and the estimation of cumulative cause-specific hazard function using maximum likelihood as well as Bayesian method. The Bayes estimates are obtained based on class of known informative priors and two loss function. Comparison of the estimate based on the simulation study and real life data. The likelihood function based on the cause-specific hazard function is given by question 7, and the log likelihood function under our Butterwell distribution is given by equation 8. The estimate of the likelihood function are obtained using the numerical method since the expression of the normal equation are not in closed form, and therefore the estimate of cumulative cause-specific hazard function are obtained using the invariance property of MLE through equation 9. The Bayes estimate. For obtaining the Bayes estimate, we have to define first a prior of the known parameter. In this study, we consider a class of non-informative prior for the baseline parameter, which consists uniform, Jeffreys, and Harvey, and we assume normal non-informative prior for regression parameter as follows. Posterior distribution. We use the Bayes theorem for obtaining the posterior distribution based on the joint prior and the likelihood function using question 10, and we observe that the joint posterior density are not in any explicit form, so we use the MCMC method for generating the posterior sample. Loss function. For obtaining the loss Bayes estimate, we consider two types of loss function. First is the symmetric loss function known as the squared error loss function, which is defined by L1, and the Bayes estimate under the squared error loss function are obtained by the equation 11. And the second is asymmetric loss function known as Linux loss function, which is defined by L2, and the Bayes estimates under the Linux loss function are given by equation 12, where phi is the hyperparameter of the Linux loss function, which defines the degree of asymmetry of Linux loss function. We performed a Monte Carlo simulation study to observe the finite sample behavior of the proposed estimator for our model. For simplicity, we consider two causes of failure and one single covariate X, which is generated from the standard normal distribution, and we assume the two parameter values as follows for cause 1 and cause 2 respectively. The censoring time D is generated from the uniform distribution, where D is imposing the percentage around 20%. We consider for sample size 20, 50, 100, and 200, and the whole procedure is repeated 500 times. The comparison of the estimate are made based on the mean square error MSC of cumulative cause-specific function and the average estimate. And the cumulative cause-specific function is obtained at 3 time point 0.5, 1, and 1.5. All the results are obtained in the simulation study are satisfactory, which is given by table 1. Table 1, we observed that all the MSC of under proposed estimator are decreasing as sample size increasing, which verifies the consistency property of the MLE, and the Bayes estimates under uniform prior work well as compared to other estimates. Real life application. We analyzed the data of bone marrow transplant, which from January 1996 to February 2000. Survival of the patient in this dataset are measured in years. This dataset have 3 causes of failure, so we combine in two causes. First is the CGVHD known as cause 1, and second is the combination of the time to relapse and time to death known as cause 2. It is seen that out of 100%, 86% experience with the CGVHD event and 10% experienced relapse and death, and 4% were right center. The effect of two covariates such as treatment and age is observed. First, we characterize the shape of the cause-specific hazard function for CGVHD by non-parametrically and compare with the Butterwell distribution, and it is observed that the hazard function for CGVHD event is initially increasing and starts showing decline. We therefore compared the goodness of fit of the model with viable gamma modified viable distribution and log normal distribution based on AIC and BIC. The AIC and BIC for CGVHD or Butterwell distribution are least among the other distributions. The estimates of the cumulative cause-specific hazard function are obtained for CGVHD and other causes. The parameter estimate and the AIC BIC of the CGVHD event are given in table 2, and the parameter estimate for both the causes are given in table 3. And it is observed that the AIC for Butterwell distribution is less among the other counter distribution and BIC also. This is the figure for the cumulative cause specific phase person for CGVSG event, and this is the figure for baseline cumulative cause specific phase person for other event. And it is observed that from both the figure, the cumulative cause specific phase person for CGVSG event is more. Conclusion of the study. In this study, we consider the problem of comparing estimation via cumulative cause specific hazard function using Bird-Well distribution as a baseline model. The flexibility of the distribution has been demonstrated through the behavior of the probability density function and hazard function. We utilize both the classical and Bayes estimators. The Bayes estimates are obtained based on different non-informative priors and two loss functions. The behavior of the Bayes estimates is better under uniform prior compared to other two priors in class of non-informative priors. The treatment BM, PAB, and age have no any significant effect on CGVSG, but the effect of age is significant on the other causes under Bayes estimate, and the treatments are significant under likelihood estimate. References we have considered. Thank you.
Yeah. Thank you for two things. One, explaining things clearly, and keeping it well within the time. Now, I think the audience, it's open to you. You can get clarification of any questions that you supposed to raise. Any questions from the audience? Sir, can you see, because it's not visible here? Professor, can you see any raise of hands?
Hello?
Professor, can you see anybody raising hands for questions?
No.
Okay. Then, okay. So I will put my own questions. Sir, you have you proposed any estimator on your own? Or whether you tried with already existing estimator for the data?
Yes, sir. We only try for existing maximum likelihood and Bayes estimator. And in Bayes estimator, we consider a class of non-informative prior for baseline parameter, which is first time we introduced. We compare the significance of the prior.
Okay, that means see, because I heard something every now and then there was proposed estimator a statement in between, so I was thinking of that whether you have introduced a new estimator, so that I think we can go into detail. Okay, that is one thing. And how about see, you said you have dealt with the Bayesian approach.
Yes, sir.
How you selected your parameters? You said the uniform is performing better compared to the other two. That is, it's coming out from your probably in your less mean square error or something of that sort.
Actually, we compared mean square error for simulation study for sample size. So, and we interpret that thing, sir.
So I no something like a hyperparameter are you using, or you are putting it directly?
Actually, for hyperparameter for uniform prior, we choose randomly hyperparameter, and for Jeffrey and Hafti prior, there is no need to choose hyperparameter. They are non-informative prior in the thing.
Okay, sir. It is well conceived, and the direction is very well. So I think your profession is also here. Will be very much satisfied by your defending and way of presentation. So all the best for candidate and the guide as well.
Thank you, sir.
I think we can move to the next candidate.
Thank you, sir.
Thank you.
So the next one, Kalaivani. I think whether Madam is here ready for presentation. Kalaivani, estimation of reliability functions of K out of N system with variable distribution. Whether the candidate Kalaivani is present? No, it seems. Or is there a time lag? Okay, we'll move to the next one. Shubham Shaini, right? Estimation of whether the candidate is present?
Yes, sir, I'm ready to present.
Yeah, okay. Then I will read the title. Estimation of stress strength reliability for generalized Maxwell failure distribution under progressive first failure censoring. Sir, you can proceed. First you can share and then you can proceed.
Is it visible, sir?
Yeah, it's visible. You can start.
Okay, sir. Good afternoon, everyone. My name is Shubham Saini. I am a research scholar in Department of Statistics, University of Delhi. So the title of my presentation is Estimation of Stress Strength Reliability for Generalized Maxwell Failure Distribution under Progressive First Failure Censoring. Here is the contents of my PPT. So let me start with introduction. As we know, censoring has a major role in live tests. Type 1 and type 2 censoring is...
Can you make it large? Can you make it large? Yeah.
Yeah, that's better.
Type 1 and type 2 censoring scheme gained more attention among various censoring schemes. To save time and money, one can use type 2 censoring, but when the lifetimes of products are very high, the test can consume too much time. Johnson in 1964 described a study in which the experimenter can group the test units into a 5 sets, each as a bunch of test units, and then perform the test for each unit simultaneously until the first failure occurs in each group. Then Balasuria in 1995 showed that when the lifetime of a product is very high and test facilities are scarce but the test material is relatively cheap, one can test mn units by testing m sets, each containing n units. Each of these sets of units is then tested separately until the first failure occurs in each sets. There is another censoring scheme known as progressive censoring in which the experimenter can remove active units during the experiment. Wu and Kush in 2009 introduced the progressive first failure censoring schemes as the combination of first failure and progressive censoring schemes and obtain the estimates of the parameters of variable distribution. Due to its applicability in the live testing experiment, the progressive first failure censoring scheme has become popular censoring scheme in the last decade in literatures.
Can you enlarge it a little further? Is it possible? Please check.
Yeah.
That's better. Yeah.
The joint PDF for failure times under progressive first failure censoring scheme is given by the equation number 1. One can note that the following censoring scheme are special cases of progressive first failure censoring scheme, which are the first failure censoring scheme, the progressive type 2 censoring scheme, the type 2 censoring scheme, the progressive type 2 censoring scheme, the type 2 censoring scheme, and the complete sample case. Now the generalized Maxwell failure distribution. Maxwell distribution has many applications in physics and chemistry. It explains many fundamental properties of gases, pressures, and diffusion. Recently, the Maxwell distribution has become a well-established lifetime model in literature. This distribution has been extensively studied in lifetime models. For example, Tyagi and Bhattacharya considered the Maxwell distribution as a lifetime model for the first time and discussed the Bayes and minimum variance unbiased procedure for the parameter and the reliability function. Chaturvedi and Rani in 1998 generalized the Maxwell distribution by introducing one more parameter and called it generalized Maxwell failure distribution. Also, they obtained classical and Bayesian estimators of the parameters of generalized Maxwell failure distribution. To the best of our knowledge, the stress reliability for the generalized Maxwell failure distribution is unexplored under progressive first failure censoring data till date. So now the stress reliability function. The stress reliability delta is frequently used as a measure of performance when a system of strength X is subjected to the stress Y. The system works till the stress applied on it remains less than its strength. Due to wide application of this model to science and engineering, several authors have considered estimation of delta in literatures. A random variable X is set to follow. Let X be a random variable denote the strength of a system and follows generalized Maxwell failure distribution with parameter θ1 and gamma1 and the stress imposed on it denoted by random variable Y, which also follows generalized Maxwell failure distribution with parameter θ2 and gamma2. The measure of system reliability under the stress strength setup is given by the equation number 4. We also obtain the maximum likelihood estimation. Suppose x1, x2, and xm1 under progressive censoring scheme R1, R2, Rm1 is progressive first failure censored sample of size m1 from the generalized Maxwell failure distribution, and similarly y1, y2, ym2 under the progressive censoring scheme S1, S2, Sm2 is progressively first failure censored sample of size m2 from the same distribution. Then the likelihood function for the object sample is given by this equation number 5. In order to obtain MLEs of all the parameters, we derive corresponding log likelihood equations by partially differentiating about likelihood function, log likelihood function, with respect to all the parameters. And since the likelihood equation cannot be solved analytically because they are non-linear in nature, so we used fixed point iteration method to obtain the MLEs of the parameters. Now, using the invariance property of MLEs, we substitute the MLEs of all the parameters in the instance reliability function and obtain the MLE of instance reliability function given as equation number 10. We have also obtained the MLE of density function and the MLE of reliability function given in equation 11 and 12 respectively using the invariance property of MLEs. We also obtain the asymptotic confidence interval. We observed that the MLE of delta cannot be obtained in a closed form expression, so we cannot derive its exact distribution. Here we calculate asymptotic confidence intervals for delta by using the fact that the distribution of MLE is asymptotically normal. And the 101 alpha % asymptotic confidence interval for delta comes out as given by this formula. Now, to obtain variance of delta using a result of Rao, the variance of delta can be obtained using this formula. Here, variance and covariance of theta 1, theta 2, gamma 1, gamma 2 can be obtained from observed Fisher information matrix. The element of Fisher information matrix is nothing but the negative of the second partial derivative of log likelihood function with respect to all the parameters. We have also obtained the Bootfee confidence interval. When the sample observation may not be sufficiently large, assumption of asymptotic normality may not be valid. In such cases, asymptotic confidence intervals of parameters discussed in previous subsection may not be a good choice. So we consider here bootstrap confidence interval for delta based on bootstrapping method discussed by Efron in 1993. Here is the steps which used in Bootfee method. Similarly, we found Bootfee confidence interval using these steps. Now, Bayesian estimation. Under the Bayesian paradigm, we consider the parameters that are to be estimated as random variables, assuming the parameters theta 1, theta 2, gamma 1, gamma 2 having independent inverse gamma priors with respect to PDS given as follows. The joint polarity density is given by equation 13. Now, the joint posterior distribution of the unknown parameters is given by this equation number 14. Since the joint posterior distribution of the parameters in equation 14 cannot be obtained analytically, the Markov-Chain-Monte Carlo techniques is used to obtain the Bayes estimation, and the Metropolis-Hastings algorithm is used to generate random sample from any complex distribution of any dimension that is known up to a normalizing constant. Here is the full posterior conditional distribution of parameters theta 1, theta 2, gamma 1, and gamma 2. The full posterior conditional distribution of these parameters are not in well-known distribution. So here to generate the random sample from this equation, the Metropolis-Hastings algorithm is used. Here is the steps which is used in Metropolis-Hastings algorithm. And since the full posterior conditional distribution of each parameter depends on some of the other parameters, the Gibbs sampler is also used here. The MCMC techniques of MH algorithm using Gibbs sampler is given as follows using these steps. Now we also obtain Bayesian credible and SPD credible intervals using the procedure given by Chen and Shao in 1999. So here's the procedure given by these steps. I'm not going to discuss it. So now,
Sir, sorry to interrupt. Sir, you have 1 more minute.
Okay.
Accordingly, you plan.
Now in simulation study and real data analysis, we perform the Monte Carlo simulation study to compare the performance of MLE and Bayes estimator under different progressive first failure sampling scheme. Also, we have analyzed a pair of data set for illustrating purpose. We calculate the biases and mean square errors to compare the performance of both estimators. We also find Bayesian credible interval and SPD credible intervals in terms of the average confidence length and coverage probability. Different progressive first failure and sanctioning scheme with the different sample size are reported in this table. Here we provided some plots of conditional posterior distribution. From these plots, we can see that the conditional posterior distribution are similar to Gaussian distribution. So we take purported density as a normal distribution to generate a random sample from posterior density of parameter. To examine the performance of estimators of reliability functions graphically, we plotted the values of different estimator of reliability functions. From this figure, we can see that Bayes estimator based on informative priors of reliability function are very close to the actual values. Also, the small group size provides better result. Also, we have plotted the trace plot and posterior densities of theta1 and theta2, in which we can see the difference between the results based on prior 1 and prior 2. We have also plotted the consumption plot for all the parameters, and here we can see that the after about iteration 5,000 iteration, the chain eventually converged. So we have taken 5,000 as a burn-in period in Markov chain Monte Carlo method. Now let me conclude. In this paper, the classical and Bayesian estimation procedure of the stress reliability for generalized Maxwell failure distribution using progressive first failure sanction data are obtained. The maximum likelihood and Bayesian estimation method are obtained in this paper. The asymptotic boot T confidence, Bayesian credible and SPD credible intervals of the stress reliability were developed. The simulation results showed that the Bayes estimator were better than the ML estimates in terms of biases and MSCs. Also, it was observed that the SPD credible intervals outperformed than all other intervals. The ML estimates were quick and easy to obtain, but for informative priors, the Bayes estimators were more efficient. Thus, if there is no prior information available, the quick results are required. The ML estimation method is recommended. If prior information is available, the Bayesian estimation method can be used. The result and methodology discussed in this paper will be beneficial to the data analyst and reliability practitioner in real-life situation. Here, the computation approximation methods were used. In future, exact estimation procedures can be developed. So thank you all. Here is the references of my paper.
Thank you, sir. And any questions from the audience?
So any specific reason for choosing Maxwell distribution?
So it is a generalized Maxwell failure distribution. Maxwell distribution is a particular case of this generalized Maxwell failure distribution. And
No, I'm asking, you have chosen this distribution as a lifetime distribution. Any specific reason which attracts you to choose this distribution for this study?
Because not much work has been done on this based on this distribution.
Have you tried for gamma prior? As you used inverse gamma prior?
Yes,
right?
sir. Gamma priors.
Have you tried for gamma prior?
No, sir, I didn't try.
Then why you choosing this inverse gamma?
Because, sir,
any specific reason?
It is quite flexible and it model a variety of informative priors.
But gamma is also flexible.
Yes, sir, but it provides provided better results, so that's why we use it only.
I think one
sir,
of the
yeah,
please.
Sir.
Yes, please carry on.
I have
one Mr. Srinivasa.
Yeah,
please.
I have one suggestion. Why the candidate has not taken the real data example to exemplify the results and both traditional and Bayesian.
Right.
Because of lack of time, that's why.
Okay.
So you may think of real data also using.
Yeah.
I think then it will automatically answer Professor Navin Chandra's question also. Going for a particular lifetime distribution. Okay. So your data, okay, if it is going to suit well with the something like distribution, real-time distribution, okay, then I think you can justify it. So now you, yeah, that is one way you can justify it. And I think, okay, that is one part of the story. And whether any other question from the audience? Okay, if none is there, sir, you have taken some MCMC approach for deriving your posterior distributions. So,
Yes.
what software you used?
Pardon, sir?
No, for deriving posterior distribution through simulation. So
Yes,
you
sir.
said you have used the MCMC techniques, like a metropolitan Hastings algorithm and other things.
Yes, sir.
So what specific software you used?
Because, sir, the posterior distribution cannot be obtained analytically, so that's why we have used these techniques, Markov and Monte Carlo.
Sir is asking which software you have used.
R programming.
R you are used. Okay, okay. So that is one thing. And see, you started with saying that there are different types of so censoring, and you said the progressive censoring also.
Yes, sir.
Have you used progressive censoring in your model?
No, sir. I'm using progressive first failure censoring, which is a generalization of the censoring scheme.
Okay. And
Progressive
how will
is a particular case of this progressive first failure censoring.
Okay, okay. So now your topic says that it is related with the stress strength. Okay.
Yes, sir.
Here, actually, how you justify that particular terminology? Where you use this that stress strength concept in your modeling?
Sir, stress reliability can be used in in a system to test the performance.
No, in fact, all reliability we derive it, okay, based on the general concept. But when you specifically mention about stress,
so let me give you an example. John Stone in 1983 presented an application of stress reliability to military application, in which an anti-tank sabot round fired against a Soviet T-62 tanks. He used a Bayesian approach to estimate the probability that a given round will penetrate its target.
Sir, accepted. But my question is how that stress strength model, how you are incorporating that concept in your model. So the one that you developed and simulated, and you got some tables with the different sample sizes and different priors. Okay. So here, how you bring in that stress model? That is what I am asking. How you are getting into that stress strength concept here? Could you follow my question?
Actually, I didn't get it.
Okay, see, the thing is, your topic says that you are dealing with stress strength reliability, right? So normal reliability under Bayesian setup with the generalized Maxwell failure, that and all okay, right? So you have justified saying certain aspects, right? But the component stress strength, okay, how that is implemented in your problem? Whether it gets reflected in your maximum likelihood structure, or whether you are going to give any stress level that you are going to use for this particular component, or whether you don't at all use any stress level. Only if you stress, okay, if you fix your stress level, then the things will get accelerated and you can get quick results. That is the idea of stress strength, actually, right? So applying accelerated stress, okay, did you make provision for such stress parameters? That's what I am asking.
Sir, we haven't fixed any level of this stress or strength. We have used general form.
Okay, okay, yeah. So at least I think it's only a suggestion. It's up to you yourself and your guide to decide. Finally, you are in the actual field, so it's only a suggestion coming out of from our side. So if that is going to be a stress related model, then you can bring in stress component or stress parameter, and you can also have some liberty to vary your stress component and fix what is the maximum stress that is giving a better results in terms of reliability with the minimum time or minimum cost, something of that sort. It's only a
Yeah,
suggestion.
that's why professor asked some real life data. If you go, then it may be better what temperature, how you have increased, what level you have temperature. That can be seen with the real life example.
Exactly.
I will take care of it in my next.
Yeah, sure. All suggestions, they are only suggestive in nature, and we know practical difficulties getting real-time data or compatibility with the softwares and convergence time running and getting simulated data. So it's a very big task actually when multi-parameter setup is being run with simulation. It even takes time in hours together, or in cases even days together. So I think it's a very good presentation, and I think I hope or the system hopes that you benefit from the comments from the experts from our side, and you can improve further. All the best. I think next candidate. Anurag Sharma, is he present here? Anurag Sharma.
You unmute your mic, Anurag Sharma.
Yeah, I think.
Yes, sir, I'm here.
Yeah, here. Okay. So his topic is estimating the survival time of HIV/AIDS patients by reducing the number of predictors using canonical correlation technique. So that is his topic. So maybe this can be thought of something variable selection technique or variable reduction technique or dimension reduction. Possibly we will get it clarified once the candidate starts presenting. Sir, you can start now.
Okay, sir. Sir, is my presentation visible?
Yeah, it's visible.
Okay. So, good afternoon, everyone. I'm Anurag Sharma. I'm a research scholar under the guidance of Professor Gurpreet Goga in Department of Statistics, University of Delhi, and I'm here to give my presentation on my article entitled Estimating the Survival Time of HIV/AIDS Patient by Reducing the Number of Predictors Using Canonical Correlation Technique. So, in this article, we have tried to reduce the number of technique by using canonical correlation technique. And the motivation of my article comes from my MPhil dissertation, which was on high dimensional AFT models. By high dimensional dataset, we mean a dataset with large number of covariates, for example, gene expressions in cancer, where we do not have 100 or 200 genes, we have tens of thousands of genes, and taking all of the genes in the model is not possible for a statistician. So, in such cases, a pre-screening technique is used to select only significant genes out of those tens of thousands of genes by eliminating the correlated covariate or the genes with the intervals. So, the main goal of our article is to reduce the covariates in this low dimensional data set without affecting this estimated survival time of the patient. This introduction of my article, we have used a real life data set of HIV/AIDS, which we obtained from Dr. Ram Manohar Lohia Hospital, Delhi, and some introduction about HIV/AIDS. HIV is a virus which attacks and destroys the immune fighting cells of our body, and due to these continuous loss of CD4 cells, it becomes very difficult for our body and for the immune system of our body to fight infections. And this advanced stage of HIV is known as AIDS, which is called acquired immunodeficiency syndrome. And this epidemic is considered as one of the most destructive health crises of modern times. Some statistics about the HIV/AIDS. In 2013, worldwide 36 million persons were infected from HIV/AIDS, which caused 1.2 million deaths globally, And in India only, we talk about only India, 2.5 million people were estimated to be suffering from HIV till 2014, and there are many sources of transmission of HIV, which includes transmission of blood, semen, genital fluids, or breast milk of an infected person. Now, a brief introduction about the technique which we have used. We have used canonical correlation technique, which can also be defined as a technique of finding two data set of basic vectors. So this technique divides the data set into two variables of similar, two sets of similar variables, and then it tries to determine the correlation between these two sets, and on the basis of correlation, it tells us which variable or which data set of variables can be chosen in our model instead of all the variables present with us. So this technique, this analysis, it measures the stress of relationship between two canonical variates. These variates are nothing but these two sets of variables which have been formed with the homogeneous variables. And the advantage for researchers over the existing variable selection techniques are, first of all, it limits the probability of committing type 1 error, because it easily assesses the relationship between two sets of variables in a single relationship rather than separate relationship for each dependent variable. For example, we have 10 variables, and instead of finding relationship between 10 C2 variables, what does it do? It tries to determine the correlation within the whole variable data set. And thus canonical correlation analysis is technically able to analyze the data involving multiple sets of variables, and it is consistent with that purpose. So we had the data set from Ram Manohar Lohia Hospital from 2010 to 2014, and the data set consisted of 767 patients which were diagnosed with HIV/AIDS during that period, and the follow-up time was obtained, which was defined from the date of diagnosis of last contact, date of diagnosis to the time of last contact, and by getting the files, we had 11 prognostic factors, and we used accelerated failure time model, which uses survival time rather than hazard time to estimate the survival data. And first of all, we fitted AFT model with all of the 11 available predictors. However, it may be possible that these 11 predictors might be related with each other, and therefore, instead of taking all of those 11 predictors in our data set, what we can do, we can choose a number of variables out of those 11, which can help us in getting the better estimates of survival time with less standard error and less AIC value. Then, so in our data set, we had 11 predictors which were divided into two sets, one with the patient's lifestyle factors such as their age, their gender, what was their drug, their alcohol, whether they were alcoholic, whether they were smokers, and whether they were infected by opportunistic infection. And the other factor was grouped with socio-demographic factors such as state, what was their living status, what was their occupation, what was their marital status, and what was the condition of their spouse's health. And after that, we used canonical correlation technique to determine the association between these two groups. And if there was any association between these two groups, which variables should be included in model, which set of variables should be included in our model, and which variables should be left out, was found out by the means of loadings and cross loadings. And then again, on the basis of chosen set, AFT model was fitted to see whether this model has any improvement over the previously fitted model or not. So these were the results. These results shows the canonical correlation where we can see the percentage of variance. So the predictor in the first set, which was the lifestyle factor, has a correlation of 0.568 with variance of 41.41%, whereas prognostic factors in the second set has a correlation of 0.580 with relatively lesser variance of 39.34, which shows that the factors in second set has better correlation and lesser variance. And then we determine the loadings and cross loadings using Wilks lambda. Wilks lambda first of all chooses the hypothesis that there is no significant difference, no significant correlation between these two sets of predictors. But in our Wilks lambda, the p-value was less than 0.05, which shows that there was significant correlation between these two sets of predictors, which is set A and set B. Then we determine the loadings and cross loadings. And looking at the loadings and cross loadings, the general rule says that the loadings with mode greater than 30 should be chosen. Therefore, the second set of variables were chosen in the model, and the model was then fitted with these second set of variables, which were state, what was their living status, marital status, what was the condition of their spouse's health, and then the standard error of the coefficient of this previously fitted model, that is the model with 11 predictors, and the model fitted with only second set of variables were compared, and it was observed that the second set of variables had lesser standard errors as compared to the standard errors of the predictors fitted in earlier model. And then their AIC values were also compared. It was seen that the modified model, that is the model with second set of predictors, had lower AIC values as compared to the previously fitted model, which shows that this model fits better than the true model. And therefore we can see that the canonical correlation shows the way to choose the number of variables rather than taking all the predictors in the model, and in this way we can get a better fitted model, which might be helpful in estimating the survival time of the patient and for researchers in the medical field also.
So you're left with one more minute, please. Control.
These are the references, and thank you. I'm done, sir.
Okay, thank you. So thank you, sir, for your presentation. Any question from the audience? If there is any question? Okay.
Hello. Can you
Yes.
suggest
Please.
any reference regarding pre-screening technique which you have used to select the significance covariate or selection of significant covariate?
Sir, I haven't used any pre-screening technique. I was giving you the example of high dimensional data set which uses pre-screening technique.
Acha. So
we have used those techniques. We have tried to use those high dimensional techniques in low dimensional data set.
Okay.
So any other question? Okay, sir, I have one question. See, normally canonical correlation is used when we deal with the two sets of variables. Okay,
right.
And you are dividing your independent variables into two groups, one consisting of socio-demographic variables and another set consisting of the possibly clinical variables. Is it not?
Right, sir. Right.
And you are trying to catch hold of a linear combination in the two groups. And how can this guarantee that these combinations or variables suggested by the loadings of these combinations are related to the dependent variable, in this case, the survival time? Basically, we are trying to, the selection of variables should be in tune with your dependent variable, mainly the time of death or the event. But you are within the independent variable itself, you will be grouping. into two
Right,
groups.
right.
Okay, the first question is, the selection here may not have any impact on your dependent variable, which is totally out of picture when you totally consider your independent variable alone. Leave it whether you are splitting it into two groups or three groups. Even
Right.
if that is taken into logic, another question will come: what is the criteria to divide the group? How come you divide something with respect to socio-demographic? So if somebody comes out with some other categorization, okay, we have to
Yeah,
give
yeah.
a cutoff point. Okay, so and one more thing is,
Yeah, we are still working on it, sir, and we are trying to find different groups and which might be optimum one. And yeah, it's a first step in a long process, and we'll still be working on it.
yeah, that's why I am saying, see, first you verify whether the methodology itself is okay, and then you can try with different categorization or groupings. I am questioning the very logic of dividing the groups, independent variables alone, without any consideration to the dependent variable. That is, so far you have totally kept it away.
Okay,
So, and
okay,
you
sir.
are trying to say that the captured things are going to be used for studying the dependent variable, and you never get that dependent variable into picture at all. So, you should.
It has not seen. It has not seen any dependent variable or something.
Yeah, it
In
may
his
be
presentation.
misleading. Yeah.
Yeah, is in his presentation.
So you
Okay,
should be
sir,
very
I'll see.
careful with this technique. Okay, finally, what matters is you should try to get hold of certain important, statistically or clinically important variables that are going to influence your dependent variable, not that you develop some groups and apply canonical correlation. So
Okay,
you should be
okay.
very, very careful. Only if you cross that stage, then only the second question that arises: what
Yeah.
kind of groupings that you could, first of all, whether groupings and application of canonical correlation, whether that catch hold of good predictors or explanatory variables. That is that itself is under question. So you have to be a little bit careful in applying or extending this technique. Okay, take care. Right.
Okay, sir. Okay, thank you.
So the next candidate, I think we can move to is
Radhika.
yeah,
Something.
Radhika Megan.
Yes, sir. Am I audible?
Yes.
Yeah.
Yes.
Okay. Her topic is estimation and comparison of poverty line in different states of India by using quality adjusted life year.
Thank you.
Madam, you can share and proceed.
Okay, sir. Sir, my screen is visible?
Yeah, visible. You are audible. You can proceed. You can maximize it to some extent.
Sir, is it okay?
Yeah.
This
That's
is
fine.
fine. This is
Okay,
fine.
so good afternoon, everyone. The topic of my presentation is estimation and comparison of poverty line in different states of India by using quality adjusted life year. So firstly, we'll start with the objective, or the aim of our paper was to observe the poverty ratio across different states in different time periods from 2004 to 5, 9 to 10, and 11 to 12. We have done reviewing the methods used to set these poverty lines with the help of consumption expenditure pattern. Then finally, we estimated the quality values, that is quality adjusted life year values for different states, and categorize the states depending on the poverty ratios, which in turn help us to uplift those sections of the population which are lying below poverty line by indexing them on a scale of 0 to 1. So now we'll discuss how far the poverty parameter has reached our country, India. Poverty line gives a snapshot about the nature of poverty in different regions across India. It not only distinguishes between the rich and poor, but also reflects the same level of utility over different commodities. So poverty lines are also considered as deflators for cost of living differences. These deflators categorize the individuals in such a way that their households with a defined standard of living is considered to be non-poor if they lie above the reference line, while below it they are deemed to be poor. After defining the poverty, we set a link between the poverty and an health outcome. So poverty, as we know, is an ill health state of an individual or a group of households. So one of the major reasons for the occurrence of poverty is income inequality, which directly affects the health of an individual and its quality of life. So wealth, then it directly relates to how much better is our quality of life. An individual can prioritize his quality of life with or without a disease burden. So this quality of life is measured by means of a health outcome called QALY. Now, QALY is the definition of health outcome. It is exactly a summary measure which incorporates the impact on quantity as well as quality of life. Next, we define the poverty line and the QALY together, where poverty line gives a true picture about the prevalence of poverty across different subgroups of a population lying in different geographic areas, while QALY gives the quantity and the quality of life lived by a population who lie below the poverty line in this context. Then we summarize the different states by using this health outcome. We are in a way giving an opportunity to those subgroups or populations which are lying closer, having the QALY values closer to 1, which implies that they need slight improvement in their health conditions. Thus, a small uplift can make those subgroups rise above the poverty line with good QALY values. On the other hand, individuals whose value lie closer to 0, it indicates that their health condition is bad and needs more improvement. Now we'll define the term utility. Ravelin and Lokshan defines the poverty lines with respect to n mutually exclusive group of states. We have taken all the states of India such that all individuals within a given state share the same utility function defined over various commodities with constant price over a particular year. Each household has its own consumption pattern, which maximizes the utility so that it uniquely belongs to a particular state. Now, when we talk about the consumption term, which is used as an indicator for the measurement of poverty where income is difficult to measure. So it also indicates the differences which occur in the consumption bundles, which directly affects the level of utility in different regions. This utility consistent poverty line is defined as a minimum cost of common utility at the prices faced by each state. For this, we have used the Martin model, which is defined as the expenditure as a function of the price, PI, and where U represents the minimum cost of utility in the jth state along with the vector price, and where XI refers to the commodities for the food and the non-food items which we consider. There, UZ denotes the minimum utility level required to escape the poverty, by which consistency requires to be constant for all J. So far, there's a huge literature related to the measurement of poverty along with the study of the trend pattern. But for the first time, it has been done by means of QALY for different states across different time periods. Next, we move on to the methodology section, where data has been collected from the NSI 61st round for 2004 to 5, also from the 68th round and the 68th round. This is a secondary data which complies from the Planning Commission website. It enlists all the poverty estimates, headcount ratio in percentage, number of people below poverty lines in lakhs, share in consumption expenditure of food and non-food items in percentage, and constant prices for health and education. Next, since in this we have taken the relationship between the poverty estimates as a dependent variable and other explanatory variables like the headcount ratio below poverty line, the utility for food and non-food items. So on taking data as a whole, it did not give good results, which lead to huge variation in the values across different states. So we resort to stratification. Here we have done stratified random sampling, which gives us better representation of the entire population under study. Since poverty ratios and value of variances differ across the strata, so we consider disproportionate stratification. Poverty lines represent the same level of utility through time and space. This concept helps us to make an assumption about the utility being constant in a particular year. So this utility function is defined as UZ, stated here, and from the table above we have used these weights in order to compute the further utility functions for different years. The utilities are assumed to be constant throughout for all the states. Due to unavailability of data, we could not fit a varying utility function over different states. Then we have applied the Bruish-Pagan test for the heteroscedasticity for the error variances in the regression model. And after this, checking for heteroscedasticity, we fit the polynomial equations for different stratas defined as from A1, A2, A3 for the first strata groups. And similarly, we did it for B1, B2, and B3. So on fitting the polynomial for 6 strata for 3 different years, we get the estimated poverty ratio denoted by PR hat. And then using the utility function derived in the earlier slide, we have tried to compute the QALY. So this QALY has been defined as the formula of length of life, which is assumed to be 1 year, into the quality of life of the people living below the poverty line, which is computed using the utility function. So now you can see this table for the strata A. The sample size varies from 17 to 21. There are eight states such as Andhra Pradesh, Bihar, Chhattisgarh, as you can see in the first column, Haryana, Karnataka, Kerala, Maharashtra, Punjab, whose position remains constant in strata A over different period of time with improved quality values as the year progresses. So over and for the time period 2009 to 10, as you can see in the fifth column, more than half of the number of states have quality values greater than 0.5. Thus, it shows better quality values in comparison to previous year 2004 to 5. Thus, a moderate improvement is needed for those states with quality values less than 0.5. And now you can see in the second last column for the quality values for strata 2011 to 12, there are four states such as Haryana, Kerala, Punjab, Sikkim, whose values they have better quality values and they're better health states. That is closer to 1. So a small uplift by the government through different initiatives can help these group of states to rise at a better pace at rise above the poverty line. Similarly, we have tried to conclude from the strata B. In this, the sample size varies from 13 to 17 from 2004 to 2012. There are a number of 6 states such as Andhra Pradesh, Jammu Kashmir, Meghalaya, Mizoram, Nagaland, Puducherry, whose position remains constant in strata B with improved quality values over a period of 3 different years. Thus, for the time period 2004 to 2005, the quality values remains less than 0.5 for all the states except for Jammu Kashmir and Pondicherry. But for the strata B in 2010 to 11, there are 3 states such as Gujarat, Nagaland, Pondicherry, whose quality value is closer to 1. This implies that these states have a better health state, and they are ready to rise above the poverty line if given a certain amount of upliftment. Almost all other states, like in 2011 2012, the time periods in this time period they have quality values closer to 1, except Meghalaya, which implies a slight improvement in terms of quality values can make a larger section of the population rise above the poverty line. Thus, we can conclude that the concept behind the quality serve as a great importance for policymakers to identify the quality of life of different states lived by the group of individuals who are deemed to lie below the poverty line. Although this paper demarcates the different states on the basis of number of people below the poverty line as well as the quality of life lived by those sections of the population, thus by means of providing adequate facilities, we can help them rise above the poverty line based on this quality measurement. There is a huge variation in quality values across different states of India. It indicates that few states are on the verge of better quality of life with quality value closer to 1, then other states are in worse condition with quality value closer to 0. Thus, it will help the policymakers to initiate new frameworks for people lying below the poverty line. Although eradication of poverty is an important objective, human being needs a certain minimum consumption of food and non-food items to survive. Thus, measurement of poverty helps us to evaluate the help us so that the individuals can meet their survival needs. These are my references. Thank you. Yes, sir.
Sir, unmute your mic. Sir, unmute your mic. Viswanathan, sir.
Okay, so it's a nice presentation. Now I expect questions from the audience.
I have one
Sir,
question. Hello.
Yeah, please carry on. Please carry on.
Myself, Dr. Manish Kumar. I have one question. What does PRU represent in the table? PRU.
Sir, PRU refers to the poverty ratio value. That is the estimated symbol which we have used.
Poverty ratio values.
Yes, sir.
You are
For different states.
For unit. Actually,
for different states.
And one more question in the table. You have shown for 3-year data. The recent one is the quality value is decreasing. It should increase, no? With the year. Government is the government of India is making policy, various policies. So that will increase or decrease quality value for each year for a particular state.
Yeah, right. Basically, the quality value has to lie in the interval of 0 to 1. So as the poverty ratio decreases, the quality value increases. Is it okay?
Yes, yes.
Any other question? Okay, I hope there is none. And madam, whether you have that quali questionnaire now with you? The quali, the one that you have used to measure, finally you reduce it to 0-1 scale as you mentioned. Whether you have any screenshot of questions or how many questions included in that quali?
Sir, we haven't used the questionnaire method, which is the standard method. We have used the indirect utility approach.
Okay,
We
that
have
is
we have calculated the utility weights, and then we have, since utility is calculated as a production function of food and non-food items, so we have maximized it in order to get the utility values. We have differentiated it.
So for a particular state, for a particular time period, okay, you say this is the quali value, right?
Right.
How you arrive at it? How you get it?
Sir, for a particular state, since we have followed the Ravelin and Loxian approach, they say for a particular state the utility value remains constant. So we've calculated the weight by differentiating it with respect to the, say, for a food item. If I calculate, then I keep the other items as constant. So I place the value as the weight, and that is the value which we get on that. And these values are calculated by keeping in accordance the polynomial estimated equation which we are getting for that particular year.
Okay, what about in that fitted polynomial, what that x1, x2 and all represent?
So it represents the different, like we have taken the explanatory variables as below poverty line, and then we have taken this head count ratio, then we have taken the food and the non-food items, and the health and the education ka jo bhi expenditure has been done for that particular year. These are the different variables which it is representing, and the fitted, depending on the R square, we have chosen the best model which fits the poverty ratio.
Yeah, at least you could have included the list. What are all the how many variables you included, and what are all the description of the variables, because that will at least throw some light on the explanatory variables. Okay, that is one thing. And one more thing is, see, finally you have a table of comparison, okay, which compares states in the rows and 3 different time periods in the columns, and finally going by your quali value, you say when there is an increase, the state gets increased. I mean, the quality of life gets increased, something of that sort. So this is purely a descriptive one, right? So have you gone for any statistical testing to see that the difference is statistically significant?
So by using the model of polynomial fitting, whatever poverty estimated we got, we did error regression. How much is the difference? How we can minimize the squares? So here we could pick it out that whatever model we are using, whether it fits the data or not. Since the error were very less, so we could come out with that yes, we can use this model in order to predict the utility function.
That is, madam, for justifying your model selection. But my question is, after selecting that particular model, you have estimated for each state and for the 3 time periods, and you consolidated in the table. Okay. Now I am not questioning the validity of the model, that you have justified already, right? My question is, from column 1 to column 2, column 2 to column 3, if there is an increase, you say the quality has increased. But that is only an observation. Okay, it's a say something like a descriptive statistics. Say from this year the mean has increased to this much, income has increased, or poverty has decreased. But whether that increase or decrease, is it statistically significant? Have you done any statistical significance test?
No, sir. I can further perform the difference of the means test in order to check
that's what
whether
I am suggesting, in the sense that that may require more deep and advanced tools, because it's now become a panel data, right? So once you take the things, both classification with respect to states, okay, geographical, and one over time. So getting entries is okay, as you said. You can apply different say. Probably I might. You have got this data from NSSO. You are saying, right?
Yes, sir. Yes, sir.
It's in a way a reliable source only. But having done that, you can start. You can take the final table as your input. Data, and you can introduce certain parameters, and based on the significance of the parameters, you can claim there is a real quality improvement, or there is a decrease in the quality of life. Okay, and possibly you can have a categorization to, as you mentioned, okay, you can group into 3 clusters or 4 clusters, saying these are all okay, developing at a faster rate or not that much faster, something of that sort.
Okay, sir.
But you better search
Validate.
certain tools, okay, for under panel data to claim certain things, because if you see, publish it in any journal, okay, possibly you can see a table with some stars appearing, okay, and the stars will say star, 1 star saying that it is significant at 5%, double star significant. So
P-value,
unless,
right.
because see, you can imagine the structure, you are already using the data fitted into a regression model that comes from quali, and that comes from income variables and outcome variables from your NSSO. So NSSO goes through field operation division, it collects data in a sample manner. So sampling error might play a very, very huge role unless that is taken into account while making certain conclusion towards the end. Okay, it will be highly risk to make certain observations or conclusions. Okay.
Okay, so
So I
thank
think
you,
this
sir,
is
for your
a
suggestion.
better thing. Yeah, you can search over certain literature. There are certain good panel data analysis book available. Baltagi is one such book. Okay, you can note that Baltagi by Panel Data Analysis.
Okay, sir.
That is a very book to begin with. So once you get into that, I think you can catch hold of the path, and you can select proper tool, and you can say make it robust, and makes it a very more scientific, and for presentation in international journals and other things. Okay, madam, all the best.
Thank you, sir.
So the next candidate, I think. T.N. Kavida. Whether Kavida is present here?
T.N. Kavita.
Okay. We'll move to the next candidate. As whether she is present?
No, I think not present. She is absent.
Okay, right. Then we will move to the next candidate. Then Souvik Banerjee, present?
Yes, sir. Am I audible?
Oh, yeah, sure.
Please.
So his topic is identification of risk heterogeneity on multiple time to event data of protein markers. Sir, you can share and proceed.
Okay. Am I visible?
Yes. Please present you.
Yeah,
it's getting.
It is getting.
Is there?
Yeah. Please.
Okay. Hi, hello everyone.
Little bigger. Make it little bigger.
Okay.
Yeah, fine.
Okay. Thank you, sir. Hello everyone. I am Souvik Banerjee. So today I am going to present my work on identification of risk heterogeneity on multiple time to event data of protein markers. I am a student and research scholar in Department of Mathematics and Computing, IIT Dhanbad. So this is a joint work with Dr. Atul Bhattacharya and Dr. Gajendra Vishwanath. So what are protein markers? Protein markers are some important biological characteristics which are used to identify the risk of different diseases. So they are different biological, measurable biological characteristics. They play a crucial role in identifying the disease onset as well as improving drug development process. Now, all protein markers are not characterized as a biomarker. There are so many markers. However, only a certain number of markers which have some favorable characteristics which can be exclusively can be used for disease outcome. So that those are used for as biomarkers. The survival probability of a patient depends on the status of the biomarker. For example, the survival prediction of breast cancer patients diagnosed with HER2 positive status that is different from the same of HER2 negative status. So the treatment pattern for HER2 positive people and HER2 negative people are different. Now there is certain characteristics based on which one patient is characterized as whether he has HER2 positive or HER2 negative. There are certain threshold level. So, but when we observe the gene expression values, they are continuous variable. So it is identifying a proper threshold level or cutoff level to convert those biomarker expressions into a categorical statuses. Now, for a disease progression, especially in cancer, there are multiple indications like locoregional relapse, distance metastasis, and death. Now, due to the interrelated nature of the states, like after a local regional relapse, maybe the death due to that relapse or death may not be due to the relapse, or it may happen that the relapse is decreased and again the patient may be treated. So the individual analysis for each event will not reveal the dependency structure among them. So it happens, it becomes a competing risk, or it may become a semi-competing risk data. The competing risk data where the occurrence of one event, it censored the occurrence of others. Now that there are this dependency structure in survival data, this can be modeled using a random component called frailty. The term was first coined by Babu in 1979. It models the heterogeneity between cluster of observations. Now there are several patients when are there, so there may be some cluster of patients which have a pretty similar kind of survival outcome. So the frailty variance of different group, this can be interpreted as a measure of heterogeneity between clusters or between individuals. Now, in the presence of competing events, the use of only one frailty variable per biomarker status now is for all causes of failure is questionable, because the biomarker levels, they are dependent each other, and also under a certain cluster, all the patients infected within that certain cluster, there is some kind of correlation maybe there. This correlation can be modeled using a frailty component. So that's why frailty for different competing events within a particular biomarker status are likely to be correlated, and since they represent the same observed covariates on cluster level. This work has been motivated by data of breast cancer. So it was collected from Sung Yat-sen Cancer Center. And the patient who they have followed for the year 1991 to 2004, and after the data, the follow-up period was less than 3 years. Other than the cause of death were excluded from the study. So a total number of 326 samples were collected, and 4 biomarker expression level HER2, ER, PR, and ERBB2 we collected the data. The patients can either develop a distant metastasis or they may experience death. Now, this I like to clarify that when the distant metastasis, after that the patient may or may not experience the death. So here in our study, we converted in a competing risk model by choosing that whichever event comes earlier, whether the patient experience a distant metastasis or the patient experience a death from any other causes. So with some basic methodology, we first use the Cox proportional hazard model. The proportional hazard model that lambda is the baseline hazard function, the xi are the covariates for ith patient and corresponding coefficients. Now when we turn to the competing events, for when there are suppose j competing events are there, 1 to up to j, and then for each of them we compute the proportional hazard model. And the likelihood function for the proportional hazard model using the cause-specific hazard function is defined in equation 3. Now we incorporate the frailty part. What is the frailty? That is the biomarker level specific or status specific effect on the kth level of biomarker. So suppose there are k levels of biomarkers. So for each of them we incorporate W1, W2 up to Wk. Then the overall likelihood that is displayed in equation number 5, where delta ki, that is the indicator of the event or cause of failure for patient I in level k. Now we said that the frailty component we cannot take the independent frailty component. So there must be some correlation should be attached in it. So how to attach the correlation? That we use a frailty decomposition method. The decomposition method was first proposed by Yasin et al. In 1995. So here the ZK naught, that is the level specific frailty, that is shared frailty among all events or all competing events, and that ZKJ, that component, that is dependent on the specific biomarker level and also as well as on the specific event. So the ZK naught, ZK1, those are independent frailty component. We computed it in this way so that the expectation of the frailty component becomes 1 and the variance becomes in the form displayed in equation 8. Now obviously there is a certain problem in it, because the problem is that here the correlation is always positive. So we assume that if the correlation is positive, then only this kind of equation is valid. If there is some negative correlation, then this will not work. likelihood for taking the decomposed frailty component and all the J computing events is in this way. So we computed in our statistical software and we used expectation maximization algorithm to compute the parameters. So the whole likelihood function is computed and tabulated in R, and we used iteration method and we computed the parameters. So how we are going to obtain the threshold levels. So the gene expression for each biomarker that is divided into 100 equidistant values. Now for each values is taken as a threshold level, and the patient which have the gene expression less than that threshold level and above the threshold level in these two groups, and thus we compute the correlated frailty computing mix model. So here our main interest is to find the risk heterogeneity due to distance metastasis and to obtain the threshold level. So we focused on the frailty variance related to the distance metastasis only. The threshold value which have the maximum frailty variance gives the maximum heterogeneity between the two groups, and that threshold level is selected. However, the threshold levels are obtained in this way. They are independent for independent biomarkers, because when the independent we are taking one biomarker at a time and we are computing this correlated frailty model, and we are obtaining a threshold value with maximum frailty variance. But as these are taken one at a time, they are independent in nature. In reality, they are dependent to some extent, and we assume that they are the occurrence of one threshold level, or when if they are taken into consideration together, then maybe there some changes may happen. So the correlation between those biomarkers should be taken care into the frailty variance. Now here, when we are taking all those into a single frailty variance, we found a problem, and so we observed that whenever we have the maximum frailty level, the maximum frailty denotes the best possible heterogeneity level, and at the same time, if we divide it into two variables and we compute the Cox-PH model, then the cutoff with minimum p-value will give the better partition. So we used a p-value combination method. There are several p-value combination methods that have been proposed by Fisher, Pearson, Mudolkar, and George, Eggington, and Tippett. In the combined p-value technique, so the p somehow there is a transformation made, and taking the p-value of all tests together, we compute a single p-value. Now the problem with this approach is we have to take all the p-values together. So if there are, suppose here we have only 4 biomarkers, suppose we have to work with suppose 10 biomarkers, then for each of them we taking 100 equal parts or even more parts, the number of it increases, the number of tests we have to consider, it increases very rapidly. So we have to find a somewhat sequential selection using the p-value combiner method. So what we did is we computed a Cox-PH model taking displayed in equation 10. This y1, y2, yk, these are different biomarker levels. So for each of them, we start with a threshold level first, and this threshold level we select from that we obtain from computing this frailty model using that independent each biomarkers. Now we feed the Cox model at each cutoff the threshold level with minimum p-value using the p-value combination method. So the p-value combination method uses the p-values for all y1, y2, and yk. And here in this picture, you can find that we are keeping this threshold levels fixed at C2, CK minus 2, CK minus 1, and we use the different Cox models. So all of these Cox models are for different threshold levels. We compute, we use this Cox model, we compute the p-value combiner method, and based on that, we obtain the optimal threshold level for first one, that is C1 star. And once it is selected, in the next step, the C1 star comes is made as that threshold level, and for the same process is continued for the second biomarker. So at rth level, this CR-1 is already changed into CR-1 star. This rth biomarker is found optimal at CR star, and then R+1 star is already fixed at the obtained from correlated computing mix model. So in this way, we made a sequential threshold selection. So here we obtain optimal threshold value for all biomarker expressions. However, this process is order specific. So in which order we are taking those biomarkers, which order they are entering the process, that becomes dependent. So we perform this procedure for all possible combinations of biomarkers. Here we have 4 biomarkers, so the all possible combinations, that is a total of 24 combinations. For all of this we computed this. So here we present the cumulative incidence functions for the defined events, and the we based on those those cutoff levels we obtained, we computed the shared gamma fidelity variance for each part. Now you can see that this is the order of the genes, that ER, ERBB2, HER2, and PR. So in different order we obtain different threshold levels, and we obtain the shared fidelity effect. So for each of them, suppose when we obtain the optimal threshold level, the patients with less than that optimal threshold level and patients with higher than the optimal threshold level, for each of them we use the shared fidelity effect, and we find that the shared though this whatever be the order, this is not much dependent on the order. So we assume that even if we take different kind of orders, the risk is independent of that order specification, and it is more about the threshold specification. So whatever in order we take it, the threshold is coming at a certain level, or we can find that there are several kind of difference in the risk or in the shared fidelity effect in these models. We also use the shared Gaussian fidelity model, and we obtain that there is a difference in the fidelity variances for each of them. So for each in this way we obtain a threshold level, and we can say that using those threshold levels we can identify the difference in risk, the heterogeneity in risk among the patients. So we elaborated an efficient statistical procedure of dividing the gene expressions into categorical variables and validated the results. We used additive gamma fidelity model under computing setup and used the computing fidelity model. We also think of extending the proposed procedure for all associated events. Here we have taken only the distance metastasis only, but it can be associated with all the events, and then we can take a composite kind of score based on which we can say how the risk heterogeneity is behaving. Also in this study we partition the gene expression on a dichotomous scale, that is we partition the gene expression on 2 parts only. It can be a polychotomous classification where survival like outcomes differs at different levels of expressions. So here are my references. Thank you.
Yeah, thanks for your nice presentation. Any question from the audience?
No, I have no question, but I appreciate the presenter. A nice piece of work in detail. He did very well work. I congratulate him for his good work and presented well. Thank you.
Thank you, sir. Thank you, sir. Thank you so much.
So if there is no other question, let me post 1 or 2. See, the idea of going for biomarkers, right?
Yes.
Being clinical, okay, first, how will you fix the biomarkers? Whether you did it some other based on some other literature or with some medical experts?
Sir, actually it is based on medical experts, and those 4 biomarkers we have selected, they are very closely related to breast cancer. However, we have worked on the classification of biomarkers. We have already published some papers on classification of when we have high dimensional of biomarkers. From there we obtained that these 4 biomarkers are also coming in our work also. They are statistically significant. So as they are very close to the breast cancer, we are taking those 4.
My question is how do you selected these 4 biomarkers?
This 4 biomarkers is based on medical context. So we consulted with medical representatives, and they said that based on their opinion, these 4 are very close to the breast cancer data, basically close to breast cancer. So that's why we are choosing.
Okay. So having chosen a particular model, and here one suggestion is you are assuming independence, okay,
Yes.
while selecting the threshold values. Okay, that
Yes,
is
yes.
going to play a very big role. If independence, naturally, if the degree of affinity of variables, normally as we see in socio-demographic variables or to some extent in psychological variables, okay, they are of lesser order, but when it comes to clinical variables, they are highly dependent. So in that sense, assuming independence among the markers, and when that is that basis is used to fix the threshold value, I think that is probably you can assume some joint distribution, and you can even to some extent reduce the number also.
Yes.
Reduce instead of 4. Yes, sir.
It is challenge. In fact, it is challenging to decide and choose among them. That's also good.
Yes, as Professor Naveen was pointing out, okay, so selection is foremost, and then as I was mentioning, going for a joint distribution or joint thing which accommodates to some level of agreement between the two. Okay, that is also nice. And yeah, initially, okay, when you started presenting, you were saying that it works with competing risk or semi-competing risk. You mentioned a word called semi-computing. Can you? What is meant by semi-computing?
So the semi-computing risk is when one is terminal event like death, and another is suppose distance metastasis. So in here the scenario is when you get a distance metastasis, you are not dead. After that, you may recover, or you may go back to death, or you may die. So here there is a path that you may go from fit to distance metastasis to death. But in competing event, there is no such event that no such path. Either you experience distance metastasis, or you may experience death. So there is no path from going distance metastasis to death in competing risk. Whereas in semi-competing risk, there is that path.
Yeah, exactly. So the thing is that the path, when path is taken into account, the more appropriate term is called multi-state models.
Yes.
Right. Rather than the semi or giving some other terminology, the multi-state is more appropriate to deal with. Anyway, but this is a very good, nice presentation, and I think all the best for your further research.
Thank you, sir. Thank you so much.
So we will go to the next candidate.
Yes, sir, yes.
It is Naga Durgam Baba. Whether the candidate is present here, Naga Durgam Baba. Okay. What about Pavitra? Pavitra?
Yes, sir, I am present, sir. Am I audible, sir?
Yeah, you are audible.
Yeah.
So the topic is a procedure for the selection of single sampling plan by variables based on Weibull distribution. Madam, you can share and proceed.
Okay, sir. Thank you, sir. My screen is visible, sir?
Yeah, visible, but share the
So sorry,
PPT.
sir.
Yeah, getting it.
Sir, okay, sir?
Yeah.
Okay, sir. I'm going to talk about a procedure for the selection of single sampling plan by variables based on Weibull distribution, sir.
Yes, please.
Introduction to acceptance sampling. Acceptance sampling uses statistical sampling to determine whether to acceptance or rejection of a lot. It has been a common quality control technique used in all industries. It is usually done as products leave the factory, or in some cases even within the factory. Sampling inspection is an activity for taking decision on one or more lots of finished goods have been submitted for inspection. Statistical inspection is determined whether to accept or reject a lot of production material by using acceptance sampling, and it has been adopted. Suitable sampling inspection in that situation is called sampling inspection. Introduction. Generally, the acceptance sampling plan, inspection plan is categorized into two types. Acceptance sampling by attributes, another one is acceptance sampling by variables. In attribute sampling plan is the attribute form, and result either conform or doesn't conform. Generally used for two purposes. Production against accepting lots from a continuing process whose average quality deteriorates beyond an acceptable quality level. Protection against isolated lots that may have levels of non-conformance greater than can be considered acceptable. For example, attribute sampling checks whether an item is defective or not. It is a yes or no answer. I am going to take up my part variable sampling. in variable sampling data in this variable form, and the result is stated on a continuous scale. To achieve the same operating characteristic, a variable sampling plan requires fewer samples than an attribute sampling, since more information is available in the measurements. For example, variable sampling is about checking how much, how good, how bad, or etc. Like the sampling is to determine the sampling size n and acceptability constant k in favor of consumers and the producers by using the sampling inspection plans, such as single, double, multiple, and sequential, etc. My objective is, in this paper, single sampling plan by variables are devised assuming that the quality characteristics follows a variable distribution for a range of values for the measures of skewness and kurtosis. A procedure is developed for determining the plan of parameters for specified requirements to ensure the protection to the producer and the consumer. I have taken the variable distribution. Sweden mathematician Balodi Weibull, who described in detail 1951. So it was named after variable distribution. It was first identified by Frechet in 1927. The variable distribution is one of the important and most used life distribution. So I will use the variable distribution. It is very useful in survival analysis, reliability engineering, failure analysis, extreme value theory, weather forecasting, and wind power industry to describe wind speed distribution, as the natural distribution generally matches the variable shape. Formulation of variable distribution. The first one is consider the following probability density function of variable distribution in equation 1, and cumulative distribution function of variable distribution is equation 2. Various measures, mean, variance, skewness, and kurtosis of variable distribution equation 3, 4, and 5, 6. OC function for single sampling plan. Let us take fx of mu comma sigma be the underlying distribution function of x with mean mu and variance sigma square. That is, gives the probability that p value in equation 7, probability of acceptance p of p in equation 8. The acceptable quality level is defined by P1 in equation 9. The limiting quality level P2 is defined by equation 10. Where mu1 and mu2 are the mean of the underlying distribution, which results in acceptable and rejectable quality levels. Alpha and beta is the producer and consumer risk, is given by in equation 11 and 12. Also, we call where beta is the type 2 error and alpha is the type 1 error. Probability of accepting rejectable quality is beta. Probability of rejecting acceptable quality is alpha. Plot the measure of probability of acceptance against P. Results in a curve is called operating characteristic curve. Designing single sampling plan by variables. Known standard deviation. First one is known standard deviation method. The distribution fx, if only necessary to transform the distribution as follows. In equation 13, then P1 can be defined in terms of P1 from the cumulative distribution function of underlying variable distribution. Underlying distribution, that means variable distribution in equation 14. Here, then equation 15 is from transform equation from 13, as well as P2 in equation 16. Here to find the sample size n and acceptability constant k for known sigma method, it is denoted by n and k and also given by 18 and 19. Note that if alpha equal to beta, so that k alpha equal to k beta, then we have very easy form to calculate the acceptability constant k in equation 20. I have considered only one specification. Consider upper specification only. Known standard deviation and unknown standard deviation. Known standard deviation following under the condition. If x bar plus k sigma greater than u, reject the lot. If x bar plus k sigma less than or equal to u, accept the lot. Unknown standard deviation method, x bar plus k is estimated variance is added. X bar plus k is greater than u, reject the lot. X bar plus k is less than or equal to u, accept the lot. For example, in known standard deviation method, suppose it is known standard deviation method that a group of measurements has sigma equal to 10, beta 1 equal to, skewness and kurtosis 2.2125 and beta 2 equal to 4.8410. Suppose that it is decided to protect against an upper specification limit u equal to 500. with the following protection. Let us suppose that the variable distribution with parameter k dash equal to 0.850, lambda dash equal to 0.975, and thus k equal to 1.1765, lambda equal to 1.0256. M, it is denoted by mean equal to 0.9699, and S, standard deviation, S equal to 0.8272 can be fitted to the measurements. Let the distribution function f of x is 0.97 and 0.90 corresponding to p1 and p2, solving for xp1 and xp2. We have the following in equation 20 and 21 from cumulative distribution function of variable distribution. From the above equation 20 and 21, we get n equal to 71, around 71. Then find k. We substitute above formula, we get k equal to 1.8265. Next one is unknown standard deviation method. The possible formula for unknown standard deviation is given by n and k. The equation 21 and 22 and 23. The value of kp1 and kp2 can be obtained from xp1 and xp2 for the same distribution by using the parameters of this distribution. The unknown sigma method to find the standard deviation from the estimated variance. For example, the same example is given, and it will be used. Sorry. Let us suppose that the same situation exists as in example 1, except that the standard deviation is not known but it's estimated from the sample data. Here the normal deviates k alpha k beta equal to 0.10 gives 1.28155. It will be it have taken from normal deviate table. Sorry, sir. It will give k equal to 1.8265, the same as the known standard deviation method, and then n equal to, it's very different, 191, n equal to 191. Conclusion, an implicit assumption in devising plans by variables is that the quality characteristics follows the normal distribution, which may be unrealistic often in practice, and hence an appropriate probability distribution which could be non-normal or symmetric or skewed is required to associate for the quality characteristics in the evolution of sampling plans. The approximation of normal distribution for a linear combination of independent variables, even when the individual variables depart from normality, is effectively used in developing the procedure for determining the parameters of the plan when requirements for producers and consumers protection are specified. In most of the practical situations, the process is non-normal and heavy-tail distributions. This article presents one-sided single sampling plan for variable distribution only, but the study can be extended many other non-normal distributions and lower specification also. Here, the known standard deviation method gives much smaller sample size than unknown standard deviation, and it also gives better protection of both producer and consumer. Acknowledgement. This paper is financially supported by DST. Also, we would like to thank organizers for giving this opportunity. These are my references, sir. Thank you, sir.
Good, madam. It's a very good presentation.
Thank you, sir.
Any questions from the audience?
Can I ask one question, sir?
Yeah, please,
Yes,
Prof.
sir. Yes, sir.
When they are finding a k values,
Yes, sir.
do you use the simultaneous minimization procedure?
No, sir.
1 minus alpha and beta condition. You have given the two equations
Yes,
from
sir.
that.
Yes, sir.
Did you apply the simultaneously minimization?
Yes, sir.
So, did you try for the OC curves?
Yes, sir.
You have not shown in here the what is the shape of the OC curves for those known sigma and unknown sigma. What is the performance of the OC curve?
Sir, here I have no documents, sir. I'm in Net Center, sir. I have only the PDF only, sir.
Okay, no problem. You can consider for the further work or the.
Okay, sir. Okay, sir. Thank you, sir.
Yeah,
Okay,
the
no
very
problem.
purpose
No
of senior professors like Srinivasa Rao and other professors, their contribution comes in a long way to improve. Yes, sir, we will. We will.
Yes.
So it's a very good opportunity for you to learn things and different opinions also. So if you are confined to your own domain, then possibly that may have some limitations. Here you can see different professors from different domains contributing in different directions. All will enrich your knowledge, and you can work accordingly and improve. So individually you have worked out for specific specifications like particular alpha and particular beta, and you have come out with k value and n value. But what professor was suggesting is why can't you do it for different values and plot it in a graph, study the things coherently. Okay, you can have a global comparison of what's happening when something known unknown. Okay, possibly the variance of the system and other things. Okay, I think one more professor is waiting there, Rajagopal. Yeah,
Yes,
sir,
sir.
you can please welcome.
Good evening, everyone. And it's a very nice work that using variable distribution for designing variable sampling plans. They have found a methodology to find the N and K, and in continuation of the questions raised by Srinivasa Rao Gade, most probably she might not be having answer for my question also, because it is a continuation of that. Suppose they might have done, Pavitra, you can answer. Suppose if you have done empirical study on different values of N and K, you might have worked out on the OC curve. Did you study the OC curve? I hope you have answered previously.
Sorry, sir.
No. Okay. If you attempt to study the OC curve, you will have an empirical study also. For different values of N and K, what is the performance of the OC curve? Okay. My question is in continuation of that. What you have told in your conclusion itself that many of the distributions don't follow normal distribution. That's why you have considered non-normality. That's also right.
Yes,
But did you attempt to compare the values of the increase or decrease in sample size or risks using the same sampling plan with the normal distribution? Suppose you have obtained for a particular parameters of alpha, beta, that N and K, some values for N and K. With the same values of N and K, what is the performance of normal distribution? Or for same risk, what is the increase or decrease in sample size of normal distribution?
Sir, I didn't work, sir. So
Okay, as Professor Srinivasa Rao suggested, it can be your next work.
Yes, sir.
You please, please note
nice
down.
work.
Note down.
Yes, sir.
And may I know who is your guide, or I have missed your first slide. Can you show me the first slide, or who is your guide?
Dr. R. Vijay Raghavan, sir.
Okay. I am also collaborator of Dr. Vijay Raghavan. This is the work in continuation of with my PhD work.
Okay, sir.
Long back, 12 years.
Okay, sir.
We have started this work, then Vijay Raghavan has continued for Pavitra's work.
Yes, sir.
My best wishes to you. Thank you.
Thank you, sir. Thank you so much, sir.
So probably she will be your academic granddaughter.
Probably Pavitra would have referred in your references my work, because ours is a pioneer work in this field.
Yeah,
it is great, sir. Sir, it is great carrying out your work.
Thank you, thank you.
Yeah, it's always nice. Some great senior people come out with some good suggestions,
and luckily
because they might be in a.
Sir,
Yeah,
luckily, sir is present in this session. That's great for the candidate.
Yes, sir. Yes, sir.
Okay, so you can utilize the experience of such senior persons, their advice and their suggestions, and you can enrich your knowledge and working area. All the best, madam.
Thank you, sir. Thank you, sir.
I think we can move to the next candidate.
Okay, sir. Thank you.
Thank you, Professor Vishwanathan and Naveen.
Yeah,
Thank you, sir.
thank
Thank
you.
you, sir.
Welcome,
Thank you,
Professor.
Professor.
CR Saranya, whether she is present?
Yes, sir. Yes, sir.
Okay.
Am I
Application
audible?
of application of I find it difficult to pronounce. What is that?
Birnbaum Saunders distribution.
Saunders distribution in the evaluation of special type of double sampling plan for life test. Okay, madam, you can share and proceed.
Yeah. Is my screen visible, sir?
Your screen is visible. Try to maximize it and proceed.
Yeah. Is that okay, sir?
Yeah, fine.
Hi, good evening, everyone. Myself, Sharanya CR. I'm a PhD research scholar under the guidance of Dr. R. Vijayaraghavan, Department of Statistics, Bharatiyar University, Coimbatore. And my topic is application of Birnbaum Saunders distribution in the evaluation of special type double sampling plans for life test. Let me start with the introduction of acceptance sampling plans. Acceptance sampling is a product control methodology to make a decision about the acceptability of a lot of products based on sampled observations. Reliability sampling plans comes under acceptance sampling procedures, and it has the rules and procedures for making decision about the lot acceptance or rejection based on sampled lifetime information. The review of literature. The theory and development of reliability sampling plans based on exponential and variable distributions are presented by Epstein in 1960 and Good and Cow have presented in 1961, 62, and 64. A detailed account of such plans was provided by Schilling and Neighbor in 2009. Gupta and Grohl considered gamma distribution for modeling lifetime data and constructed the acceptance sampling plan for life test when the life test is truncated at a pre-assigned time, and it is published in the year 1961. Balasurya in 1995 developed reliability sampling plans under sudden death testing for the two-parameter exponential distribution. The military handbook H108 in the year 1960 provided the sampling procedures and tables for life and reliability testing based on exponential distribution. Vijayaraghavan et al. In 2012 have provided the selection procedures for determining the sampling inspection plans for life tests based on Weibull-Poisson mixed distribution. And life test sampling plans based on log-normal distribution is constructed by Vijayaraghavan and Uma in 2016. Loganathan and Gunashekaran in 2019 developed a procedure for designing reliability single sampling plans under a hybrid censoring scheme, assuming that the lifetime is distributed according to exponentiated exponential distribution, and compare the performance of the exponentiated exponential sampling plans with exponential sampling plans. These are few review of the literature. Now, in this paper, I have considered Birnbaum Saunders distribution for modeling lifetime data. Birnbaum Saunders distribution is a two-parameter lifetime distribution, and it is also known as a fatigue life distribution. Birnbaum and Saunders in 1969 formalized the fatigue life distribution, and it is named after them. The main advantage of Birnbaum Saunders distribution is that it can model the three forms of failure rates: increasing, decreasing, as well as unimodal or inverse bathtub shaped hazard rate. And Birnbaum Saunders distribution is having wide range of applications in the fields of fatigue and reliability studies. The Birnbaum Saunders distribution is having the probability density function given in the first formula, and cumulative distribution function is given in the second formula. Here, delta is the shape parameter and theta is the scale parameter. And phi, small letter phi denotes the standard normal density function, and capital phi denotes the standard normal distribution function. The mean life, the reliability function, and hazard functions of the Birnbaum Saunders distribution is given in the respective formulas. Now, coming to the special type of double sampling plan for life test. Special type of double sampling plan, we can say it as a extension of double sampling plan. And in this, the main importance of special type double sampling plan is that we are not making any decision about acceptance in the first sample. So the operating procedure is as follows. Select a random sample of size N1 from the lot and place them for life test. And experiment is stopped at a predetermined time t. And we will denote the number of failures before time t. And let it be denoted by the letter M1. If M1 is greater than or equal to 1, that is, if one or more failures occurs before time t, we will reject the lot. And if M1 is equal to 0, we will select another random sample of size N2 from the lot and place them for live test and observe the number of failures N2 before the truncation time t. And if in the second sample, the number of failures is less than or equal to 1, the lot is accepted. Otherwise, the lot is rejected. That is, in special type of double sampling plan, we will allow only maximum of 1 failure. And in the first sample, no acceptance is allowed. The OC curve and ASN functions of special type double sampling plan is given in these formulas. Here, P of x given in P denotes the probability of x failures in a sample of size n, which can be obtained using either binomial or Poisson distribution. Now, the designing procedure of live test sampling plan. As we all know, the lifetime of a random variable is a continuous random variable, and it can be modeled using any continuous probability distribution. So here, the Birnbaum-Saunders distribution is considered for the model of lifetime with parameters delta greater than 0 and theta greater than 0. The probability of one failure before time t is obtained using the cumulative distribution function of the Birnbaum-Saunders distribution. That is, t is equal to probability of t less than or equal to t, which is f of t theta delta. Now, criteria for obtaining the optimum parameters of the sampling plan are, as we all know, it is the probability of acceptance at P0 is greater than or equal to 1 minus alpha, and probability of acceptance at P1 less than or equal to beta. Here, P0 and P1 denotes the acceptable quality level and unacceptable quality level, or we can say that acceptable and unacceptable proportion of lot failing before time t, and alpha and beta are the producer's risk and consumer's risk. So, for a live test sampling plan, this P0 and P1 are related to the quantities of mean life, and we can say mu0 is the acceptable mean life and mu1 is the unacceptable mean life, which are prime focus of any product with lifetime as an important quality characteristic. So the criteria can be rewritten as probability of acceptance of mu0 greater than or equal to 1 minus alpha, and probability of acceptance of mu1 less than or equal to beta. So we can we should find the parameters, optimum parameters of the sampling plan satisfying these two conditions. Now, for finding an optimum sampling plan, the procedure is as follows. Specify the parameters or specify the acceptable mean life and unacceptable mean life, mu0 and mu1, with associated risk alpha and beta, and value of the shape parameter delta of the Birnbaum-Saunders distribution. Then, and specify the test truncation time t. We can obtain P0 and P1 corresponding to the values of t by mu0 and t by mu1 using the formulas of cumulative distribution function and mean of the corresponding distribution, Birnbaum-Saunders distribution. And the optimum parameters of the sampling plan can be obtained such that it satisfies two conditions: probability of acceptance at t by mu0 greater than or equal to 1 minus alpha, and probability of acceptance at t by mu1 less than or equal to beta. Numerical illustration. A special type of double sampling plan for live test with the desired discrimination is to be instituted. Then the lifetime of the product is distributed according to Birnbaum-Saunders distribution. Assume that based on the experiment results, the value of the shape parameter is taken as delta is equal to 0.75. Acceptable mean life and unacceptable mean life are specified as 5,454 hours and 3,243 hours, with associated producer's risk of 5% and consumer's risk of 10%. Then the test termination time is specified at 600 hours. And for the given requirements, we can obtain T by mu0 and T by mu1 as 0.11 and 0.185 respectively. And optimum parameters of the special type double sampling plan can be obtained as N1 is equal to 29, N2 is equal to 175, with ASN equal to 199. This optimum parameters are obtained such that the probability of acceptance at T by mu0 greater than or equal to 1 minus alpha, and probability of acceptance at T by mu1 less than or equal to beta. So satisfying these two conditions simultaneously, we can obtain the values of N1 and N2. Now the sampling procedure is as follows. Select a random sample of 29 items from the lot and place them for live test. And the test is truncated at the time of 600 hours. And observe the number of failures before 600 hours. And if one or more failure occur while testing the first 29 items, we will reject the lot. If no failure occurs, then we will take another sample of N2. N2 is 175. and conduct the life test for these 175 items. And if no more than one failure occurs, we will accept the lot. And if 2 or more failure occurs, we will reject the lot. In the second sample, if 2 or more failure occurs, we will reject the lot. And the items that survive beyond the time limit, truncation time, are treated as passed. The conclusion is a special type of double sampling plan for life test is proposed when the lifetime variable is distributed according to Baum-Saunders distribution. Parameters of the special type double sampling plan for life test N1, N2, and ASN are obtained under the assumptions of Baum-Saunders distribution for different values of the shape parameter. The procedures and tables for the selection of sampling plans are developed when lot quality is evaluated in terms of different criteria based on mean life, median life, hazard rate, and reliable life. The operating characteristic values of different proportion defective values were obtained, and conversion factors are provided, which would help to determine the mean life, median life, hazard rate, and reliable life for a specified test termination time and vice versa. The factors for adapting military standard 105D to lifetime reliability testing index by acceptable quality level are provided. These are the references. Okay.
Thank you, madam, for your nice presentation. Any questions from the audience? Yeah, please, sir. Carry on.
Oh, yes, please, sir. Please.
Thank you, sir. I have one question. How they have decided that the T over mu naught and T over mu 1? What is the relationship between the mu 1 and mu naught?
Mu naught is the acceptable mean life and mu 1 is the unacceptable mean life, and T is the test truncation time, the life test termination time that is fixed in advance according to the past experience. The relation between T by mu naught and T is that the the cumulative distribution function of the specific distribution is a function of T by mu rather than directly mu. So we can take it as a function of T by mu.
Do you have a comparative study with the Balakrishnan and Levy's paper? Balakrishnan et al. They also studied the Barham-Sundram distribution.
Actually, they have considered generalized Baum-Saunders distribution for constructing the sampling plans under census scheme.
They have also studied the same
generalized Baum-Saunders distribution. But this is the basic Baum-Saunders distribution, and I have not done the comparative study.
Okay.
Okay, sir. Thank you. Any other question from the audience? Okay. So if no other question, madam, the one thing is that have you derived the relationship between your N1, N2 for this particular distribution in terms of equations?
Yes, sir. I have done that.
But that was not shown here, or
no,
was
actually,
it ready with you?
No, sir. Actually, it is not ready. The thing is, we can obtain the N and C using the iterative procedure that satisfying the two conditions: probability of acceptance at mu naught greater than or equal to 1 minus alpha, and probability of acceptance at mu 1 less than or equal to beta. Satisfying these two conditions, we can obtain using the iterative procedure. It is Gunther's iterative procedure is used.
Professor Rajagopal, I think, come out with some question. I think. Please carry on, sir.
Any one or two simple environment or situations wherein this Birban distribution can be applied.
It is derived as a distribution of for fatigue life, modeling fatigue life, and human mortality also.
Okay, you might have given some applied example. So you might have applied your sampling plan in a real life example. Okay, all the best.
Sure, sir. I will do next time.
Any other question? Madam, in your process of development, you said that the distribution of shape parameter lambda, delta,
Yes.
And you have fixed it around 0.75, something of that sort. I don't remember it. So, and you say that it is based on the experimental result. So
Yes, sir.
how you are fixing the delta value there?
Actually, in the illustration, I have given some assumption kind of illustration. But in the real situation, we can say production process will start with the 100% inspection. And once the process is stable, we will go for the sampling plans. So from the 100% inspection itself, we can make out what distribution it follows and what will be the parameter of the distribution. From the results of the experiment, from the 100% inspection. And based on that, we can decide what is the acceptable mean life and unacceptable mean life from the producer as well as consumer.
But this looks somewhat contradictory in the sense before carrying it out, you need to go for 100% infection. That means the sampling plan is not at all necessary in the second stage. Once you start doing 100% for fixing the delta, then what is the need for carrying it out as a double sampling plan when you know the clear picture for all the values?
No, sir. If you are like once the process is stable, only we can use the sampling procedure, any lot by lot sampling procedure. So I'm saying before that.
No, can I interfere here?
Yeah, please, sir.
The very purpose of acceptance sampling plan, as everyone knows, is to give evidence to the consumer, that is the end product process. Therefore, in order to prove the quality of the lot, you have to draw a sampling, definitely. And these acceptance sampling procedures are required for a in-between process. So supposing that there are 2-3 stage production process, one output of one stage will be the input of the second stage. Certain inside situations can also be acceptance sampling can be used. Therefore, sampling is necessary in all situations in acceptance sampling.
Yes, sir. That is absolutely accepted. But my question is, she was telling that that delta was fixed using experimental value. How is it?
Can the candidate show that slide?
Yeah. That's what. Please go to the particular. Is it? Please pause if possible. Right.
Yes, sir. Is it visible?
Yeah.
Okay.
Little bit before this one. Yeah, this is exactly. Yeah, delta is 0.75 you claim, and that based on some experimental results. Okay, so what experiment you did and how you fixed it?
Sir, that's what I said, sir. This is actually based an assumption illustration is given for particular this value. What will be the sample?
Yeah, if it is assumption, it cannot be questioned.
Okay, no, I can help there, I suppose.
It is assumed.
Yeah, you can say.
It is not assumption. The statement meaning based on the experimental result, it is that they are mentioning they have taken a sample and they are using the term estimation. So from the sample, the parameters will be estimated. Then only these values will be used for finding NNK.
Yeah, maybe a pilot survey or something of that sort. Yeah.
Yes.
Maybe for a real data.
Or from past experience, that may be
maybe
assume
that
that
past
based on
experience or the real data. They can collect the real data and can estimate the parameters.
Okay.
And
so,
then apply
madam,
the.
Yes, sir.
Yeah, you can note down all the points shared by the great professors.
Sure,
and I think you can be very specific in your drafting. And when you say it comes from experiment, you can say within brackets it's from a pilot survey conducted prior to this particular model. Okay, so something of that sort, finer information you can incorporate. I think this part of the thing is going well, and I think this is a well presented and organized study presentation. Thank you, madam.
Thank you, sir.
I think we will move to the next candidate. The next candidate, first let me check whether he is present. Manish Kumar, present here?
Yes, sir. Yes, sir. I am present.
Yeah, the topic is a generalized class of estimators of mean of finite population using two auxiliary variables in two-phase sampling. Sir, you can share and proceed.
Oh, okay, sir. Okay, sir. Sir, my slide is visible?
Yeah, it's visible. You are audible. You can proceed.
Okay, sir. Good evening, all of you. My name is Dr. Kumar. I am working as assistant professor in Acharya Narendev Agriculture University in Ayodhya. I am going to present my research paper, a generalized class of estimator for the mean of a finite population using two auxiliary variables in two-phase sampling.
Sir, you can
The
maximize
overview-
by minimizing the right and margin, right? So you have a arrow mark there in the right side of your screen. You can click it and yeah.
Okay, sir. Full view.
Full view. Yeah. Okay, that is also possible. So you can directly also do.
Yes, sir.
So that gives more
yes, sir.
clarity. Yeah. Thank you. It looks nice now. Please.
Okay, sir. So the overview of my presentation consists of the abstract which I have submitted and the introduction part. The next one will be the existing estimator, and then the proposed class of estimator, and following that we will calculate the mean square error of the proposed class, the proposed estimator with the other existing estimator, and then it will be validated with the help of empirical analysis. And I have given certain conclusion on the basis of my study. This is the abstract for the paper which I am going to present. In this work, I have proposed a generalized class of estimator by reviewing the estimator of mean from the literature of sampling theory. And I have worked out the mean square error and compared it with the other existing estimator. And I have conducted an empirical analysis consisting of real data sets. Actually, in the sampling literature, there are mainly three types of estimator: ratio estimator, product estimator, and regression estimator. But sometimes we use a combination of estimator, such as ratio with regression or product with regression, so that the efficiency of the estimator will increase. And it will have the minimum mean square error. So in this direction, several authors have contributed towards the sampling technique and the estimation process. In this paper, I have suggested the estimator in case of two-phase sampling by utilizing information on the auxiliary variable. For the purpose of present investigation, I have considered 8 estimators of the sampling literature. The equation 1 represents the estimator developed by Sukhatme in 1962. Equation 2 represents the ratio estimator developed by Srivastava in 1970. Equation 3 represents the ratio estimator, which is a chain type estimator developed by Chan in 1975. The next one, equation 4, represents the estimator developed by Mukherjee. Equation 5 represents the estimator developed by Singh et al. The next is the estimator developed by Hendig, which is given by equation 6. And then the Singh and Chaudhary suggested the ratio type estimator by using exponential type chain estimator, which is given by equation 7. And later on, in 2014, Singh and Madhi developed estimator, which is given by equation.
Yes, sir.
So,
please. Yeah, please.
Yes, sir. Please, sir.
Yes, sir. So these are the estimators.
Hello, just Manish Kumar, please 1 minute silent. Sir.
Yes.
Manish Kumar is requested to on his camera because the presenter is also recording.
Yeah, please on your camera.
Manish
Actually,
Kumar.
sir, my laptop camera is not working, sir.
Okay, carry on.
Carry on.
I am presenting with the help of laptop and the camera is not working, sir.
Okay, go ahead. Go ahead, present.
Oh, okay, sir.
Manish Kumar ji, your voice is not coming.
Yes, sir.
Hello?
My slide is visible, sir.
Ah, yeah,
Yes.
please
You
go
can-
ahead. Please do presentation. Continue.
Yes, sir. Yes, sir. So in this paper, the 8 equations I have given, which represent the equation that was suggested in the sampling literature for estimation of the mean into phase sampling. Now, the mean square error of all these 8 estimators, which was suggested earlier, is given by equation 9, 10, 11, 12, 13, 14, 15, 16. So this represents the mean square error of the suggested estimators in the sampling literature for the estimation of mean into phase sampling. Now the notations that I have used is the usual notation. And now the proposed class of estimator. We have extended the work of Handy by judging the estimator. So the proposed estimator is given by equation 18. In this case, we have taken alpha and gamma as the scalar, which can be some function of unknown parameters of the auxiliary variable. And in this case, we can see that for suitable choice of alpha and gamma, we can get a plenty of estimators, which will belong to the proposed class. For example, the remark 1 represents that for alpha equal to 1 and gamma equal to rho xz, the proposed estimator reduces to the Handic estimator, which is given in equation number 6. And that is the equation E6, which represents the estimator suggested by the Handic. So this is a particular case of our proposed class of estimator. Now we have worked out the mean square error of the proposed class by considering the transformation as suggested in the slide. So we are representing the proposed class of estimator T in terms of the error function, and we get the equation number 20. This equation to obtain the mean square error of the proposed class. So finally we will get the mean square error of the proposed class T by equation 22. Now we can see that there is a term xi. So we have obtained the optimum value of xi for which the proposed the mean square error of the proposed estimator T is the minimum, and that will be given by equation number 24. Now we have the following theorem that the mean square error of the proposed class T will have a lower bound, which is given by the equation number 25 for the optimum value of xi, which is rho yz cy upon cz, where cy and cz represent the coefficient of variation of the variable y and the auxiliary variable. Now we have compared the efficiency for the proposed class with the other existing estimator. First, we will compare it with the usual unbiased estimator, that is the mean y bar, and it is given by condition 1. In the second condition, we have compared the proposed estimator with the Sukhatma estimator, and similarly, in proceeding in a similar way, we have obtained the conditions, theoretical conditions, up to equation number 9. Now, for the purpose of present investigation, we have conducted an empirical analysis by considering the natural population data sets, and the population which I have considered is the population 1 by Anderson, the second population is by Cochrane, the third one is by the Handic, and the fourth by Murthy, and the fifth by Sukhatme and Chand. Here we have used the real data sets for obtaining the percentage relative efficiency of the proposed class and compared it with the other existing estimators. The percent relative efficiency table is given in equation number in table number 1. Here we can see that the estimators are presented and their corresponding PREs are obtained for all the 5 natural population data sets. And now we have the conclusion from table 1. We can see that T is the proposed class of estimator, and it is given in the last row. We see that the percentage relative efficiency of the proposed class T is maximum in all the 5 populations. So we can conclude that the proposed class T is more preferable and accurate for estimating the mean in case of two-phase sampling. And here we can see that the handicap estimator, which was the particular case of our proposed class, achieves the percentage relative efficiency less as compared to the proposed class. Now, in this case, we can conclude that the proposed generalized class of estimator consists of as many estimator by choosing the value of the scalar alpha and gamma, where alpha and gamma can be the real number or the function of unknown parameter of the auxiliary variable. We have established theoretical as well as empirical analysis of the proposed class T with the other existing estimator. There is one more conclusion that as our estimator include the auxiliary variable and the efficiency is increased, so we can say that by using the auxiliary variable, our efficiency is increased as compared to the usual unbiased estimator y bar of the study variable. So we can present the present work can be extended further by utilizing information on multi-auxiliary variable. We have worked out in the case of two auxiliary variable. It can be generalized for the case of multi-auxiliary variables also. So these are the references of the present paper, and this one is the reference. Thank you.
Yeah, it's a good presentation. So any question from the audience? So any question?
Yes, sir.
Yeah, please.
Is this the only population for which this proposed estimator is better as compared to the existing, or in general you can say this proposed estimator is better than the existing ones?
No, actually, we have obtained the theoretical condition under which the proposed estimator will be better than the other estimators. Theoretical conditions have been shown. So I have considered only 5 natural population data sets. We can check for other population also.
Is there any? Have you checked? Is there any estimator which is existed, which gives less mean square error as compared to this proposed estimator which you have proposed now?
I have actually compared my proposed estimator with the 8 existing estimator. So I have worked out with the 8 existing estimator and not all. So we can check for other estimator also. We can check the efficiency.
Yeah, you can check, but under certain conditions.
No. I interfere here. What Farooq Dar asking, whether have you taken the basis as MSC or bias for numerical comparison of these proposed estimators with respect to existing estimators?
Yes, exactly, sir.
I think Farooq is asking like this, right? Hello?
Yes, sir.
Yes, sir. I have obtained the mean square error criteria.
Yeah, that's he asking.
Yes, sir. Yes,
sir. Yes, sir. I want to say, is there any existing estimator which gives less mean square error, but you have obtained less mean square error as compared to the existing ones under certain conditions only? So if the population have that conditions, then only you can use this estimator. Otherwise, there are estimators which are given which gives the less mean square error as compared to this.
Yes.
So his question is something like, do you have any condition on your population, whether population structure, population distribution? Do you have any condition on your population from which you draw the sample?
No, actually, I have used the population from the earlier works of I have mentioned the source from where I have collected the data, and from there I have checked the theoretical condition, and then I have calculated the table for the percentage relative efficiency.
Yes, sir. Under that conditions only you are using the estimator. Otherwise, otherwise it is not better to use the estimator.
So one thing is that one thing is that going by the variety of estimators that he has compared right from Sugatme's one from 1962, what I feel personally is that I think to date I think this estimator is going to serve as the best unless some other person comes out with less mean square error with some other estimator. So that is one variation, because you can see a variety of estimators, of ratio estimators using auxiliary information in different
yes, sir.
formats. So to some extent, we cannot guarantee that is not always there in any scientific research or proceedings. Okay, to some extent, with some 95% confidence interval, so to say, in statistical sense. So its estimator seems to work well. Any other questions, sir?
Can I have a look on the references?
Thank you.
Which
please,
basis for
sir,
this
carry
work?
A slide number, sir. Which page?
References.
Reference ones.
Acha, references.
The particular article which is basis for this work.
This one. Handy 2012.
Okay, thank you. I have taken a screenshot.
Yes, sir. Handy 2012 from this article I have suggested the GIS document.
Okay, thank you.
Okay.
Okay. Any other question from the audience? So more question in some sense is a measure of your success. So you have reached them and as a reaction questions are pouring out. Okay, if no other question is there, then I have one question. See, in the development process, you are mentioning two parameters, alpha and gamma, right? So two parameters, alpha and gamma. And towards the end, possibly in the conclusion section, so you claim that they can either be constant or functions, say something like covariance or correlation, right?
Yes, sir. Yes.
So my question is, if it is taken as a covariance or correlation or some other moments of the auxiliary variable already used, like Z, or a new variable, maybe some Z1, Z2, etc., that is okay. So can you think of that gamma and alpha being constant in any situation? Can you come across?
Sir, yes, sir. By considering the alpha and gamma as one, we can see that the proposed estimator, I will show you in the slide, sir, this. Yes, sir. In equation 18, if we consider alpha and gamma, alpha as 0 and gamma as 1, then the proposed estimator reduces to the regression estimator into phase.
Regression estimator. Yeah, that's what.
Yes,
See, yeah, that's what I'm telling. Okay, you can even imagine some other value also other than 0 and 1. But my question is, this estimator to some extent improves, getting improvement, or provides better MSc of that sort. Okay. Basically, I don't have, it's only an intuition. If it is going to be a constant, okay, either, as you mentioned, it will reduce to one of the previous existing estimators. Okay, for different combinations, different estimators also possibly. One combination you have given 0 and 1. Okay, but unless they are functions of say auxiliary variables, okay, auxiliary variables, I think we cannot improve further, it seems, because you have done more work, so you should be in a position to throw more light. Can you did you come across any other situation in which different constants, rather than say gamma, I mean rho or covariance of that sort, okay, different constants, pure constants, and still getting good results than the existing one? Did you come across any such thing?
Sir, I have actually used the particular case handy, and you can see in remark 1, I have taken alpha equal to 1 and gamma equal to rho sz. So by using that condition, it reduces to the handy. But I have given one theorem that the optimum value of MSc, the minimum MSc will be the lower bound will be in by the term of equation number 25. So optimum estimator of the proposed class will be that estimator which will have the lower bound suggested by equation 25.
What about rho there? Is it correlation between y and z?
Which one, sir?
No, yes, no. In your lower bound, there is a correlation rho.
Yes,
is it
sir.
Correlation coefficient between y and z?
Yes, sir. Correlation between y and z, and rho yx is the correlation between y and x.
Okay, okay. So this inequality you are able to reduce, and this holds good for any value of gamma and alpha, it seems.
Yes, sir. Actually, for alpha and gamma, we can take any value of alpha and gamma, but the mean square error, the lower bound of the mean square will be that 25. Other will be can be more than the this lower bound. You can see here in the table that here you can see that YH bar, the Handic estimator, for the first population, the mean is percentage relative efficiency is 188.09. 188.09 for the first population for Handic. And for the proposed class optimum MSC is 196.39. So here we can see that the change, there is a change in the MSC. The Handic, we cannot regard the Handic as the optimum estimator of the proposed class.
Yeah, yeah, that seems okay. So the lower bound that you are, is it the lower bound you have derived it, or you have taken it from some other paper?
No, sir. This I have derived it. I have suggested that the Handic is not the optimum estimator.
Okay, that is okay.
So
Lower bound means that is the minimum attainable thing. So any other estimator has to be upper than somewhat lower than this. Okay, that is accepted. But see, the problem is when you are deriving a lower bound. Okay, associated. Can you fix any optimal alpha and gamma? So to attain this bound.
Actually, I have attained the optimum value in a combination form, and that is represented as xi. Sir, here in equation 20.
Oh, that's very nice.
Xi as a function of alpha and gamma, and
No.
value of xi,
have
which I have obtained. Yes, I have obtained the value of xi by equation number 23.
23 provides xi. So will does it uniquely fixes your alpha and gamma?
No, sir. Actually, alpha and gamma in combined form, they are represented with the help of xi, and the optimum MSC will be obtained by reducing it by derivating the mean square error with respect to xi and equating to the 0 using the condition.
What is the relationship between alpha and xi?
The relationship is yes, sir.
Have you derived it? Relation? Have you put it here?
Yes, sir.
Relationship between alpha as a function of xi. Do you have it?
Yes, sir. Here you can see below equation number 20 in the slide.
Psi is equal to alpha into z bar something.
Yes,
yeah, that simultaneously associates alpha and gamma. That's what I am asking. I want gamma alpha as a function of xi, some f1 of xi, gamma something like f2 of xi.
Yes, sir. Yes, sir. It is in combined form.
Okay. Then possibly there might be some internal association between alpha and gamma, but which is also expected naturally.
Right.
So they cannot be totally two independent parameters which bring down to the minimum possible value. Sir, it is a wonderful work, and I think we enjoyed a lot by your finer details, as well as getting clarifying our questions to a greater extent. Sir, all the best, and carry on your research with more enthusiasm.
Thank you, sir.
So welcome. So I think so any other speaker we have, those who have left in between now joined?
Shall I announce, sir?
Sir, please.
Yeah. I think Kapil Kumar is present right now. M Kalaivani. TN Kavita.
I think Kavita has completed it.
No,
not okay.
And another is A Naga Durgamba. I think these four people are absent in this session.
Okay. So if possible, I think shall we accommodate somebody else from the other session? If we have some time issues.
Sir, what they have given a list for this session. The 13 people list are given.
Okay,
And I
fine.
think those of 9 people were present in this session, and they have presented their work.
Okay,
and
fine.
4 people are absent. No further list is with me right now.
Okay,
Therefore, we have to conclude here itself.
Sure,
Sir, time is up, sir. Anyways.
Yeah, sure.
Yeah. So, first of all, let I thank our great honor and privilege. Sir has accepted our invitation in a very short notice and chaired the session of technical session 3 of day 2 of this international conference on CRO, School of Thought. It is very great, and we are very thankful to sir. Sir has chaired this session very nicely. All the session went on very well, and lot of good discussions and comments are invited from the participants, and they, especially Rajgopal and G. Srinivasa Rao. They have given lot of good comments to the, including the our Professor Viswanathan sir has given lot of good comments to the our presenter. Yes, I am sure, sir. Surely they will get benefited with these comments. And this session was very nice. And this session was basically reliability, survival, and sampling theory areas covered, and acceptance sampling plan also. So really, it was very great, sir. Thank you very much, sir, for chairing this session. Thank you very much, sir. And now over to our general chair of this conference, Professor P. Tirupati Rao, sir. Thank you, sir.
Sir, unmute and speak.
Sir, unmute your mic, sir.
Session chair has already made comments. Sir.
Sir, I have made as and when the candidate completed his thing, and yeah, one general comment I want to make it, provided if you permit me for 2 minutes.
Will be the conclusion.
Okay. Sir, in the sense,
Viswanathan sir for accepting our invitation.
It
is in a 11th hour, not in 11th hour. 11th hour, 50th minute. 50th minute it was asked. So we are. This is the occasion which has we know that Professor Viswanathan is a highly dependable, and whenever we are in crisis, we may bank on him. That is what I am. Actually, your participation is adding lively interactions to the conference, sir. So really, I'm very happy. As Naveen Chandra correctly pointed out that the session participants today, who are presenters today in this session, are very lucky that chairing session is having keen observations on all the works. Almost peer review was happened in this session. And moreover, 2 more speakers, Professor Naveen Chandra mentioned that one is G. Srinivasa Rao and another is Rajagopal. Both also very vibrant researchers. And it is one way better to know the researcher whether their ideas are in correct path or not. So they can make refinements before publishing this activity. Definitely, the very purpose of these type of events is to have the feedback on their thought process. Okay. So it is a matter of every researcher is making an amateur activity. We cannot say researchers are doing a perfect or perfection professional way of presentation. So every day is a new learning, new beginning. In that respect, a researcher with a new thought has to be appraised. I mean, has to be encouraged. What I understand. So mind, what you call it is brainstorming on these intellectual forums will always help the budding researchers to make their path firm. Okay, so therefore I'm hoping and optimistic that some of the papers are going to be for peer reviewed and also withstand in the peer review process. Anyway, we are making the next step of things that already among the participants, one is Professor Suresh Daman from UK, London. He has given offer. He is editor for 2 or 3 journals he has mentioned. And Suresh Chandra Malik is having one journal. And one person is not presented, but he is having regular interaction with from Iran. He has also promised that he is having 2 journals in optimization techniques. So right now we have 4 to 5 journals. People are interested to publish our works. So therefore, your comments definitely will add the value for our review process. We will send the papers again, sir, to you, Viswanathan, sir.
Sure, sir.
So you have to give a remark on each title after reviewing of yours. Then only we will consider for the papers whether to be published or not. Okay, we will send the communication soon to you. So among which who are presented, our Naveen Chandra will give. Basically, the Naveen Chandra report we will send. We will send again to that report to you. Yeah, report to you. Then your opinion is also we need, sir.
Sure,
Okay?
Professor. We will.
So for only presenting papers only, not all. Not all.
Okay.
Okay.
Thank you,
Thank you, sir. Thank you very much. Now the time is 5:10. We have to start the next session. We don't have time, sir. 2 to 5 only your scheduled time.
Yeah.
Your scheduled time is 2 to 5.
Even 4 people are attending.
5 to 5:30 is tea break. Let us
Okay.
let us allow people to have some cooling. Otherwise, they may not be comfortable with us.
Thank you, sir. Thank you, sir.
Thank you, Naveen Chandra, and
Thank you,
all
sir.
the senior participants in the board.
Thank you, Mr. Nathan, sir. Thank you.
Thank you, sir. Thank you. Sir, Sivasamy, sir. Sir, wear your shirt, sir.
No, sir, you should ask in Tamil. Eppadi irukkinga, sir?
Okay. Right, sir. Right.
Thank you, sir. Thank you.
We'll meet again 5:30.
Thank you, sir. Thank you.
Right, sir. Thank you. Ganapati.
Yes, sir. Sir.
Received your this one, that YouTube link for 28th technical session.
Yes, sir.
Whether it is created for 28th main session. Ganapati is not there.
Sir, Ganapati might be on the, we said no, we are shifting. I came to the department now, so he will come, sir.
You are operating from department?
Yeah, right now. Just now we are shifting. He is going home and then he will connect from there.
Okay, okay.
Yeah, sir.
So
it's working from the department, so it's fine. Like past 1
there
hour
is
I
no
went
issue. No issue, no?
No, no issue, sir.
You are working from research scholars room, huh?
No, sir, sir's room, sir. From your room, sir.
From my room?
Yeah, yes, sir.
That signal is okay?
Yeah, it is working, sir. It is all fine. Yeah,
So
we checked
you
everything.
okay.
He came here and we checked everything and went, sir.
Okay, thank you.
Okay, sir.
So you know that how to start the recording, everything, am I right?
Yes, sir. Yes, sir. Yes, sir. I know, sir.
Oh.
I can do it.
Hello, sir. Sivasamy, sir. How are you, sir? Unmute your mic, sir.
I'm fine.
How are you, sir?
I'm fine. Safe.
I'm fine. Good, good. Today, now you are having session, no?
Huh?
You are having talk today. I mean,
Yeah,
now.
yeah. I am listening.
Present session means what I understand. There are people. Just a moment, sir. I will just go through it. Only 9 it is. Yeah. Vaichanathan is chairing the session, no?
Okay.
Yeah. Have you received communication, sir? Repo, I mean, schedule.
Yeah. The
Yes.
schedule I received yesterday.
Okay, yourself, one professor from Sri Lanka.
Okay.
Samanti Konara Singh. She is from Sri Lanka. Professor Anup Chaturvedi from David Hanagal. Hanagal is another one. Professor Parameswar Pandit, and then Sivasamy. One named by Professor Praful Kumar Swain from Utkal University. So use these people, I think, today's session. 1, 2, 3,
Sir.
4, 5, 6, 6. Yeah.
Sir.
Yes.
Only Professor Anup Chaturvedi has sent the PPT, right, sir? Anyone else has sent paper and the PPTs?
PPT, are you having with you?
Yeah, Anup Chaturvedi I am having.
So
sir.
he want to operate from our end, huh?
No, I don't know, sir. You have sent the mail to me. I have got the PPTs. I have kept it ready. Like if required, we can do it from here, sir.
PPT. Anup Chaturvedi, you have to send to Vaichanathan.
Yeah, the other slides I have sent, sir.
Anup Chaturvedi also you send.
What, sir?
For Vaichanathan, yes, Vaichanathan. Because he is chairing the session now.
Yeah, sir. That not the PPT, sir. His presentation.
Presentation, safe side, you keep it.
Yes,
When
sir.
it was asked, you have to show from your end.
Yes, sir. I'll do it.
Introducing him, that PPT you have to send to Vaichanathan.
Yeah, that is already been done, sir.
Yeah. Okay. It is with Vaichanathan already?
Yes, sir.
Welcome, Professor Anup Chaturvedi, sir. Welcome, sir. Unmute your mic, sir. Professor Anup Chaturvedi is there. Samanti Konara Singh. Hello, madam. How are you?
I'm fine. How are you?
Welcome to India on virtual mode.
Yeah. From the morning, I was here time to time.
Yeah. Where is your hometown? What is your
I'm in Colombo.
Huh?
Colombo.
Colombo only. Okay, capital.
Yeah.
Good. So, what are the major cities, madam, in Sri Lanka after Colombo?
Colombo, Kandy, Gaul, Mathura, and things like that.
Okay. So you are operating, are you local of Colombo or you are near to that place?
We are in Colombo and the office also in Colombo.
Okay. So you are born and brought at Colombo, it seems.
Yeah. Yes.
Good.
Have you been to Sri Lanka?
No, madam. Let us have some near possible occasion after COVID.
Yes, exactly.
So COVID in one way has made many positive things, and we are able to meet with no cost. We are meeting all. Okay, if otherwise if it is a physical meeting, we have to spend so much of money, the expenses. So in terms of time, in terms of cost, in terms of efforts, everything.
Yeah.
Welcome, Pandit ji. Parameshwar Pandit ji. Welcome. So today's session we are having professors from Konara Singh, Samanti Konara Singh. What is the pronunciation, madam? Samanti or Samanti?
Samanti.
Samanti. Okay, sorry.
Konara Singha.
Konara Singh. Okay.
Konara Singha.
Konara Singh. Okay.
Yeah.
Oh. Okay. What are the official languages there in Sri Lanka?
In Sri Lanka?
What are the official languages? Only.
The Sinhalese and Tamil.
Oh, Tamil also official language.
Yeah.
Okay, good.
English has become a working language, but it is not official. Official languages are Sinhalese and Tamil.
Oh, I see. Okay, Tamil is become official language in Malaysia and Singapore also, it seems.
Really?
Yeah. So the speakers now. Welcome, sir. Namaste ji. Professor Anupam Chaturvedi. Anup Chaturvedi, not Anupam. Anup Chaturvedi. Nice, sir. Welcome.
Can you hear me?
Yeah. Yes, you are audible, sir. You are audible and visible.
Okay.
Clear. You are clear. So, how is your environment there, madam? You are seeing.
Yeah.
How is that weather there?
That's why I'm looking at the sky. It's very dark. We'll see.
No problem, madam. It will
Not
be.
yet started, but about to. We'll see.
Okay. Oh, okay.
The monsoon is activated and thundering, and so like you are lucky. Normally it start about 3 o'clock, but today it didn't happen yet.
Okay. We'll see that. Definitely, we will make it. We have very good signals. Our program is going on without any interruptions. No problem. God Almighty is in our favor. No problem.
Now my presentation is at 5:30, no?
Yeah, first presentation is yours.
That's fine because it is about to rain. So if you manage to finish, that's fine. Because here it is very risky, like the thundering is very bad. So we are supposed not to have the telephone conversations or anything. Like a lot of people die with that one. And the telephone, the breakdowns and so many problems with the thundering. So we'll see.
Okay, somewhat you are lucky because you are in capital. So therefore some infrastructure issues will be having advantage. When interior Sri Lanka, you may have some more issues. Because you are in capital, somewhere you are blessed with certain immediate facilities. Yes. Vaidyanathan still to come. Just now we were. How it appears, sir? Just now I pronounced your name, Vaidyanathan.
Oh.
It appeared on the screen.
Yes.
It's so accidental.
That is the power of the thought.
This is what I used to believe that communication among cosmic bodies.
Right. Namaste.
Thank you. We are all on time. All speakers are also on the board now.
Yes.
Earlier we used to use the term called on dais. Now we have to say that on dashboard now.
Correct. Virtually. Yeah, I am able to see some speakers.
So,
Yeah.
so much of new terminology are coined thanks to COVID.
Yes.
So it's very nice occasion that people from different parts of India and different parts of Professor Anup Chaturvedi from Allahabad University and Professor Pandit from Bangalore University, Professor Samanthi Kumar Singh from Sri Lanka, Colombo. She is the director for Institute of Mathematics and Management. It's a very nice combination, madam. Institute of Management and Mathematics. Which is first, mathematics or management?
Mathematics is first.
Mathematics is first. So, being a statistics person, we are happy that you are heading Mathematics and Management Institute. So very
Actually, my base is mathematics. That's why.
Oh, good. So you did masters or PhD in statistics?
PhD in statistics. All the others in mathematics.
Okay.
I mean, I have masters in both mathematics and statistics.
Oh, both. Okay. Where you did your PhD, madam?
In the University of Peradeniya, Sri Lanka.
Okay. Right. Sir, Vajranathan sir, had you received all the material?
Yes. I have got everything. Yeah.
So there are six speakers today. Professor Madam Samanthi Kumar Singh from Sri Lanka. Second one is Professor Anup Chaturvedi.
Yes.
And Professor Pandit from Bangalore University. Then Professor Sivaswamy, it seems, another one. 4. And Praful Kumar Swain.
Correct.
That is, one more name is there?
Yeah, Professor Hanagal is there. David Hanagal.
Yeah, Hanagal sir also will join us. So, former professor of Pune University.
Yes.
Okay. So, now as we are all on time, if you wish, you can start. Now, I would like to take the privilege of inviting all the people, particularly invited speakers and delegates. Very interesting. Delegates are also from various parts of the globe. So, I'm very happy that Professor CRO School of Thought has attracted many vibrant researchers, either from budding to established researchers. So this today we have a third session of invited speakers. I mean, now it is the third session on second day. Not third. Is it fourth session? Am I right, sir? It is
fourth session of the second day.
Yeah, fourth session of invited speakers. So, yeah. So for this program, our Professor Vaidyanathan is right now, some reasons he is an assistant professor, but his professorship is due, not even associate professorship. Okay. So there are some lagging issues in our university. He was a worst affected person. Okay, anyway. Now I think I can safely claim and call him as a Professor Vaidyanathan. He is going to chair the session today. Professor Vaidyanathan, who is a professor of our department, he did his master's program from Madras University. Basically, he did his master's program and I think master's program from college and Laila College, sir, where you did MC College.
Yes, sir. Yes.
Laila. Yeah. So better you introduce yourself, then
yes.
other programs. Now I switch on to Professor Vaichanathan. Over to Vaichanathan.
Yeah, thank you, Professor Tirupati Rao, for giving me an opportunity to chair this session of intellectual speakers, and I welcome all the members on behalf of our department for this fourth invited session of the second day of the virtual conference. Now, as Professor Rao was telling, myself, Dr. Vaidyanathan, I joined this department in 2010, and before that, for more than a decade, I was working in Loyola College, Chennai. So I did my master's and bachelor's degree in statistics from there, and my PhD is from Madras University. I basically work on distribution theory, data mining, so and with statistical inference. So this is my related area of interest, and I have been guiding PhD scholars. Two scholars have got degree under me, and some people are also on the pipeline. They are working. So this is just a brief introduction about me. So as per the program schedule that I can see today, we have got 6 speakers, and all of them are going to talk on various topics, but generally it's basically modeling. What I can see the commonality between all the speakers is that there are modeling like statistical models, frailty models, stress strength model, and joint modeling of longitudinal and time to event data. So I think it's basically some sort of a reliability session with distributions coming into the picture. That's what I get a fair idea when I look into the topics. But anyhow, once we know the content, then only I can tell what actually we can know what actually is the talk about. But anyhow, on the face of it, it seems that all the topics are quite interesting. So yeah, so I think without wasting much time, I will go for first speaker, calling the first speaker. But before that, it's my privilege to introduce maybe for 2-3 minutes about the speaker, and then I will hand over the session to the speaker. So we can have some sort of 25 minutes for lecturing for this talk, with some sort of interaction maybe for 5 minutes. Okay, so that's how we plan this session. So I just share the profile of the first speaker. So the first speaker on board is what we have is Dr. Samanthi Konarasinghe. Madam, I don't know whether I'm pronouncing your name correctly. There is any mistake, please. Yeah. So I'm just sharing my screen. I don't know whether it is. Yeah, it should be visible. So yes, sir. Yes, thank you. So the first speaker for today's session is Samanthi Konarasinghe. She is presently the academic director and statistical consultant, Institute of Mathematics and Management, Sri Lanka. So we have got a very brief bio information about Madam. So Madam actually is an award-winning scientist and has served as a statistical consultant and a lecturer for more than 2 decades. And she has credit. She has developed various mathematical and statistical techniques. Some of them widely applied are circular model, circular indicator, and SAMA circular model. Okay, so she is basically a multidisciplinarian. She has obtained her Bachelor of Science degree in mathematics and postgraduate diploma in industrial mathematics, Master of Science in applied statistics, Master of Business Administration, and PhD in statistics. And apart from that, she has got some, I think it's some sort of an attraction towards the fine arts also. She has got the diploma in classical music, and she is a member of American Statistical Association, Institute of Applied Statistics, Sri Lanka, National Science Foundation, Sri Lanka, and she is also the editor of a good number of journals like Journal of New Frontiers in Mathematics and Statistics, Journal of New Frontiers in Economics and Business, Journal of New Frontiers in Healthcare and Biological Sciences, similarly in Education and Social Sciences, published by Institute of Mathematics and Management of Sri Lanka. And she is also an editorial member of American Journal of Theoretical and Applied Statistics. And she is an advisory member or a technical or scientific conference member of Scientific Technical Research Association. And she has got the best paper award from the International Conference on Advances in Mathematics, Computers and Physical Sciences, and the International Conference on Business, Economics, Social Sciences and Humanities. And she was awarded IMR of Best Scientist Award India. And she has been invited to speak on various topics and share her knowledge as keynote invited speakers in various international conferences and forums in Thailand, Singapore, Malaysia, India, and Australia. And she was also the guest of honor and the chief guest of many international research forums. So one more credit is that, most interestingly, Dr. Samanthi is not only a scientist, as also an artist. She is a violinist, a painter, writer, drama producer, and an actress. So I think this is just a tip of the iceberg that what we have seen on her profile. And possibly what I see is that she is a multi-talented personality, not only on academics, but also to her credit in fine arts and literature. So that's a very rare combination, madam, that we observe in academic circle. Anyhow, with these few introductory remarks, I welcome you, madam, to give your talk.
Adding one point to your Vaichanathan, math
Yes,
and music are the divine subjects. So madam is making both math and music. So very
yes. Rare combination.
Okay. Thank you so much.
Yes.
Yeah.
First of all, I would like to thank Professor Tirupati Rao for inviting me for this great event. And I can't forget my friend, my good friend, Professor Rajeshwari of Pondicherry University. She's the one who introduced me to
Actually,
Pondicherry.
she introduced you.
Yes, she introduced me. We have met in Madurai 2 years ago. So India is like Tamil Nadu is a known place for me. Like before this COVID came, several times a year I used to visit Tamil Nadu for several conferences. So then I'm waiting till the boundaries open for me to come again for India and other destinations. Anyway, as Professor Rao said, good that at least we can meet this way. Thanking the technology, we can at least meet this way. And the Professor Rao's wishes are very powerful because, you know, in Sri Lanka, these days the monsoon is very the unpredictable. Like every day, after 2 o'clock, it is heavy raining and thundering. So I told him that sometimes I might not be able to do the presentation due to the disturbances from weather. But confidently, he said, "No, madam, everything will be fine." Yes, it is. It is the sky is very dark. I can see. No, they're not going to disturb us. So powerful person. Okay, let me start this. Is my PowerPoint sharing?
No, it's not till now.
Yeah, it will come. I think it is buffering. Had you shared, madam, present now option? You select the option present now.
Wait, give me a second.
Yeah.
Turn on captions, is that? Or the present now, right?
Yeah. Present now. Present now.
Present now, then a window.
Total screen.
And click on that PDF or PPT. First to open that PDF or PPT.
Okay, I'm not that used to the Google. I'm so used to the what's called the other one, the Zoom. So the present now, the entire screen or the window?
No. First you open your PDF or PPT, madam.
Yeah.
You keep it
and then
minimize
then
it.
you go to the present now.
Yeah, it is already open and it is minimized.
Okay, fine. Then you go to the present now.
Oh.
There you have got an option, present a window.
Yeah.
Yeah, if you click that window, you can see that PPT will be there or PDF will be there. Yeah, you can click there and share. Is it coming?
my, let's see the entire screen. Oh, it's not present now. A window. It's not appearing.
Madam, you are using which browser, madam?
Yeah.
You are using which browser?
The
or?
Chrome.
Yeah, it's coming.
Yeah, now
madam.
it is coming.
Yeah, it's coming, ma'am. Just
coming. Yeah.
Coming.
It's coming. Ah, okay.
Yes. You just now just click that PPT.
Yes. How is it now?
No. You want to
No, you
share
have to open your
PPT or PDF?
It is a PPT.
Yeah, now you just select you just open your PPT, ma'am, in desktop.
Yeah, it's already open and it says sharing.
Otherwise, you just minimize this the screen. Minimize this Google Meet screen. Minimize.
Yes, it's coming. Seems it's coming.
Or PPT is not to open, I think.
No. PPT, you give a click and you press one arrow button, madam.
How is it now?
Now white screen came means a blank screen it is. You just give press one arrow mark, any arrow mark, or enter button.
Yeah, did. It's not sharing.
No. Are you seeing that PPT in your desktop?
Yeah, I'm seeing it in my desktop. And it
Okay.
says it is sharing.
Okay. Wait. Can you please once again? No. Just please close your PPT and please once again open one. Just minimize this browser. Now
Yes, you are presenting to everyone. Click here to return to the video call when you are ready to stop. Oh no, that is that.
Yeah, otherwise
And
you just
now
stop
the
the
presentation.
person.
Yeah, now the
One
presentation.
second.
Yeah.
Your PPT is not visible from others. You just
Shall I
stop
quickly?
your. No. You just stop your sharing now first.
It's not sharing now.
Yeah, make it stop sharing now. You do it from beginning. Okay.
Okay. Let's do it from the beginning.
Yeah. Please once again. First you open your PPT, ma'am.
Okay, it's open.
After
And
that
then go to the meeting.
Present now. Yes.
Then the present now.
Enter
Window.
Okay.
Yes.
You just select that.
Sorry,
You just if you
And
select a
share.
window means no. You just select a enter
Select the window, madam.
Yes.
It's
Yeah.
coming.
Yeah.
Okay.
It's coming.
You can put it into slide view.
Yes, ma'am.
Yeah. It has come.
Continue.
Okay, finally it came.
You can put it into slide view. Yeah. Yes. Fine.
Okay.
It's fine. Yes.
Right. Okay. So once again, thank you for giving me this great opportunity to international virtual conference on Prof. C.R. Rao School of Thought on Statistical Sciences. Today, I'm going to talk on role of statistical models on real life. I don't need to introduce myself. You all have introduced already. So my topic is role of statistical models, but I'm starting from mathematical modeling instead of statistical model. So what is mathematical model? Mathematical modeling is converting a real world problem into mathematical language. It is known as mathematical modeling. So if you go back to the history of mathematics, like initially only the theoretical side was there, and later the Romans were the first to use applied mathematics. That means using mathematics in real life situations. So later it became very popular, and actually there is quite a useless argument whether the pure mathematics is more important or applied mathematics is more important. I would say both are equally important, because without pure mathematics there is no applied mathematics, and if not applying in real life, that also some sort of not useful. Anyway, like at present, the mathematical modeling are widely used in real life applications. So briefly, we'll see what is mathematical modeling. This is the process of mathematical modeling. Whether in any field, whether it is agriculture or meteorology or biology, medicine, healthcare, in any field, the mathematical modeling, the process is this. This mathematical modeling begins from the real world observation. Actually, we don't see the problem, we observe something. We would say, like, you feel like you get a stomach pain. That is a symptom. When you go to the doctor, you would say, doctor, I'm having a stomach pain. So then that is the symptom. Then the doctor will start thinking, as shown here, the doctor will start thinking, 1 minute. Okay. The doctor will start thinking, what would be the problem for this one? What are the root causes? Same way, like this mathematical modeling. Maybe a company or maybe the university. Like a university, you observe that the mathematics or statistics results going down. That is an observation. So you start thinking, what are the reasons? Actually, you speak to the students to get some idea. You speak to the lecturers and parents or something like that. And based on them, you devise a mathematical model, like some sort of mathematical model. Then what you do is you make use that mathematical model for estimations. Actually, we would say predictions, but actually speaking, it is estimation. Then once when the estimations are done, like you can't say it is your model is good until you balance, you see whether they are balanced. That means that is a place where the statistics come into action, mathematical modeling process. Like you compare the predicted outcomes and observed outcomes. If they are okay, that means if the statistical tests agree with them, then you use the model for real life forecasting. If not, you refine the model. So this is the, briefly, this is the role of, this is the mathematical modeling process. Then if we classify mathematical models, there are several classifications, of course. I'm talking about two main classifications: static versus dynamic models and deterministic versus stochastic models. So static model, if a certain model does not have time-dependent component, that means any of the variables are not time-dependent, then that model is a static model. And if a model has some time-dependent component, it is a dynamic model. That is static versus dynamic. And the next classification is deterministic versus stochastic. You know, the real life is full of uncertain. As I started at the beginning, I said it might rain. So we don't know for sure. I thought it is going to rain. It might or it might not. The real life is full of uncertain. Now, this is the best period to understand the uncertainty in real life, because the few months ago, we were free to fly into any direction of the world. But now, we are like birds without wings. So we are strict to our home places, hometowns. So the uncertainty in real life. These deterministic models, they are not associated with any randomness. Conversely, stochastic models are capturing the randomness. So they are related to they are associated with probability distributions. Another name for stochastic models are statistical models. That's why I started from the mathematical modeling. Statistical model is not something totally different from the mathematical model. It is a type of mathematical model where it is a stochastical model where the randomness is captured. Actually speaking, statistics is a different the stream of the different stream, yet some refer it as mathematics of uncertainty. As true, statistics is developed on probability theory, yet it is stored like almost it is depending on the mathematical techniques. Therefore, referring statistics as mathematics of uncertainty is not wrong. So the statistical model also a type of mathematical model. The statistical models, we can basically divide into several parts. One is univariate statistical models. That means an equation or set of equations explaining the behavior of a single random variable over time. That's only the time series data, basically, I would say. Over the period of time, we are collecting the value of some variable. And multivariate statistical model, that is explaining the joint behavior of several dependent and several independent, or one dependent and several independent, but basically several independent and dependent variables. Then the regression models. It doesn't have a time dependent component explaining the behavior of one dependent variable and many independent variables. So these are the basically applied or the mostly applied statistical models in real life. So then if we look at the scientific forecasting and statistical model. Forecasting. What is forecasting? Foreseeing the future. Forecasting is simply foreseeing the future. The forecasting is begun from the beginning of the time. We would say the forecasting was begun from the beginning of the time. Like the astrology, palmistry, all these are forecasting things. And we can't say they are lies. They are wrong because they have been there for thousands of years. Then what is this scientific forecasting? If a certain forecasting is based on mathematical modeling, that is called scientific forecasting. So that's how the mathematical modeling or the statistical modeling becomes so prominent in scientific forecasting. If scientific forecasting, that is based on mathematical modeling. As I said, statistical modeling also a type of mathematical modeling. So scientific forecasting plays a vital role in research and management, almost in every field. Like we can't say this field or that field. Like almost every field, it is so prominent. Like at present, the entire world is struggling to use time series forecasting techniques to capture to forecast something about this COVID. So even in agriculture, medicine and healthcare, meteorology, engineering, biological sciences, management, and even social sciences, we are using scientific forecasting. Therefore, the role of scientific forecasting in real life is very prominent. So, well-known statistical models for real life. Some well-known models are regression models, trend models, decomposition models, ARIMA, autoregressive integrated moving average, and seasonal ARIMA, then Arch and Garch models. So they are well-known models in real life situations, and they were highly successful. So now we are statisticians. We are mathematicians, or we are statisticians. What is the role of statisticians? The role of statistical models in real life is easy to understand. Applying statistical models to capture or to solve the real world problems. It is simply to understand. So what is the role of we statisticians? We must be able to apply statistical techniques to solve real world problems. That is a basic or the primary duty of statisticians. And secondly, making people understand the importance of statistical theory and applications. So you might have seen that why I'm saying this, at present, more than mathematics, statistics is very popular. Almost like every field, everyone is trying to apply statistics and everyone is trying to do statistical forecasting. But if you see the highly reputed journal articles, the impact factor is very high, the science citation, everything is there. But according to American Statistical Association, where I am a statistical consultant, more than 50% of the published articles are wrong in the statistical analysis aspect. Like if they are doing a statistical modeling, like say regression modeling, most of the researchers, they do not test the model assumptions. Then the basics are violated. So for categorical data, they use regression analysis, not the logistic regression. So likewise, so many misinterpretations are there. Therefore, we statisticians should take actions to correct them, like as universities or even as individuals. Whenever you get a chance, you can correct them, or as universities, you can try to do them. like as the American Statistical Association, we are trying to do something in a legal framework. However, we have decided to do it at individual level as well. So there are two of the duties of we statisticians, role of statisticians. But most importantly, we must develop new techniques, forecasting techniques and theories to the real world, because if the theories are there, like they will pave the path to applications. So we must try to develop new techniques to the real life situation, apply in the real life situation. So I would like to share a bit of my experience. I was able to develop several statistical techniques to the world, the circular model, circular indicator, Sama circular model, Sama circular indicator, and so on. So like the Sama circular model, I'm going to talk about that and how it happened. I think that will be useful, especially for the research scholars or even the researchers to develop something. This happened like when I was doing my PhD. As everyone does, I was searching for a topic. I mean the research area, not the topic, research area. Then one of my friends, the finance professor of a certain university in Sri Lanka, said, Samanthi, there is a big problem in Sri Lankan share market. With the existing techniques, we can't forecast the Sri Lankan share market. We can't understand why and how it happens. So, will you be able to, you will be able to do it because you are a mathematician and a statistician. As I said earlier, my first bachelor's degree is mathematics, then first postgraduate in mathematics, and of course master degree I have statistics. So I thought, okay, I will take the challenge, and I thought of model development of forecasting Sri Lankan share market. That was my objective in PhD. Then I registered for the PhD in the rank number one university in Sri Lanka, the University of Peradeniya. And that was the way I got my BSc degree as well. So I was doing some work with some senior professors, but halfway, like after several months, we all got stuck because we realized that I am going to do something like statistical development, yet related to the share market or the stock market. So my professors or me, we were not aware of we didn't have any knowledge about the stock market. Then we thought of, okay, taking one professor from the financial market and then another professor, like my existing professor in the statistics, and we'll go ahead. So we tried it, but the problem was the finance professor was unable to understand the statistics part. Statistics professor was unable to understand the finance part. So we had no option. At one point, like by the time we were doing this and that, by the time about we have spent about 2 years. Yes, after about 2 years later, the university said, now Samanthi, this is not going to happen. We can't, they tried with every university in Sri Lanka, even overseas. So they failed. They said, we are unable to find a supervisor. So are we going to quit this? I said, no. If I start something, I'm not going to stop. That is not the way I am doing. So I thought, one of my friends said, why don't you do a master's in business administration? Like as a maths person, as a stat person, doing master's in business administration is like a Greek. But I had no other option because university was suggesting me to quit. And I thought I'm going to do it somehow or the other way. I stopped the PhD halfway. I hold it for a while. And I registered for a master's in business administration in another university in Sri Lanka. And while doing my PhD work slowly, I completed my master's in business administration. That's how I got MBA. Then only I could bridge the two fields, statistics and the financial market. Actually, it was so hard, and like it was a really, really difficult job because while I was working, I did all these things. Yet, that is the best thing happened in my life. I got stuck in between and did my MBA. That opened a wide scope for me in research. Then with that, I could understand any field easily. And finally, I ended up with a circular model. that is to forecast the Sri Lankan share market. But I realized actually when I was presenting the PhD thesis, I mean before that I did about 20 publications. Yes, I did 20 publications from my PhD study, and that is based on circular model and circular indicator. And I proved that mathematically, and using the real life data, I proved that these techniques can be applied not only to share market but also to the other fields as well. Basically, this circular model was developed to capture any irregular wave-like pattern. So the Sama circle, but the circular model has one limitation. I will tell you later. I started with Sama circular model. It is actually the improved version of the circular model. So the Sama circular model, the development was based on Newton theory of uniform circular motion, or the Newton's law, the Fourier transformation, least square regression, and differencing technique. So if we consider a motion of a particle in a horizontal circle, if a particle is moving in a horizontal circle with angular speed omega, constant angular speed, then the period of oscillation t equal 2 pi over omega. And the Fourier transformation, this is the discrete version of the Fourier transformation. Fx equal ak cos k omega t plus bk sin k omega t. This is the discrete version. So I found that, and I proved that if there is a wave, any wave, regular or irregular, like the period of oscillation, the theoretical period of oscillation is the time between two peaks or proofs of a sine or cosine function. So I proved that if a time series follows a wave, regular or irregular, with f peaks in n observations, then its period of oscillation can be given as total number of periods over total number of peaks. So I proved that. Then I modified omega as 2 pi f over n. With that, I modified the Fourier transformation this way. Yt is this one, and I included the error term as these are real life data. Then in physics, the Fourier transformation is extensively used. So they find these ak and bk. These coefficients were found by the laboratory experiments, but with real life data we can't do that. So I used the least square method to estimate ak and bk. But this is the circular model. The limitation of this one is this model was applicable only for trend-free series. So that was a real disadvantage of the model, because the real life data are with trend and other components. So I used the differencing technique and improved the model. Then the improved model, or the Sama circular model, is this. Yt equal, Yt is the value of y at present, and the d order differencing and the circular model part. So these are the model assumptions. T is a continuous random variable. T, the time is greater than or equal to 0. K is a positive real number. It need not to be an integer. It is a positive real number. Here, like you might have seen the regression, multiple regression. Though it looks like regression, it is not. Here, the sine and cosine series were obtained using this omega. Omega is calculated using the number of peaks and number of observations in the series. So then, this Sama circular model, like if you look at the significance of Sama circular model, the time series data comprises several components. They are trend, seasonal variation, cyclical variation, and irregular variations. So, like with these, they follow irregular wave-like pattern. Generally, this type of data series are common in almost every field. So the most widely applied techniques are decomposition technique. Decomposition are either additive or multiplicative model. Arima and Sarima techniques, they are the widely applied techniques to capture irregular waves. But these techniques cannot capture, they are unable to capture the cyclical variation. What is seasonal and cyclical? Seasonal variation is a wave-like variation within an year, like the period of oscillation is less than 1 year. When it comes to cyclical variation, period of oscillation is more than 12 months, more than 1 year. So the decomposition technique is unable to capture the the Arima-Sarima, only the seasonal part is capturing. A decomposition technique, of course, with the trending, deseasonalizing, and after that again have to go to the Fourier transformation. So no one is doing. The researchers assume that the cyclical variation is not appearing, but it is wrong. Cyclical variations are there. And in contrast, the Sama circular model is capable in capturing all these components of a time series. Arima-Sarima superior to decomposition techniques. Yet, many researchers have shown that another weakness in Arima-Sarima are the forecasted values do not follow the actual pattern. That's also another weakness of this one. So the Sama circular model has been applied, as I said, it is a new technique, has been applied in some fields with real life application. And in those applications, the Sama circular model was superior to decomposition as well as Arima and Sarima. Even the American Statistical Association this year, reviewing those applications, they also agreed with the fact that Sama circular model is superior to other existing techniques. So some of the applications of Sama circular model in real life, that was applied in finance, hotel and travel sector, economics, gender studies, and meteorology. Not that I did all myself, and some other researchers have done. And some of the applications are using this for tourist arrivals. Then the forecasting BSE Sensex index, the Indian stock market index, and then the forecasting Sri Lankan stock market, this consumer price index, and the unemployment of Australia and all. I will show you one example. This was Sama circular model on forecasting female unemployment of Australia. And so you can see this time series plot has some sort of trend and irregular wave-like pattern. So using the technique, to use the Sama circular model, first use the differencing technique and then apply the model. I'm not going to explain how it is done, and you all can understand it. So the best fitting Sama circular model. To do this modeling, I use MATLAB programming, because the existing software cannot be used for that unless you write the program. But you can use Minitab if you want. You can make this series and run it. However, I use MATLAB, and the best fitting Sama circular model for female unemployment of Australia is this. You can see it has some autoregressive part. That means present value depend on then say this month is last month and one before the last, and there are 3 trigonometric functions were significant. So this satisfied all model validation and verification criterion. These 3 trigonometric parts were the most important thing. When I found the periods of oscillation of them, they were 19 months, 6 months, 19 months, and 10 months respectively. That means, as I said earlier, these are the waves. These were the sine 2 omega t, cos 0.5 omega t, and cos omega t. They were the waves. So the period of oscillation of them were 6 months, 19, and 10 months. 6 months and 10 months means this female unemployment of Australia has 2 seasonal patterns and 1 cyclical pattern, where 19 months. That's what I said. Seasonal Arima is unable to capture this, even these 2. The seasonal Arima will capture 1 seasonal length, but not 2. So, but this gives more information. And similarly, I did the forecasting consumer price index of India. And found this is the best model. It also comprises 2 trigonometric parts and 1 lag thing. So that also irregular wave-like pattern. Then here also I compared this with Sarima forecasting and this one, and found that this is superior. However, Sarima also was successful in this case. And these are some other applications on tourism in Sri Lanka, total arrivals, Asian arrivals, and so on. Basically, in any field, field is not important. In any field, irregular wave-like pattern with trend can be easily captured by the summer circular model. So what I wanted to basically tell you is these are some of the references, like almost about about 20 or more papers are published by me based on circular model and summer circular model. You can see them in my Google Scholar profile or this Senido and other this DORG and all. So that means the ORCID and other places. So basically what I wanted to tell you is, like, my topic is role of statistical models in real life. It is easy to understand. We all know how important it is. What is the role of statisticians? Applying them correctly, teaching people and making people to use them correctly, and more importantly, developing new techniques. So I could do something. I'm not saying that I have done a very big thing. I did something, and I'm trying to do something more. We must learn more and more theory, because without theory we can't do any new developments. Research scholars and the researchers, even a senior professor, like, can use, especially if you are a person with a mathematics background, then you can develop new techniques. If you are a person with physics background, it is easy for you to develop new things. So with that, I have to say one thing: practice makes perfect. And determined, dedicated, and done is the motto of the Institute of Mathematics and Management. I have been a lecturer in various universities in Sri Lanka. 20 years. Later on, we started this Institute of Mathematics and Management. So this was the motto. We followed this one. We were determined and dedicated and done. So thank you very much for giving me this opportunity. And that's all. Due to time limitations, I'm not going to talk anymore.
Right. Very nice presentation, madam. And may we know this, how these models are SOMA circular model?
Yeah.
As your references, these are all very recent works you have coded. Yeah. What is the history of these models? So when did this pioneering work started?
This circular model was introduced in year 2016 and summer circular model in 2018.
18, very, very young, it seems. Very nice. Very interesting, madam. Exploring the different parameters of measuring the series related methods through SOMA circles models is, I hope that is this invention or discovery, call it as, is going to make a tremendous mark in coming future, particularly studying the time series related studies. So really very amazing talk. We have started with a very humble beginning, and you made how a very simple thought when you are converting as a knowledge product. So you made a very, very systematic way how to initiate, convert a general context as a mathematical problem and exploring the hidden parameters within that problem is a very interesting. And your proposed model, though it's a very young, it seems, it's going to make more vibrations in future. Very nice, madam. Very nice. Thank you very much for sharing this valuable talk.
Thank you.
Yes. So yeah, thank you, Dr. Samanthi, for giving a nice presentation. Actually, this wavelet and Fourier transformation have been used for quite some time in modeling, and you have combined that in the time series aspect and try to bring out your new model which captures these oscillations of these time series data. So that's a good thing. So I think the Sama there represents the first name of yours, if I am not mistaken. The Sama circular model is Samanthi.
It is part of, actually it is like this. It's a bit of history of Sri Lanka. After the independence, until that, education was limited to only some privileged class. So after independence, one good person has introduced a free education system to the country, and I am a product of the free education. So in that, the free education system of the country, the first, the textbook of the grade 1, there were two main characters. They were Sama and Amara. The female character was Sama. And so honoring the person who initiated this free education, I named that as Sama circular model, not because I am Samanthi.
Okay.
That's good. That's good. So we came to know a bit of history. History
towards your nation is highly applauded.
Yes. Correct. Yeah. So any quick questions from the audience? Anybody wants to have some sort of interaction with the speaker before we go on to the next, invite the next speaker? Is there any quick interaction?
Okay. Then thanks.
Okay. So fine, if there is no other interaction, so let us thank the speaker. Thank you, madam, for giving this nice talk, and hope that we will meet in some future conferences also organized by the department. Thank you, madam. So
I would like to take this opportunity to thank you, madam. And one more thing, we want to make some academic journey with you, and your interactions and your what we call it as collaboration with ours is very much essential. Our department is having 8 faculty members, all are working in 8 different areas, and we are very much interested to let us have our future journey with you.
Yes,
okay?
definitely. Okay.
If possible, we will have some collaboration works with our university and your university, your institute.
Yes, definitely.
Thank you.
Okay, bye.
thank you. Yeah. So thank you for that. And the next speaker for today's session is Dr. Anup Chaturvedi. He is professor in the Department of Statistics. So yeah. So Professor, are you ready with your talk so that I can just introduce you?
Yeah.
Professor Anup Chaturvedi is there?
Yeah.
Yes, sir. Thank you. So I will just give a very small intro about you, and then you can make your presentation. Yeah. Just give me a second. Just sharing my screen. Yeah. So for the second talk for today's session, I warmly welcome Dr. Anup Chaturvedi. He is a professor in Department of Statistics, University of Allahabad. So he is recently superannuated after serving the university for 38 years as senior lecturer, reader, and professor. And for some time he was the head of the department of the statistics department for about 7 years. And to his credit, he is a member of the Fellow of the Royal Statistical Society, and he has published 2 edited volumes. One is the Handbook of Applied Econometrics and Statistical Inference, published by Marshall Decker, USA, and some recent developments in statistic theory and applications by Brown Warkell Press, USA. And his research interests basically include shrinkage estimation with reference to linear models, dynamic models, panel data model, and data mining in bioinformatics, Bayesian unit root and co-integration tests, and control chart for autocorrelated data. And Professor Chaturvedi has got some sort of foreign exposure. He has visited a lot of universities, University of Paris, University of Wollongong, Australia, and then City University of Hong Kong, Tilburg University, Netherlands, and several other universities as visiting research fellow, visiting lecturer, and visiting professional fellow. And he has supervised 21 research students for PhD degree, and he has worked on 6 research projects. And he is involved in editorial and refereeing activities of various high impact journals. So with these few words, I invite Professor Chaturvedi, and his talk title for today's talk is Testing Stationarity in Gorge Process using Bayesian approach. and with an application to crude oil and petroleum product spot prices. So with these few remarks, sir, I invite you to give your presentation.
Thank you.
Thank you, sir.
So, can you see my slides?
Yes, it's visible, sir.
Okay. So I would like to thank the organizers of the conference, particularly Dr. Rao, for giving me this opportunity to interact with all of you. The title of my talk is Testing Stationarity in Dark Processes Using Bayesian Approach, an application to crude oil and petroleum products spot prices. And this is actually a joint work with one of my PhD students, Shivam Jaiswal, and another friend, Ishaq Bhatti from La Trobe University, Australia. This is the outline of my talk. First, I will introduce the unit root problem. Just briefly, I will discuss and arc and Garg models, and then Bayesian approach to arc and Garg models. Then I will discuss the main arc and Garg model and Bayesian unit root test for the model. Then I'm going to present some results on the simulation study, just to check the performance of the Bayesian unit root test for the arc and Garg model. We have conducted simulation study, and then we have also applied the proposed test to crude oil and petroleum products spot prices. So finally, there are some concluding remarks. The first section is introduction. Botts and Jenkins approach has gained a lot of popularity for modeling time series, and in Botts and Jenkins approach, we use different stochastic processes like autoregressive moving average, mixed ALMA process, or autoregressive integrated moving average process for modeling different economic time series. Now, in fact, most of the statistical softwares have built-in programs for fitting these models. You can use these models for forecasting purposes also. Now, one of the major issues with these models is the presence of non-stationarity, and this non-stationarity may be due to the presence of unit root, or it may be due to trend component. Apparently, if you plot a time series, then you may easily get confused between these two reasons, or you may not be able to conclude whether the non-stationarity is due to the presence of trend or due to the presence of unit root or a stochastic trend. But these two have different implications. Particularly if the non-stationarity is due to the presence of unit root, then you cannot apply the usual inference procedures, like usual testing procedures, t-test, f-test. These tests fail, and then you require some modifications, like Dickey-Fuller test, which we use for testing the presence of unit root. You cannot use the usual t-test, but you require a different test procedure, Dickey-Fuller test, for testing the presence of unit root. Another implication of presence of unit roots is the effect of past shocks will not dissipate, and the past shocks have some kind of long-term or permanent effect. Then there are several classical unit true tests which have been proposed in literature. Decay-Fuller test I already mentioned. They have tabulated the critical values of T ratio under unit root hypothesis. Then augmented Decay-Fuller test, which incorporates the augmentation term, and this augmentation term actually takes care of MA disturbances. Then Nelson and Plauser proposed a test for testing trend stationarity against difference stationarity. Third and Decay in 1984, they generalized the Nelson-Plauser test for MA disturbances. And then there are several other modifications also. A major problem with classical unit root tests is that these tests are usually based on asymptotic justification. These are large sample tests. And in finite samples, often these tests have low power. These tests are also more biased towards the acceptance of unit root hypothesis. So these are some major problems with the classical unit root tests. One of the alternative is to use the Bayesian approach, which is a more formal framework, which gives you a more formal framework for testing the unit root hypothesis. It is based on finite sample theory, and it is free from such problems. So in Bayesian approach, we incorporate the current sample information contained in your likelihood function with the available prior information. And then we get the posterior information, and then your decisions are based on your posterior information. In fact, the first paper which used Bayesian approach for testing the unit root hypothesis was by Singh, published in 1988. Then there are several other papers dealing with the Bayesian approach. And in Bayesian approach, your decision is based on the posterior odds ratio. On the basis of posterior odds ratio, you decide whether you are going to accept the unit root hypothesis or you are going to reject it. Now, often in time series, we observe heteroscedasticity. Not only heteroscedasticity, we observe time-varying heteroscedasticity. To capture or to model time-varying heteroscedasticity, arc and dark models have been proposed. Autoregressive conditional heteroscedastic and generalized autoregressive conditional heteroscedastic models. Dark models are commonly used in modern several econometric data set, available in financial economics or macroeconomics. Particularly when you have time-varying heteroscedasticity, then you use dark models. The foundation for dark and arc models and its different variants was first led by Eagle, and Eagle along with Clive Rengel got Nobel Prize for working on arc and dark models, Nobel Prize in economics. Then you find maximum likelihood estimators for the parameters of ALMA process with dark errors developed by Ding and Lee in 1998. When you have high persistence in volatility, you can use integrated dark models, which are just parallel to integrated ARMA process. For example, in asset returns, often you have high persistence in volatility, so you can use calc models. Then Hansen in 1995, Halvey et al., they consider non-stationarity stochastic volatility process and its different applications they have given. Cook in 2008 considered AR GALP process, and they proposed classical unit to test for testing the presence of unit root hypothesis, for testing the unit root hypothesis in AR GALP process. Then Nakatsuma in 2000, he proposed a Bayesian MCMC method to estimate ALMA GALP models. And then you can find several other papers dealing with the Bayesian approach for GALP models with normal or 20 errors. This paper by Babu and Lubrano deals with Bayesian inference of GALP models with normal and 20 errors using the Gibbs sample approach. So there are several papers. Chev in 1995, he developed a method for calculating the marginal likelihood from Gibbs sampling draws. And we are going to use this approach for obtaining the posterior oscillation in our case. Now, often in that process, you observe fat tails. And you cannot use normal distribution for modeling fat tails. The alternative is either you use student T distribution or general error distribution. Here in this work, we have developed Bayesian unit 2 test for time series model with GALP errors. And then we have considered the MCMC simulation study to evaluate the posterior oscillation. Actually, we have considered two cases. The model with the normal errors and the model with errors following T distribution. In both the cases, it is almost impossible to obtain the exact expression for the posterior oscillation for testing the unit root hypothesis. So that's why we have used MC simulation technique for evaluating the posterior oscillation. Then we have observed the performance of the Bayesian approach in cases when the unit root is present, and we also consider the boundary cases when the root is less than 1, but it is quite close to unity. Say, for example, when the root is equal to 0.98 or 0.95. So it's very, for boundary cases particularly, it is very important to distinguish between the stationary case and non-stationary case. Then finally, we have used the proposed test for 11 time series of oil prices. Okay. So we have considered a GALP process given an equation 1. This is the model we have considered, simple AR1 model. Epsilon T follows some distribution with mean 0 and variance HT. So your variance is you have heteroscedasticity, time varying heteroscedasticity, and for modeling HT, we have considered dark process. For eta t, we have assumed a general distribution day, and in fact, we have considered two different cases when this general distribution is normal and when this general distribution is t distribution. So we have considered dark process with normal and 20 errors. The unit root hypothesis is H0 phi equal to 1, and H1 is the hypothesis that phi is less than 1, so you have a stationary dark model. For normal errors, under the null hypothesis H0, the set of parameter vectors is we denoted by theta naught 1, which is mu omega alpha beta, and under the alternative hypothesis H1, the set of parameter vectors also includes phi. Under this 20 errors, we have one more parameter, which is the degree of freedom of t distribution. So this is the set of parameters under H0, and this is the set of parameters under H1. Then the likelihood function under normal errors is given in equation 2, whereas the likelihood function under 20 errors is given in equation 3. Then we have assumed normal prior for mu, beta prior for phi, uniform prior for omega, and alpha, beta also we assume follows uniform prior, and for in case of t, when errors follow t distribution, for degrees of freedom also we assume uniform prior. Now, M0I is the model under the hypothesis H0, and M1I is the model under the hypothesis H1. We are taking I equal to 1 when the errors follow normal distribution, and I equal to 2 for the 20 errors. Then pi mki is the prior probability distribution under the model mki, and pi mki given y is the posterior probability distribution under the model mki. Then the posterior odds ratio is given by equation 4. When this is actually the prior probabilities for model M0I and M1I. So this is actually the prior odds ratio, you can say. And when prior probabilities are equal, then your posterior odds ratio is equal to this quantity, which is also known as Bayes factor. To obtain these marginal likelihoods, means for calculating posterior odds ratio, you have to obtain these marginal likelihoods under the model M0I and M1I. This is the expression for the marginal likelihood. Now, remember, your likelihood function is quite complicated, and it is not possible to obtain the exact expression for the marginal likelihood function. So we have followed the approach of chip. You can express the marginal likelihood in this form. And then you can write the Bayes factor in this form, and ultimately you can simplify it into this form. And notice that this expectation is over the probability distribution P theta 1i given y and 1i, which is the posterior distribution under the model M1i. Now, to calculate this expectation, this quantity, we use the gate sample approach. So, suppose you have capital G draws from the posterior distribution. All others, once you have drawn the gate samples, the expression for the Bayes factor is given by equation 9. And when your errors follow T distribution, the expression for the Bayes factor is, you can approximate the Bayes factor by this equation, equation 10. And then we have used these expressions for obtaining the Bayes factors. In simulation study, for calculating the Bayes factor, we have used just another GIF sampler software to generate the posterior and CMC draws, and we have implemented R using RJX package. We have taken mu equal to 0, alpha equal to 0.25, beta equal to 0.65, omega is 0.1, and mu equal to 10. Of course, one can select some other values of mu, alpha, beta, and omega and mu, but mainly we are interested in the values of phi. Particularly the values of phi which are close to 1 and phi equal to 1. Then we have taken phi equal to 1, 0.98 and 0.95, t equal to 250, 500, 750 and 1000. But here we have presented results just for phi equal to 1 and 0.98 and t equal to 500 and 1000. Then we have generated 100 independent samples for both the models, normal as well as for 20 others. Then each sample is simulated 800 CMC draws. We have discarded the first 3000 CMC draws as burn in length, and we have used trace plots to check the convergence and determine burn in length. So ultimately we have 5000 MCMC draws after discarding 3000 initial samples. Then these are the other prior parameters which we have taken. Then these are the results. So for t equal to 500, phi equal to 1000, t equal to 1000, phi equal to 1, phi equal to 1, t equal to 500, phi equal to 0.98, t equal to 1000, phi equal to 0.98. From these estimated values, you observe that these estimated values are quite close to the actual parameter values, and the standard errors are also quite low. Again, as the sample size increases, these standard errors further decrease. Similarly, these are the credible intervals. Again, when you increase the sample size from 500 to 1000, you observe that the width of the credible interval further decreases. Similarly, for phi equal to 0.98, these are the estimated values, and These are estimated values, and these are the standard errors, credible intervals. Then similar kind of results we have for the GARC process with its 20 errors. Here you have one more parameters which is new. This last parameter is actually new, estimate of new. Again, you observe that the estimated values are quite close to the initial parameters which we have selected. Standard errors are also very low. As you increase the sample size, the standard errors further decrease, and similarly for the credible intervals, the width of the credible intervals decrease when we increase the sample size. Now, when we apply the unit root test, then we have tabulated the proportion of correct decisions for the GARC process when the errors follow normal distribution and when the errors follow S20 distribution. Sample sizes, and then we have considered the cases when phi is equal to 1, 0.98 and 0.95. And these are the proportion of correct decisions. So, particularly, say for phi equal to 1 and t equal to 250, for the almost 83% cases, you have correct decision. Even for the value of phi equal to 0.98, which is quite close to 1, for t equal to 250, in 72% cases, you have correct decision. Correct decision means your unit root hypothesis is rejected. And once you increase the sample size, this proportion increases to 1. Say for t equal to 1000, it is 1. So 100% cases. So you are clearly able to distinguish between the stationary case and non-stationary case. Similarly, for the 20 errors, even for the phi equal to 0.98, if you take t equal to 1000, then for 97% cases, you are able to reject the unit root hypothesis. For phi equal to 1, t equal to 1000, for 91% cases, you are able to accept the unit root hypothesis. Your decision is correct. So here this test procedure is quite powerful in this sense. And we have applied this Bayesian unit root test for the 11 times these of spot prices of crude oil and petroleum products in dollars per barrel. We have these 11 time series. The data we have taken from US Energy Information Administration database. And for each time series, we have 895 observations. So we have analyzed all these 11 time series. First, we have plotted all the 11 time series, but here I am showing the graph of just 2 time series. And you observe that these graphs show nonlinearity and heteroscedasticity. And then first, we have tested the unit root hypothesis, and we observe that only one time series does not have unit root hypothesis. And for all other 10 time series, for all other 10 spot prices time series, The unit root hypothesis is accepted. So those time series show non-stationary behavior. Then we also check whether the errors follow a student t distribution or normal errors using the base factor. So we observe that these 4 time series favored Garg process with student t errors over the Garg processes with normal errors. You can use normal errors. These are the estimated values of parameters. Particularly for phi, you observe that values of phi are quite close to 1, but still you are able to reject the unit root hypothesis. For many of these time series. These are the estimate of parameters when errors follow t distribution. Then we have calculated the log of base factor. On the basis of log base factor, we have taken the decision. These are the final concluding remarks. Our simulation results show that the estimates of parameters are close to the true parameter values. We have used Bayesian approach for estimating the parameters as well as for testing the unit root hypothesis. And for both purposes, our procedure works well. Bayesian unit root test correctly identifies the stationary process even if the parameter is close to but less than unity. And then we have applied the results to stock prices of crude oil and petroleum products, and we observe that the Bayesian estimation and unit root test results substantiate each other. In the sense that the time series for which unit root hypothesis is rejected, the estimated value of phi is also less than 1. So these two results substantiate each other. Very much.
Yeah. Thank you, Professor, for the very detailed presentation on this cost process and the use of Bayesian approach there. So it is a very nice talk application in crude oil prices. So any quick questions for professors, maybe 1 or 2? I think there is one hand raised by Naseem. Yes, madam. You can just unmute and talk.
Madam, can you adjust your camera so that we are...
Yeah. Please unmute yourself.
So madam has some problem in the previous session also.
Okay.
We can ask her to type in the chat box better so that it can be.
And there is one question that has come. I will read, sir. How to determine prior hyperparameters in this case?
Pardon?
How to determine prior hyperparameters in this case? That was one question by Ricky.
Yeah, that's the problem. Is usually we say that you take the hyperparameters based on your prior information, but if you don't have any much prior information, then you try to select the values of hyperparameters such that your prior information is either non-informative or it is quite close to non-informative prior. So in fact, we have selected non-informative priors, means uniform one, or even for normal prior, we have taken the prior values to be large so that it is quite close to the uniform distribution. So we have taken, you can say, the priors which are very close to the non-informative priors.
Okay. That's good, and thank you. Yes. So, any other interaction with the speaker? I think there is one more chat. Maybe I will see. Thank you. Yeah. And so, yeah. So there are no questions. Thank you very much, Professor, for sharing your thoughts and time and accepting our invitation on this conference. So we are very thankful to you. Thank you, sir. Thank you.
Okay, thank you.
Okay, so I take this opportunity to invite the next speaker for today's session, Professor Anagal. Sir, are you there? Yeah, Professor is there. I'm able to see. Yeah, welcome, sir.
I just opened it.
Yeah. So I just introduced Professor Anagal. Yes,
Welcome, Dr. Anagal and Dr. Adivai and all the people on the board. Please make it safe.
Yes. So, yeah, I'm just sharing my screen for Professor Anagal. Is it visible?
Can you see it?
Yes. So,
can you see the presentation?
No, I am just presenting, sir. After my introductory remarks about you, you can start your screen sharing.
Can you see the screen now?
No.
Anagal sir.
Yes.
There will be some instruction to you, then only you can
Okay.
Yeah, you can just stop sharing in that case.
Okay.
So, yeah. So, I take this opportunity to welcome Professor David Hanagal. Actually, he is a regular visitor to our department in all the conferences that most of the conferences that we organize. Professor will be a part of it, either as an advisory member or as an invited speaker, or sometimes even as a thematic speaker, thematic lecture series. So it has been a quite good time that we usually spend with Professor Anagal during our offline conference, but this time this is going to be online, so we have to meet him virtually. So welcome, sir, for this invited presentation. So I just share some introductory remarks about Professor Hanagal. Professor Hanagal recently got retired from the Department of Statistics, Savitribai Phule, Pune University. He was there for quite long time in the department, and he has guided and seen the growth of the department to its present thing. So, to his credit, he has this profile. Anyhow, his profile, he may be in 1 or 2 pages, but actually it's very big. So he has been an editor of various journals. You can see Interstat Journal, American Journal of Biostatistics, International Journal of Agricultural Statistical Sciences, and he is associate editor of the Journal of Indian Society for Statistics and Probability and Journal of Indian Statistical Association, actually published by Pune University. And he has been the editorial member of popular peer-reviewed journals in statistics, statistical papers, Journal of Applied and Computational Mathematics, International Journal of Environmental Sciences, Journal of Statistics and Reliability Engineering, Advances in Reliability, etc. And to his credit, he has written 3 books on Introduction to Applied Statistics, a non-calculus based approach, published by Narosa, and Modeling Survival Data using Frailty Models, which is quite popular among the reliability researchers, and Modeling Survival Data using this Frailty model. So these 2 books are quite popular. One is by Springer, and he has guided 9 PhD students and has published more than 130 research papers in well-known international journals, and he has presented more than 50 national and talks in national and international conferences. And he has been has worked as visiting professor at Michigan State University between 2006 to 2007, and he worked as visiting professor at Mexico during 1996 to 1998. And apart from that, he has got industrial exposure. He worked as a senior biostatistician or scientist at Henry Schein University during this period of January 2002 to December 2008 and 2003 to 2004. And he has been a governing council member of the Indian Statistical Association. And more than that, Government of India has recognized him because of its talent and academic caliber. He has been in the role of the assessor of this National Assessment and Accreditation Council, and he has been the UGC chairperson of statistics for drafting this learning outcome-based curriculum framework. So which has come out even for undergraduate and postgraduate students, and he is a subject expert for UGC for Special Assistant Program Screening Committee. He was there, and selection of major and minor research projects. So he was one of the selection committee members and subject expert for the selection of UGC postdoctoral fellowship and UGC Special Assistance Program for Karnataka University, Dharwad, and Banaras Hindu University. He was one among the advisory committee members, and he has been a board of studies members for reputed universities, KUSAT, Cochin, and Yeshwantrao Maheta University, and yes, to our university also, Pondicherry University. He had been board of studies member for 3 years, and he was the convener of this Kamath Award for Best PhD Thesis from ISPS. He is an executive council member of ISPS during the years 2013 to 16. He has been a treasurer of Indian Statistical Association from 2003 to 2014 and governing council member of Indian Statistical Association from 2003 till date. And a dynamic statistician with over 40 years of rich academic and research-oriented experience in national as well as international environment, not only theoretically in application as well as in terms of using statistical packages. As you can see here, he is good in SAS, S+, or SPSS, MATLAB, Minitab. So basically a combination of theoretical as well as applied statistics, and his research interests include inference in bivariate and multivariate exponential distribution. He has done quite a lot of good works on this, and then selection of better component in two-component systems, stress strength models in reliability theory, and on distributions it is multivariate Pareto and Weibull distributions and characterizations, and non-parametric inference, and test for bivariate and multivariate exponentiality against positive aging, survival analysis frailty model. So to name a few, these are his research, and his recent research include, as you can see, censoring schemes, Bayesian inference for bivariate survival data, bootstrapping, and then MCMC algorithm and software reliability model. So, yeah, at a personal level, I do know him that he works extensively on this bivariate and multivariate exponential type distributions, and his contributions there are very immense. So with these very few words, sir, I deem it a privilege to invite you to give your presentation, and Professor is going to talk on positive stable shared frailty models based on additive hazards. So that is the topic. So over to you, Professor. Please unmute yourself, sir. You're not audible. Please unmute, sir. You are not audible.
Okay.
Yeah.
Sounds okay?
Yeah.
Yeah, thank you very much for the nice introduction, Dr. Vaidyanathan. Also thank Professor Tirupati Rao for inviting me for this conference and share my ideas during the conference. And I'm very happy to be here in this conference and share my ideas. And the main thing is this priority models. Okay, this is the most emerging field nowadays. A lot of work is going on. I have a book on this priority models also. The second edition has come in the last year. It's Springer.
Oh.
I'm giving some more additional work. It's not there in that book. Some more additional work what recently has been done in this priority model. Usually, the priority model. I think. Can you see the screen?
No. Please share your presentation.
Share the. Okay, 1 minute. Present now. I have to go to window or what is that?
Yeah, window. But before that, you open your PPT or PDF.
Okay, when I present now,
yeah,
it's showing a window and an entire screen.
Yeah, you can use a window.
Window, okay.
Yeah, in that you can click your PDF or PPT and start sharing.
Okay, start sharing. Okay. Can you see it now?
It will take time. It's not come. Yeah, yes, sir.
That is okay.
Yeah.
Can I make enlarge?
Yes.
Okay, control L. Okay, it is now visible.
Yes, it is visible.
Okay, this is actually based on the additive hazard. The more popular is the multiplicative model. Okay, multiplicative model are more, there is a lot of literature on the multiplicative model, and very few material is available on the additive hazard. I already have some papers on different distributions for the additive hazard model. One is the gamma, another is the inverse Gaussian model. This is the third one, positive stable shared priority model based on the additive hazard. Let us go to the outline of the talk. I am giving some description of Sarava analysis, shared priority models, what is positive stable shared priority model. There are some baseline models I have used. Two models. One is log logistic, generalized log logistic. Another is generalized Weibel distribution. This is completely parametric approach. Okay? And I'm using the Bayesian estimation. One can also do the classical MLEs and other things, but there is some problem with the classical estimates. The main problem is the convergence of the iterative procedures in the Newton-Raphson procedure. I also did some simulation work, and after that, I use the kidney infection data to model this data, to model the our proposed model using this kidney infection data. I give some tables and graphs, estimation, and other things. And which one is a better model? I have proposed some models, and among that, which one is better? That we can see. This is the outline. Now, what is surveillance? Time to event data. There are so many event data in the real life. This is the incomplete data because we can't get all the observations in the failure data. Sometimes there is a lack of time or lack of money involved, the cost is involved, several things are involved, we can't able to produce entire data. Some data is left out. That means we have to use some censoring scheme. There are different types of censoring schemes, left censoring, right censoring, random censoring, interval censoring, current status data. Several things are there. Mainly I'm using the right sensor data. That is random censoring. This is about the censoring in the Sarava analysis. Now I'm just going to review the basic concepts of the Cox model. Cox 1972 assumed the model as a hazard model, xt given x. X is an explanatory variable, h0 is a baseline hazard, and beta is a regression coefficient. This is a very most people have used this model for the Sarava analysis. When it is usually used for non-parametric as well as parametric, both are possible. When H0 is non-parametric, one can also have non-parametric model. When H0 is known, some known distribution, then it can use the parametric model. Now, the basic assumption in this model is they use the homogeneity of the subject population, which is somewhat questionable. See what happens in the patients, for example, if you take, for example, patients in the hospital. Most of the patients, what you observe is the genetic factor that differ from person to person. And also environmental factors are also different. Each patient is not identical. They have their own biological structure. They have their different types of diseases. Somebody may be having diabetic, somebody may be having asthma, they are all together and come in the hospital and they go for the treatment, for example. Okay? And in this case, there is a heterogeneity involved because different types of people are there, patients are there, and different institutes are there, or hospital centers. They also differ. The heterogeneity will differ from one hospital center to another hospital center, and one family to another family, like that. That is the heterogeneity involved. That we have to take into account in the priority models. This is a heterogeneity is known as a priority. That we have to take into account in the Cox model. Okay. Now, what is shared priority model? The shared priority is the heterogeneity is shared by all the individuals in the group or all the patients in the sample. That is a shared priority model because they experience the same type of risk, okay, in that group. Suppose if the patients are in the same family, all the individuals have the same risk because the genetic factor is almost same, slightly different, but most of the genetic factors are same. If you consider the hospital center, the doctors, nurses, staff, the lab, operation theater, everything is same. They share the common risk. Those patients who are treated in the same hospital, they share the common risk. That is called shared priority, or the heterogeneity is shared by all the individuals or all the patients in the hospital centers. That is a shared one. Now, high priority we have to introduce. See, there are several reasons. One is there are too many covariates to consider. So many covariates, we don't know which one to consider. Suppose there are 50 covariates. You can't take all 50 covariates in the model. Then what to choose? Okay. In that case, we neglect some necessary important covariates when we choose. Lack of appropriate tools to measure the covariates. There are so many covariates, you can't measure it. There are no appropriate tools to measure. Sometimes it may be very costly to measure the factors. Researchers are not aware of the influence of the potential covariates that might exist. That is the existence of, for example, existence of genetic risk factor. That means the researcher, they may not be knowing which covariate, which factor is more influence on the response variable. That is not available several times. Then they just select some covariates. Because very huge covariates are there, huge factors are there. Then they select some certain. Not all necessary covariates are included in the model, which modify the distribution of the survival time and makes the model parameter biased. That makes the assumption of homogeneity unrealistic. Therefore, we need to introduce some random variable that accounts for the neglected covariates. We call this hidden heterogeneity or priority. That is a name called priority or hidden heterogeneity, characterizing the survival changes due to individual variation, which is apparently the priority. The priority is unobserved random proportionality factor that modifies the hazard function of an individual or related individual. We are just modifying the Cox model and introduce the heterogeneity in that. That is the thing. Clayton was the first one to introduce this heterogeneity And he was not mentioning the variety. He used this in some application of chronic disease incidences. The term variety was introduced by Wappel in 1979 in the univariate Sorrel models. A variety model is an extension of Cox model, Cox proportional hazard model. In addition to the observed regressors, a variety model also accounts the presence of latent multiplicative effect on the hazard function. Now, this effect or variety is not directly estimated from the data, but instead is assumed to have unit mean and finite variance, which is also to be estimated. The shared variety model is due to some genetic factor or environment that I already told you earlier, which are unobserved in an individual and are common and shared by both pairs organs in human or twins in a family. This shared variety mode parameter is also responsible for dependence between two components. Now, what happens if we ignore the variety? We know it is significant in the model and is ignored. Then the model will be inappropriate. Then whatever decision we take will be misleading. If the variety is ignored, the estimates of the regression coefficients will underestimate or overestimate. The AIC, BIC, these are the model selection criteria, will be more compared to the model with variety. This will increase AIC, BIC, DIC, that will increase. Actually, we have to consider the model with the lowest AIC, BIC, DIC. When you ignore, then it will naturally increase. The decision based on the model without variety will go wrong. We do the analysis, but results, the conclusions will be wrong. One can have the model based on the Cox model given by Cox in 1972, okay? Without ignoring the variety. But the model will be inappropriate and it is a misleading and it will not be appropriate and model will not be good. Ignoring the variety effect with finite mean may result in negative bias in the estimated time dependence. In general terms, we let heterogeneity go into error term. This will of course lead to an increase in the variability of the response as compared to the case when variety is included. Now, multiplicative model is very well known. It is in the latest, several authors have used, and the additive model was not well known. Very few literature is there. I also have some papers earlier in the additive hazard model. The unobserved covariates U. If the variety affect additively on the hazard function. In such situation, if univariate variety model is derived as below. Let the continuous random variable T be a lifetime of an individual. Allen in 1990 and 1989, 80 and 89 proposed additive hazard in which covariates act additively on the baseline hazard and is given by equation number T. One can also have another way of writing additive hazard in equation 3. What I did here is I took e raised to x prime beta. In the equation 2, x prime beta that is added directly, and here it is taken e raised to. This is just mathematical convenience because x prime beta that takes the value minus infinity to plus infinity. If I take e raised to, then it will be 0 to infinity. I want to make this factor from 0 to infinity for mathematical convenience. Okay, and I am now in the equation 4. I am adding the unobserved covariate U. X is the known covariate, observed covariate, and U is unobserved covariate. Beta and beta U are the corresponding regression parameters. Now I can write the e raised to U beta U as Z. That is written here, Z. Okay. and Z is between 0 to 1. Okay, that is because of exponent term. Now cumulative hazard can be written, just integrate over this hazard, you get cumulative hazard function. Now one can have survival function given the variety. You know the relation between cumulative hazard and survival function. Use that relation, you get survival function. That is written in this form. Okay, that is the thing. Now integrate over the range of the variety variable Z, having the density function of Z. We get the marginal function. Just integrate over Z, you get unconditional survival function. Because earlier Z was known, now Z is integrated down. You get this term, and this will be S0 T into LZ T e raised to x prime beta. LZ is the Laplace transform of the distribution of Z, that is the variety variable. S0 T is the baseline survival function of T. Now you can write ST in terms of this, okay, after introducing the variety term. If variety is absent, then it will be just S0 T. This LZ T will disappear when there is no variety. Now, take two components in the system, or paired organs or veins or whatever, the paired organ, kidneys or lungs, all other things, okay, in the human body. Under the assumption of bivariate survival condition for a given variety Zi is given by this one. Zi is shared between both T1 and T2, both components. You can have product of two survival because Z is given here, Z is known, that's why you can write product of the two. Okay? If it is not given, then you can't write like that, product of the two. Now you can write this way, that is after substituting the cumulative hazard. Now I am taking eta j is e raised to x prime beta. That is a covariant term. Eta is having covariant terms. Okay. Now this is a conditional. Now I am integrating over Z. Integrate over Z. Now after integrating over Z, you know the density of Z. We have to assume some distribution for Z here. And this is a Laplace transform. One can have this. This is a S0 T baseline survival function that you have seen in the earlier equation. That is here. S0 T. That is here. S0 T and this. Okay, that is here. And this is the LZ. Okay. This is a Laplace transform. Now, here T1 and T2 are dependent because we are integrated over Z. Z is sharing between both T1 and T2. Therefore, now T1 and T2 are dependent now after the integration. Now it will be bivariate survival function. There are so many shared variety models: gamma, inverse Gaussian, positive stable for variance, compound Poisson, compound negative binomial, piecewise gamma, correlated variety, additive variety. Several models are there. We already discussed some in some of my earlier papers, gamma, inverse Gaussian, positive stable, and other things. In the multiplicative as well as additive models. We are going to do on the positive stable and using the additive as our model. Now, what is positive stable model? Okay. This model is of special interest for two reasons. One is, first, it is similar to gamma variety model. The simple form of Laplace transform allows simple maximum likelihood estimation in the parametric model. Second, there exist no moments in this distribution. It's a stable distribution, but therefore the moments don't exist because the PDF cannot be defined in the on the real line. That is the problem. This was the reason why Haugaard introduced distribution in the shear finity approach. Because of the infinite mean, the univariate positive finity model is not identifiable. This makes sense because in shear finity models, the finity parameter is interpreted as an association parameter that should be identifiable from the univariate observation. That should not be identifiable from the univariate distributions. In practice, gamma finity expression may not fit well. These authors are the authors. A positive stable model is useful alternative in the part because it has attractive feature that predictive hazard ratio decreases to 1 over time. This property is observed in familial association of cases of onset diseases with heterogeneity and genetic cases. That is the reason why we are using positive stable finity model. This is the reason behind it. So this is the density, okay, and this is the density. We can't write it in the write this PDF on the real line because of, see here, this is the term containing some imaginary terms. Laplace form, there is no problem. You can have closed form expression. And in order to solve non-identity problem, that will be done by restricting the parameters this way. Because the earlier model with 2 parameter having some problem with identity problem, and that we can do it by restricting this problem. This non-identity problem will be solved when you take this restriction. Now, with this restriction, the Laplace transform is this one. Okay. Now take the bivariate distribution survival function, that is this one, given this, and given Z, that is this one. This we have already shown it. Now we are going to integrate this with respect to Z, taking Z as a positive stable. Now earlier we gave the expression for this. Now I am introducing Z as positive stable. Now that will be reduced as this one. After taking Z as a positive stable, this will be this expression. Yeah. This whole thing is raised to theta. Okay. Now T1, T2 are dependent here. Okay. When the finite variable is degenerate, and theta equal to 1, then it will become degenerate. The distribution will be degenerate in that case. Then in that case, this is a here in this case, in this equation, T1, T2 are independent because there is no theta involved here. That is the reason. Now I am taking some baseline distributions. Generalized log logistic. It's a logistic survival function. Okay, non-log logistic survival function. I am just making this as generalized by taking Lyman family, taking this raised to alpha. This is called Lyman family. Okay, this was given by Deshpande and Purohit in 2005, and gamma. Okay, that will come later. Now, this is a distribution function for the generalized logistic, introducing a new parameter alpha. Now it is 3 parameter. The cumulative hazard rate is this one. When gamma is less than 1, it is a decreasing. When gamma is greater than 1, it is okay. When both these parameters are equal to 1, it is exponential. When alpha equal to 1, it's a Weeble. And there are different possibilities of that. Okay, now substitute the values, all cumulative hazard functions of generalized logistic and generalized Weeble, okay, in these equations. This is for the priority model with the generalized logistic, and this is the without priority. This equation is for bivariate survival function with generalized Weeble as a baseline. And the next equation number 10 is, this is for the using the baseline as generalized Weeble without priority. There is no theta here, there is a theta involved. Now there are 4 models in all, okay, with the 2 baseline, with priority and without priority. In all there are 4 models. Okay, I am just taking model 1, 2, 3, 4, 4 models. 1 and 2 are with the baseline as log logistic with priority and without priority. 3 and 4 are baseline used is generalized Weeble with and without priority. Now I am using the Bayesian estimation. I already told you the reason behind the Bayesian estimation. There is a problem with classical estimates because of the convergence problem. There is a problem. Estimations won't converge in the Newton-Raphson process. Then we go for the Bayesian estimation. Now I consider the bivariate censoring. Okay, there are 4 reasons actually. The first reason is both you can observe in the component 1, okay, and component 2. Both are observed. Okay? And in the second case, component 1, that is failure is observed, and the component 2, the lifetime is censored. In the third one, the first component lifetime is censored, the second component lifetime is observed. The fourth reason is both lifetimes are censored, T1 and T2. You can write the likelihood in 4 parts based on these 4 reasons, like this. Equation 11. N1, N2, N3, N4 are the numbers of individuals for which first and second failures T1, T2 lie in the range. These are the 4 ranges. 1, 2, 3, 4. Okay, one can have F1, F2, F3 using these formulas. F1, F2, that is here. F1, F2, F3, F4. This is with respect to both T1, T2. Derivative of S, survival function with respect to both T1, T2. That means both T1, T2 are observed. And only the first failure is observed, only take derivative with respect to T1. And the second component is observed, failure of that, derivative of S with respect to only T2. And this is survival function. There is no need of derivative. You take only the survival because they are censored, both T1 and T2. Okay. I'm taking some data, kidney infection data. This is used by several authors for the survival analysis. In all, there are 38 kidney patients, okay, using portable dialysis equipment. For each patient, first and second recurrence times in days of infection from time of insertion of catheter until it has to be removed owing to infection is recorded. Catheter may have to be removed for reason other than kidney infection, and this regard as censoring. So, survival time for patient may be first or second infection time or censoring time. After the occurrence of the after the occurrence or censoring of the first infection, sufficient 10 weeks interval time was allowed for the infection to be cured before the second time the catheter was inserted. So the first and second recurrence of T1, T2, that is response. The covariates, the risk factors are age, sex, disease type, GM, AM, decade. In all, there are 5 covariates. Age, that is a continuous variable, and sex is a male and female, and 3 disease types, presence and absence. Okay, that is a categorical variable. In all, there are 5. I can denote it as X1, X2, X3, X4, and X5. Okay, you can write it in this form, model. This is our model with 5 covariates. Hazarded model with variety as Z, having process table. I am giving summary of tables and graphs now. Before going to the kidney infection data, we did some simulation studies for only the variety models. That is model 1 and model 3. That is based on the varieties model. That is a positive table. And the parameter values, the true values are there. What do you consider as a parameter here to the estimates and the true values of the parameters. They are very close. You can see here the values 5 and 4.9 and 5 here 4.9. They are very close here. The standard errors, the lower credible intervals, upper credible, that is 95%, lower and upper credible limits, the GAVQ values, the P values, okay, for this, they are very close to 0.5, and GLMM values are there. We are using the GLMM test for this. Okay, these are the values for all, and this simulation is used for the performance. We have to check the performance of the estimates, how far they perform. And if they perform very well, then we can see from this the standard error and the estimates and the GAVK test and all other things. Similarly, for the model 3, the positive stable model, this is model 3 is for baseline generalized Weibel distribution. We just take the true values and estimates. They are very close to true values. Estimates. That means the performance of the estimates are good. The standard error, lower credible intervals, upper credible interval limit, GAVK P values, and good. This one. Now we take the data, the case statistics. Okay. I have taken the positive stable variety model 1 and 3. Other 2 models are without variety. Okay, I'm taking the only variety models with positive stable. They are high. That means they are in a good agreement with the model, and one can go for the model taking positive stable as a variety and other 2 baseline models as generalized Weibel and generalized normalized estimate. We can go ahead with this baseline models. One can also have non-parametric without assuming any baseline, and that is also possible. I have not taken in this presentation. Now go for the model 1 kidney infection data with positive stable variety and taking based on the additive hazard and baseline as generalized log logistic. And these are the parameters. Theta is the dependence variety parameter, that is 0.6 to high, standard error lower, and other things. What we see here, the regression, when you see the regression coefficients, beta 1, beta 2, beta 5 covariates, the lower and upper credible limits. The beta 2, the lower and upper credible limits, both are negative, and beta 5 both are negative. And the other, theta is also, both are positive. That is also significant. Beta 2 is significant, beta 5 is significant. See, in all other things except these three, beta 1 and 3 and 4, these are non-significant. How to check non-significant and significant? See, when you take the parameters, when 0 is included in the lower and upper limits, then it is a non-significance. When both are positive or both are negative, then it is significant. 0 is not included. Okay? There is a negative effect here in beta 2, and here in beta 5 negative effect. What is beta 2? Beta 2 is the gender effect, male and female. That means the females have lower risk of infection, infection, as compared to male counterparts. That is the meaning, beta 2. They have lower infection. Beta, that is also significant, you can see. Okay, that is also significant. 0 is not included, okay, in the lower and upper. This is also significant. That means priority effect is there. There is a priority effect in the model. That means we can't ignore priority. That is the meaning. The beta 5 also significant. Okay, in the absence of disease type having lower risk. If there is a disease, there is a disease type 3, then it is a higher risk. That is the meaning. Now go to the model 2. This is without priority model. What we can see here is beta 1 is beta 1, beta 2. Okay. These two are having significant A's and this one. Okay. Beta 2. Beta 2 is same as earlier also it was there. That's a significant. The additional one is beta 1, A's effect. That means lower group of age group, they don't have much lower infection as compared to higher age group. That is the main. Go to the third model. Beta 2 is having the significant effect and beta 5. That means model 1, model 3, they have the same type of significant effect for beta 2 and beta 5. Okay? The model 1 and model 3 was priority models. Model 4 and model 4 is similar to model 2, okay, without priority. Now in all the 4 models, we saw beta 2, the gender effect. The females have lower risk kidney infection as compared to lower risk of infection as compared to male counterparts. Now we have seen all the 4 models. Out of these 4 models, which one is better? For that we have to take the compare AIC, BIC, DIC for all the models, 4 models. Okay, which one having the least value? That is a better one, best model as compared to other models. Now when you see here 628, 622, that means model 3 is having least. Out of these 4 models, model 3, that is positive stable model with baseline, generalized Weibull as is having least AIC, BIC, DIC as compared to other 4 models. Okay. That is a better, best model as compared to these. And I have also compared with gamma priority and inverse Gaussian. This was proposed in my earlier papers, gamma priority. It's not included in this earlier paper, but I am comparing with this positive stable with my earlier papers, gamma priority and inverse Gaussian. There also, what we can see, they are higher here. Okay, but our positive stable priority model 3 is lower as compared to the earlier models, what we suggested earlier. That means it is best among all these models for predicting the kidney infection data. That is the thing. Now the base factor I have taken. In the base factor also, one can see the model 3 against other models is very high. Base factor is very high. Model 3 against other factors. Here also it's high. Model 3 versus model 1, model 3 versus model 2, model 3 versus model 4. Other three models, 3 model with other 3, it is high. That means this is best among other 3 models. That is an interpretation. Base factor. Now I am comparing the AIC-BIC models with positive stable variety models. This is the model, our 4 model. Model 1 and 3 with earlier models in our paper. I am taking the additive model versus multiplicative model. In the earlier table, I have taken AIC-BIC comparison with only additive versus additive. Now I am taking comparison of additive versus multiplicative model. These multiplicative models were done earlier in our papers. Here also, the additive model works better as compared to multiplicative model in all the cases. That means whatever we proposed, the recent one, the positive stable, is better than earlier models. That is it. This is only with respect to the data of kidney infection data. When you change the data, maybe some other model may be better in that case. Now this is the graphical method for this. The non-parametrics or this parametric model. That means the model fit, whatever models we have proposed, they fit better when you see these graphs. That is I think this, I will close my talk. Thank you very much for silent listening, and thank you, Professor Tirupati Rao, for giving me an opportunity to share my ideas, and I am very pleased to be here in this conference, and very nice opportunity for me to see other talks during the conference. Thank you very much. Thank you, one and all.
Thank you. Thank you, sir, for your nice presentation on these frailty models. Usually when we think about frailty models, usually this gamma frailty model immediately comes to the mind. But in your talk, you have highlighted about this additive frailty model and its better performance when compared with other baseline models. So it was very interesting. So we are very happy to listen to you in this particular conference. Thank you, Professor. Thank you.
Thank you, Professor Anand, for your sharing valuable work and your continuous support on us. Really wonderful. We need your blessings in future also, sir.
Yeah, it's my pleasure. It's my pleasure to be here.
Thank you, sir.
Thank you.
Yeah. Sir, you can just stop your presentation so that.
Okay.
Yeah. You can stop presentation.
Okay, I'll just stop.
Sir, due to the paucity of time and we are running behind the schedule, you please go to the next speaker, sir.
Yes.
All audience are requested to make a personal way of email or something like that if you have any discussion. Time constraint due to that, please forgive us.
Correct. So I invite our next speaker for today's presentation is Professor Parameshwar Pandit. So Professor, I think you are there.
Yeah, I'm there.
Yeah. Good. Yeah. So I just present a very brief bio about Professor Parameshwar Pandit. Actually, he is also new to our department. He has been to our department he has been a regular visitor to our department during this past decade. So, and he has helped us actually in our paper valuations, in our PhD viva votes, correcting this thesis, as well as whenever we need any help, he is there always to help to the department. So we welcome you, sir, to this conference, and a very brief bio about Professor Parameshwar Pandit. Currently, he is the professor and chairman of the Department of Statistics, Bangalore University, and he has got around 31 years of teaching experience and 26 years of research experience, and he has successfully guided 8 PhD scholars, and one PhD student is working presently. And his area of interest, actually, so he has around 30 totally 82 publications, out of which 52 are international and 30 national publications, and he has completed 5 UGC projects, and he has presented around 65 talks in national and international conferences, and the research interest include basically I know him as a person of reliability and inference, but I happen to see here is he works on non-parametric inference, distribution free test, parametric inference, and goodness of fit tests also, and he is a member of various professional bodies. So he has been other outside experience, administrative experience. He has been a member technical and administrative committee of Bangalore University, Board of Studies, Bangalore Central University, and chairman Board of Studies, Bangalore University. So with these few words, sir, I welcome you to give your talk on reliability estimation in strength model for some specific distribution. So yeah, so and I request you to just make your presentation within the allotted time. Yeah, thank you, sir. I just stop presenting.
Sir, I request Professor Pandit sir to. There are 3 more speakers to go, including, and time is also we are running behind the schedule. Please.
So can I take about 20 minutes?
Yes.
Okay, sir.
Yes.
Yeah, I mean, if I know in advance, I can scale my talk in that way. That's why I'm asking you. Can I?
No, 20 minutes is okay.
25 minutes, right?
Yeah.
So. How?
So first you open your the PPT or PDF.
Yeah, I already opened it.
Yeah, then go for the this Google
Present
Meet.
now. Present
now. You can have present now. You can see.
Just a minute. Okay.
You can press the present now.
Okay.
Yeah, window. Yeah, there are 3 options there. One will be a window.
Window, yeah, fine.
Yeah, you can click on that, and then you click on the PPT.
Yeah, can you see my presentation?
Yeah.
Is it visible?
Yeah. Yes.
Okay.
Yeah, yes.
So as I thank Dr. Vaidyanathan for nice words about me. I take this opportunity to thank the organizers of this conference, virtual conference, in particularly Professor Tirupati Rao for giving me this opportunity. So I straight away go to the before that. See, I worked basically in non-parametric inference, and I switched over to reliability recently. This is for your kind information. My title of the talk is Reliability Estimation in Stress Strength Model for some specific distributions. When I say some specific distributions, I think in this talk I would be able to consider only 2 or 3 distributions, particularly inverse chain, generalized Pareto, and bivariate generalized Rayleigh, inverse Rayleigh distribution. And my plan of the talk is as follows. I am going to give you a brief introduction about the problem of estimation in reliability, of estimation of reliability, particularly in stress strength setup, and I give you brief literature survey of it, and then I consider the estimation of stress strength reliability when stress and strength variables follow inverse chain distribution for a single component system, and also for multi-component system, particularly parallel and series systems. I will be giving you, I will be presenting the maximum likelihood estimators of reliability under simple random sampling setup. Under ranked set sampling setup, I will be considering Bayes estimators for reliability. Similarly, I will be doing MLEs and Bayes in the multi-component setup. So next, I consider generalized Pareto distribution. In that also, I will be talking about maximum likelihood estimators under both sampling setups, that is simple random sampling as well as ranked set sampling, Bayes estimation. Similarly, I am considering a special bivariate generalized Rayleigh distribution. I am considering S out of K system in both generalized Pareto and bivariate generalized Rayleigh distribution. I am considering S out of K systems and I am estimating the reliability of that system. And in this particular talk, I am not considering any modeling part. For the existing models, I am considering the inferential part, particularly estimation of reliability of the system. And of course, I don't find time for other two topics, particularly transmuted family of distributions. I don't want to touch it upon because of time. So in the introduction, first I consider estimation of system reliability based on inverse chain distribution. Here the problem is to estimate R, that is probability that Y less than X. Here X is X is the strength and Y is the stress variable, and both X and Y follow inverse chain distribution. So here estimation of this R is carried out using maximum likelihood and Bayesian methods. Maximum likelihood estimation of R is derived under both simple random sampling and ranked set sampling schemes. The approximate Bayes estimators for R is obtained using Lindley's approximation. So the reason being the closed form expressions for Bayes estimators are not possible. Hence, we have used one of the approximation techniques, that is Lindley. Then we have conducted simulation study to evaluate the performance of the estimators in terms of mean squared error. Okay, so I am not going to give details about Lindley's approximation. However, the Lindley's approximation gives you to approximate this kind of ratio of two integrals that will be useful to find the posterior densities. Now, in continuation with the literature survey, some of the related work which exists in the literature are, it's not exhaustive. Ennis and Geezer, 1971, Tong, 74, Govindarajulu, 67, Woodward and Kelly, 1977. Consider this problem when the stress and strength variables follow exponential, variable, Pareto, gamma, etc. In 2008, Rakab et al. Estimated the reliability for a 3-parameter generalized exponential distribution. 2013, Solomon et al. Considered Bayes estimation of R, that is probability of Y less than X, and X and Y are independent modified variable distribution. So then, in continuation, Matak et al. Estimated the reliability for when X and Y follow exponential distribution. Hussain 2004 discussed the estimation of strength reliability for a generalized inverted exponential distribution based on RSS and SRS. The 2014 paper by Hussain has used both the sampling schemes RSS and SRS and compared them. Then Hassan et al. 2015 studied the estimation of reliability when X and Y follow Burr 12 distribution random variables based on RSS, that is ranked set sampling scheme. So now I consider inverse chain distribution. The inverse chain distribution was introduced by Srivastava in 2004, which has the cumulative distribution like this. It has two parameters, gamma and beta. Both the parameters are the shape parameters, and the density function is given by this. The hazard rate or hazard rate function of inverse chain distribution is given here. From the graph, one can see that this inverse chain distribution can be used as a model for when the lifetime of the units have early failures. If you see the graphs, we have tried to draw different graphs for different values of the shape parameters, and we can see that in every case, earlier failures can be modeled. So now, what is the reliability under testing setup? When both variables are independent and they have inverse chain distribution, and they are not identically distributed. However, they are independent. They differ with respect to one of the shape parameters. Both the shape parameters are different. The stress strength. I'm sorry, here. See, the parameters should be gamma beta and delta beta. Correct. Beta is common. So gamma and delta are different. They are not identical with respect to one of the shape parameters, that is the first shape parameter. Fine. So first we consider the maximum likelihood estimator under SRS. So we write the likelihood and log likelihood and the MLEs of gamma delta as function of beta. Say gamma hat and delta are given by expression 7 and 8. And here beta hat is the solution of a nonlinear equation of the form h beta equal to beta. See, where h beta is a nonlinear expression. So if you put h beta equal to 0 beta, so that should be solved. A nonlinear equation has to be solved to get the MLE for beta hat. So once we get to the MLEs for all the parameters, naturally by invariance property, the estimator for reliability can be obtained. So similarly, the maximum likelihood estimator for R under Sankey sampling scheme is considered. A particular type of Sankey sampling scheme is considered. See here, xi mx, I equal to 1 to mx, j equal to 1 to rx, with the ranked set samples with sample size nx, that is mx into rx, with mx is the set size and rx is the number of cycles drawn from inverse chain distribution with parameters gamma and beta. Similarly, yk my. So now, so for convenience, what I do is I just write xi mx j and yk my I. Okay, so the PDF of xij and ykl are given here, and the log likelihood the function of gamma delta beta is the following, that is the expression 13, then where xi star is a constant which doesn't depend on any of the parameters. Now, the likelihood equations are given below to evaluate the MLEs. See, again, if we solve 13, 14, 15, and 14, 15, and 16, these equations are nonlinear equations, and this can closed form expression for the parameters are not possible. Hence, we solve it using iterative technique, particularly Newton-Raphson method we have used. We can use some other methods also. And after obtaining MLEs for gamma delta beta, the MLE of R can be obtained because we have the invariance property of MLEs. Hence, this is the MLE for reliability R under ranked set sampling scheme. Now we go for base estimation of R. So here we have again the setup is the same. We have X as inverse chain distribution with gamma beta, and Y as inverse chain distribution with delta beta, and all the three parameters are unknown, and we assume that these are parameters are random variables because in base setup, so they are assumed to be independent random variables with gamma prior, Ci, and Di. So this gamma is considered because it is the conjugate prior to the trend distribution. So now we have the joint prior distribution of gamma, delta, beta, that is the product of densities of gamma, delta, and beta, because we have assumed that gamma, delta, beta are independent. So with this, see now we need to find out the joint posterior density of gamma, delta, beta. So that is in the following form. There is a ratio of integrals. So here A is this. We want to evaluate this posterior density. So again, closed form expression for that is not possible. We have to evaluate r hat. Base estimator of r is r hat, which is the solution of this integral, and it is difficult to solve and analytically due to non-existence of closed form expressions. Hence, we go for some approximation method. Here we use Lindley's approximation method for obtaining base estimator of R. So for that, we need these quantities rho 1, rho 2, rho 3, d1, d2, all these quantities, and partial derivatives like Lij's as the below, and finally we obtain the base estimator that I call it as r hat b, that is given by equation 18. Now for this single component system, we have used we have conducted a simulation study to compare the performance of proposed estimators of reliability. 1 lakh random samples of different sample sizes were generated for stress and strength variables with different parameter values. We have considered the following values for gamma, delta, beta for illustration, and the results are tabulated in below. So here we can see that the MSEs of estimators under MLE under SRS, MLE under rank sampling scheme, and base estimators are obtained. So we are comparing it through MSEs. Here we can see that no doubt MSE of base estimator is less, but it is very close to MSE of MLE under ranked set sampling scheme. And if you look further, there is very close. No doubt the base estimators are better with the particular prior. However, ranked set sampling scheme also gives a better estimators. Now, with reference to the single component system model, when X and Y are inverse chain distribution, some conclusions are presented here. That's what the base estimators are better using the approximate base estimators using Lindley's approximation are better as compared to the MLEs obtained under both the schemes. However, MLE under ranked sampling scheme is better than the MLE under simple random sampling scheme. And of course, if the prior knowledge is not there, we can use RSS as compared to MLE. Now, here next we consider estimation of system reliability of multi-component system model for inverse chain. Here we have considered two systems, particularly parallel and series systems. See, system reliability for a multi-component system consisting of k identical components is considered. The k components of the system with random strength x1, x2, xk are subject to one of the r random stressors xk plus 1, xk plus 2, xk plus r. When the system is either parallel or series, with the assumption that strength and stresses follow inverse chain distribution. Some of the earlier works, to mention few, Kunchur and Munolli 1993 derived system reliability for exponential distribution, particularly for parallel system. Hangal 96 considered this problem with maximum of 2 when x1, x2 follow bivariate exponential distribution, and X3 follow exponential distribution. Further, for estimating these probabilities, x1, x2, xk are the strength subject to this, follow a distribution such as independent 2 exponential distribution, Hankel 1998, and independent Pareto or Weibull or Gamma distribution, it's by Hankel 2003, were studied. So in all these papers, estimation of reliability is considered by taking maximum of 2 stresses. So here we have considered the stresses as R. Okay. So here we have considered 2 systems. System reliability for parallel system is this, and the series system is this. And we have estimated, assuming that they are from inverse chain. So again, here also we have used MLEs and okay. So some practical situations where multi-component system, consider a system of identical generator sets synchronizing with and running in parallel with supply utility grid. Each generator will be having independent strengths such as the voltage magnitude, the frequency of voltages, and phase angles between the voltages, with independent stresses such as power failures, short circuit currents, earth fault currents, etc. So such system can be considered as multi-component system with multiple stresses. Similarly, I have given one optical communication system example, and I skipped that. So again, I have considered reliability of series system when we have inverse chain. The RS, that is for the series system, RS reliability of the series system is this, and we have estimated delta, K, gamma, everything, and using maximum likelihood estimators. And again, this MLEs are, we will not get the MLEs in the closed form expression, but we have to solve a non-linear equation, and again, iterative techniques are used. So, and again, multi-component systems, particularly parallel series system reliability, are obtained using Bayes technique also. Here, Lindley's approximation techniques are used. Lindley's approximation techniques are used to get the Bayes estimators. Okay, the simulation study is conducted and MSCs are obtained, and the conclusion is the following. Maximum likelihood and Bayesian results are used to derive reliability of parallel series system, and simulation study is conducted to evaluate the performance of estimators through mean square criteria. Results show that Bayes estimator perform better than maximum likelihood estimators. So next, we consider, so how much time do I have, Dr. Vaidyanathan?
Yeah, it's almost maybe
so
2-3
can I
minutes.
take another 3 minutes?
Yeah, yes, please.
Yeah. Okay. So I will skip this generalized Pareto. I go to the bivariate inverse Rayleigh.
Okay.
Okay. So here, estimation of reliability for S out of K system under system setup based on bivariate generalized Rayleigh distribution. So this involves in combining the multi-component system model with a bivariate distribution. We consider a system which has K independent identically distributed strength components, each of which consists of a series structure of 2 dependent elements exposed to a common stress. The system functions if S or more components simultaneously operate. So these kinds of situations may occur oftenly in real life. For example, in suspension bridges, the deck is supported by a series of vertical cables hung from the towers. Suppose we have a suspension bridge consisting of n vertical cable pairs. One vertical cable pair consists of 2 cables on both sides of the deck. The bridge will only survive if a minimum of K vertical cable pairs through the deck are not damaged when subjected to the stress due to wind loading, heavy traffic, corrosion, etc. So this is a situation where one can think of bivariate distributions for the strengths. So here, the estimation of reliability of K independent and identical components whose operation is subject to a random stress is considered, and the life of each component of a system is constructed by a pair of dependent elements. The strength of the components represented by a pair of random variables is assumed to follow bivariate generalized Rayleigh distribution, and each component is exposed to a common stress T, which has a generalized Rayleigh distribution. The system is regarded as operating only if at least S out of K strength variables exceed random stress. Again, here also we have used the maximum likelihood and Bayesian approaches to estimate the reliability. Main purpose of this research is to estimate the reliability. Okay, so the bivariate Rayleigh distribution is proposed by Dina and in 2003, and this is constructed in the following way. Say V1, V2, V3 follow univariate generalized Rayleigh distribution, and all the three distributions are mutually independent. The probability density functions are given below, and construction of the bivariate Rayleigh is this: X is equal to maximum of V1, V3, and Y equal to maximum of V2, V3. So bivariate generalized Rayleigh distribution is the following. Here, this is constructed on the similar lines as the Marshall-Loken distribution is constructed. And here, this is not absolutely continuous, and it has a positive probability at X equal to Y. Okay, so now we have used this sort of K system. This is the reliability of a sort of K system, and you get reliability in this way, and we have to estimate delta lambda for estimating the reliability through MLEs. So again, we have the following: the likelihood function, log likelihood function as usual. We get MLEs of lambda, delta, gamma in the following way, and you can write lambda and delta in terms of gamma, and gamma is obtained by solving a nonlinear equation. So MLEs are obtained. So we have also considered the MLEs under RSS, and the estimators of reliability are obtained. Is also base estimators of RSK is also obtained using Lindley's approximation method. Again, the problem is the closed-form expression for base estimators are not possible. Hence, we go for approximation method. So some simulation studies are conducted, and again MSEs are obtained, and finally base estimators are better. Some conclusions are this: the reliability of K component system in which S identical strength components sustain a common stress is studied. Here each component of a system comprises of two dependent elements which are connected in a series. The K strengths x1, y1, x2, y2, so on, xk, yk follow bivariate generalized Rayleigh distribution, and the stress T to follow generalized Rayleigh distribution. The reliability of the maximum likelihood estimators are obtained under both simple random sampling scheme and ranked search sampling scheme, and simulation results show that base estimators are better for the considered priors, and no doubt RSS is better than simple random sampling. Because of time, I just stop here. These are some of the references. It's not exhaustive again. Some of the references I have given here. And thank you. So I take this opportunity to thank the organizers for giving me this opportunity. So thank you. So if there are questions or comments, they are welcome.
Thank you, Professor.
Sir, I have one.
Yeah, thank you, Professor Pandit, for this very nice talk where you talk about this reliability estimation of a component as well as multi-component under this inverse chain as well as Rayleigh distributions. We have touched upon the estimation with respect to MLE as well as Bayes and introduced this rank set sampling also. So I think it should be a very good opening for people working on this, that such type of comparisons among these estimation techniques can be done. So in this aspect, it's a very good work. And there was one question. I think one person was trying to pose some questions.
Yes, sir.
One quick question we can have, because due to paucity of time. Yeah, please.
Yeah, Professor Srinivas Rao.
Sir.
Yeah, hello.
Sir,
yes.
Can I ask one question, sir?
Yeah, please, sir.
Can we apply the different methods of estimation on the RSS procedure?
Yeah, we are trying on that line. Okay, we have not succeeded yet. I think it is possible. We have started working on that recently, so I think we are positive about it.
Okay, sir. Okay, thank you very much. Thank you very much to see you online.
Yeah, I have referred your papers also, I suppose.
Yeah,
it's mentioned. Yeah.
Thank you, Professor Srinivas Rao. And there is one more question. Manish Kumar is there?
Yes, sir. I am Dr. Manish Kumar. Sir, I have one query that, sir, you have mentioned that Bayes estimator is obtained using Lindley's approximation technique.
Yeah.
So there is other approximation technique.
There are other methods also. You can use MCMC,
yes,
or you can use some Kadane and I'm unable to recall the other name. So these are two that also can be used, and there may be some other approximation methods also. I may not be knowing, but these are the three methods which I know. MCMC, Lindley, and Kadane and Terane, I suppose. Okay, that also can be used, and that can be compared also. So we have done on comparing Lindley's approximation with Kadane and Terane. It is in progress. One of my students is doing in that direction.
Thank you, Professor Pandit, for spending your valuable time with us.
Yeah.
So due to paucity of time, we have to go to the next speaker. So thank you, sir. And so the next speaker for this session is Professor Sivaswamy.
Yes.
Yes, sir. Good evening, sir. Good evening. Welcome. Welcome to this online virtual conference, and we are very happy that you have accepted our invitation to be with us during this day of the conference. So on behalf of the department and the organizing committee, I welcome you for this session, sir. And a very brief introduction about Professor Sivaswamy. Currently, he is a visiting senior lecturer in the Department of Mathematics and Statistical Sciences, Botswana International University of Science and Technology, Botswana. And he has around 4 decades of teaching and research experience at university levels. I think way back in 1978 to 2008, he was with Anomaly University. He has been the head of the department for quite a long time there. And then from 2008 to 2018, he is working as is serving as a visiting professor in the University of Botswana. And so he has been assisting and supervising researchers and scholars interested in the study of stochastic processes and their applications, as well as problems related to queuing theory, reliability, and inventory. And apart from a theoretical thing, he has put its hands on Python, R, and Julia. So that's good that we have got a person who is well versed in theory as well as in the programming part also. So, and he has given numerous talks and tutorials, and he is an author and co-author of more than 60 publications in international journals. And he is also a very regular visitor to our department whenever he comes to India. I think he makes it a point to visit our department, and we do also invite him. So with this very short introduction about him, I welcome you, sir, to give your talk. And today's talk will be on the topic control chart for monitoring of waiting time statistic of a Poisson queue. So yes, Professor Sivaswamy, we welcome you. Please, sir.
Thank you, Chair, Professor Vaidyanathan.
Yeah.
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 The,
I have started. Yes.
present now. Is it okay?
No, we are not able to see anything. Does not come. First, you open your PDF or PPT, sir.
Yeah, PDF I have opened.
Then go for the Google Meet. Down below, you have the present now.
Share, huh?
Yeah, on that, you just click the present now. You will see three tabs there. You click a window.
Is it okay now?
Yeah, now we are getting. Yes. Yes.
Can I proceed?
Yes, 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 sir. Please.
It's now perfect.
Okay. The title of the topic is control chart for monitoring of waiting time statistic of a Python queue. Firstly, I greet each one of you on behalf of BUST, Botswana International University of Science and Technology, Botswana. The outline is briefly on five items. Firstly, basics of control chart, every one of you may be knowing. Similarly, the computation of movements of geometric distribution, both the conditional and unconditional, all of you may be knowing. Only the control chart for monitoring waiting time of customers in an M bar, M1 plus M2 bar 1 bar K policy. I have published a paper. I extracted the results from that. Then that follows numerical illustration and a formal conclusion. Let me read the abstract as such first. There is no precise statistical control chart for monitoring the waiting time of jobs served by any kind of waiting line facility. Monitoring of a statistic by the well-known Stewart control chart is mainly based on the assumption that the sample observations must be independent and the monitoring variable must follow normal distribution. Nevertheless, several articles on control charts have been proposed using the assumption that the waiting time of general queues is not highly skewed. This is the constraint, or even moderately skewed, and with no prior conditions on either the inter-arrival times or on the service time distributions. Hence, this paper develops a Stewart-like control chart under non-normality for the waiting time of a Python queue with a K policy. An application is then demonstrated to a few samples of queues for different values of K, not N, to search for assignable passes, if any. Walter Stewart invented the control chart in 1920s. Because of its simplicity, it was very popular at the time. Chart for waiting time. The standard control charts use 3 sigma limits. However, for monitoring the steady state queue length or the waiting times of queuing systems, there is no sound method or sound control chart to formulate the control limits. This situation motivates me to construct a modified control chart for the waiting time of customers in a Python queue. What is badly needed is calculation of the first 4 movements of geometric distribution and truncated geometric distribution. These things are outlined here. Even a graduate can do it better than me. This is for conditional, truncated geometric. Right. The 4 movements are needed in order to modify the Schwartz control limits and going to a modified chart. Generally, under SPC, statistical process control methods, while designing a traditional control chart for an attribute or count data, one must know both the mean and the standard deviation. And the limits will be like this: mean plus or minus 3 sigma, that's it, or even standard error. Real life scenarios where the monitoring statistic follows a skewed distribution can be found in hospitals, billing counters of malls and bank tellers. For example, in outpatient wing of hospitals, a change in the distribution of number of customers waiting per minute would require variation in the current manpower level. This was justified by Shore 2006. Before going to implement the proposed control chart, there are 4 colorful points to be noted. The SPC-based monitoring of performance measures of waiting lines did not follow the formal practices so far within the quality management discipline. They, for example, this paper, Kungudi and Muthulashmi, they have published, but they did not take into account the value of skewness. Firstly, because more measurements on performance measures of waiting lines over a period of time may show highly skewed tails. This should be given weightage. Secondly, no universally accepted formula exists as on date on the UCL or LCL or CL for the general GGCQs and particularly for even MMCQs. For drawing Markov-dependent samples from a normal population and using them in a chart to detect small shifts, one can refer to my paper, which was published in the year 2003, got accepted in Quality Engineering Journal, one of the reputed journals. Then I have say here summarized the Q-length distribution of this particular Poisson Q, M bar, M plus 1, M1 plus M2 bar 1 bar K. What is the interesting feature is the K policy. Before K, if the Q length is less than K, the service rate is mu1. After K, the service rate changes to mu2 greater than mu1. That is why that policy will decide the Q length. Before the say even the attainment of the Q length K, the traffic intensity could be even more than 1. After that, it should not be so. So those things are taken into consideration very carefully in the proposed methodology. Here we have exploited this Littis law, namely expected value of the Q length equals the arrival rate lambda times the average waiting time. In 1 minute of time, lambda number of customers may be arriving. If a person has to wait on the average W bar units of time, then that is the thing. This is the, I divided the state space of the Q length process into 2 mutually exclusive sets, D1 and D2 like this. Then I constructed a combined distribution or mixer, say 1 minus QK times F1 and QK times F1 of N like that. See, F1 is both follow geometric distribution, but depending upon the value of k. Then I repeated the whole argument, and here I have highlighted how to construct the UCL and the LCL. UCL is the mean of the statistic under monitoring status, plus 3 times standard deviation of that statistic, plus this is the addition, 1.324 times the standard deviation of the statistic times skewness of the statistic minus 0.5, like that UCL. But here, strictly speaking, I am going to consider the number of customers, or for that only I am going to construct this chart. I will tell you the reason later. So here I have highlighted the UCL in terms of the moments of the NS value, number of customers in the system at a random point of time. One algorithm is well developed that consists of these steps. Firstly, generate a random number from the uniform population, and then compute the inter-arrival time x1 from the exponential distribution with the parameter lambda, and find out this x1. Then it goes like this. Here you may ask, say, how to implement this. For I have my own, I have written the program in R software, in R language, and these are the commands. Only ggplot I have included in my library. Then color. Then say if you run this program, it will tell us how to construct the here sample size is only 10. For sample size 10, the distribution may not follow normal. That is the point to be noted. I think up to this it may run. If you run the program, it will give the chart. See, like this. Are you able to see? Hello?
No, sir.
No, sir.
See. I think it should, you are talking about another file. So in that case, you have to share this and open that.
Oh.
Yeah. We are using a different file. Please stop
Yeah,
share this.
programming. Anyhow, it may disturb. It may. Okay, I will leave it. Yeah. Okay. Using our program, I have simulated the data for these values. Lambda is something, and firstly I calculated waiting time, arrival time, departure time, waiting time, from waiting time Q length, W by lambda, something like that. Then I have calculated the necessary things for upper control limit and lower control limit as well as central. When you inspect the chart, we can identify if there is any assignable cause. Thus, any assignable cause that may lead to outlying observation of NS statistic may indicate lack of control. Examples of such assignable causes are attributable to changes in the service or arrival rates, or inflation of variance in the distribution of inter-arrival times or service times, or in both. Control chart for the sample data that fall in the 3 columns of table 1 show I have shown here. Here, if you see here, 1 point falls outside. That means because of one of the reasons just now outlined, the process is not under control. So we have to take a preventive some measure, and we have to bring the process under control. Then the reasons are for this lambda 1 by lambda equal to 2 and so on. The first chart was drawn. And after removing the assignable cost, I have drawn another sample of size only 90. The 19 observations fall like this. See here, lower control limit is 0, lower control. The green line is the central line, and here the weight monitoring statistic goes up and down. Say more number of points not falling on the same side, either upper above the central line or below. So this is the usual practice of inspecting the control chart. Then I conclude like this: the same sample data again simulated for our model. Figure 2, where the chart shows the in-control status of the queuing process. In this chart meets all of our expectations around the central line, and thus the queuing process is classified as stable or repeatable. It indicates that the process must be capable of operating with little variability around the target or nominal dimensions of the model's quality characteristics. So my conclusion is this: in general, SPC methods of monitoring of a statistic of a queuing system use control limits based on normal. Those approaches are not effective. Shore developed an effective control chart for non-normal populations. Here we have extended the same methodology for numerically tractable control limits, and thus monitor the system size ns, number of customers in the system at a random point of time, of some Python queue with a K policy. With this, I thank you all. But one more thing, one important thing is this. Professor Tirupati Rao is my brother. I want to thank him.
Thank you, sir. Thank you for your warm affections.
Yeah. So, and these are my references. Thank you.
Thank you, sir. Thank you.
Yeah, thank you, Professor Sivaswamy, for your nice presentation. I think we have got a question from Srinivas Rao Gade. Yeah, yes, sir, please.
Thank you, sir. Thank you very much. Sir.
Professor Srinivas Rao.
Thank you very much. Very good presentation. And I have one doubt. Shall we use for this also MMS model?
Yeah. See, here waiting time should be approximated. Please understand. Using any technique like a diffusion process method, or even the heavy traffic queues like that. Once you get the knowledge on waiting time, you can modify the limits. Only thing, the 4 movements you should be able to compute.
Yeah,
standard deviation, third movement, and skewness.
Okay. This semester I gave a
Yeah. You have asked a very good question. Please extend this to MMS.
Yeah, MMS, and she is doing in the cafeteria queuing system. But I want to apply this to the quality control aspect.
Yeah. Only thing, we are approximating the distribution. You should ensure that it is not highly skewed.
Yes.
That if that insurance is there, we can use my limits.
Yeah. I have been hearing your name through my professor K. Rosaya garu.
Professor
Rosaya garu used to tell your name always.
Yeah. From Andhra.
Nagarjuna University.
Yeah, Nagarjuna University.
Nagarjuna. I often met him at Pondicherry along with Professor Rao.
Currently is the registrar of the university.
Yeah. Like that, one day you will be elevated, Professor.
Anyhow, thank you, sir. Thank you for your nice words. And
one thing, sir, Professor Arivarinjan wants to ask something. Let him do something.
Yeah. No, he has actually put a He has put a chart. Nice presentation.
Mute off.
Yeah, Professor Aravindan.
Yeah.
Now please
I
talk.
wanted to appreciate your presentation. Thanks for the nice presentation.
Thank you. Thank you, sir. Thank you for the compliments. Yeah,
So-
okay. I thank you. Thank the chair, Professor Vaidyanathan also. Yes, sir. Thank you. So it has been a nice.
I have a minute with you.
Yeah. Yes. There is one.
Yes,
Professor
Yeah,
Rao.
hello,
Yes, sir.
Professor Swami. He may not remember me. I have met
No,
you.
you are my student at
Yeah.
Anna University.
But I'm so happy that you have brought control charts into queuing system, which I can use it in the hospital management, which I am working. It's a very practical way in which I have simplified everything. One small question you have, with a 10 sample, you are able to see a normality. Is it a very rare occurrence or it can happen more frequently? Because we are always thinking that unless it is 30 samples, we will not be able to establish a normality in getting the mean and the standard deviation. But you said even with 10 samples, you are able to look at the normality, because quality control application in the queuing system is a very rare situation, and it has a wide application in the hospital management, particularly COVID system.
Exactly, Professor.
Mm.
Only thing I want to know how to extend this to even highly skewed data. Highly skewed, please do research on that, because this land is so fertile to do further research.
Because queuing the random variables.
As Lakshman Rao mentioned, queuing models mostly we are in the assumption that are Poisson queues. Okay. Poisson means it is a skewed distribution. And we are mostly dealing with the quality control aspects with normal distribution assumption for fixing the control limits and other things.
That is for variables, not for attributes. Not for attributes.
Let me complete. In that sense, how these skewed distributions can be considered for quality control related, deciding this what we call it as limits, control limits for quality things, that may be given some emphasis. So the queuing theory is handled with positive skewed distributions. What my knowledge goes. And quality control mostly related with the symmetric distributions.
Yes.
In that sense, can we give some emphasis how these distributions can be synthesized?
Sir, the idea of the central limit theorem, when you standardize the data, it will follow normal. By standardization.
In that case, sample size should be reasonably large.
Yes. That's why I request all of you to do the research, further research for highly skewed data.
Professor Shivaswamy, can I have your contact details when you are free, so that I may be in touch?
Mail, Prof.
Yeah,
You
it's
are
a
my
very
student.
useful.
You are my student.
You are my guru also. There is no problem, and I am using
You are
all.
aged than me. You are aged than me, but my student.
Yeah, Professor. As Professor Tirupati Rao said, it's a very new thing that even queuing theory we can use control charts, which has not been tried very much in India. At least there are a lot of opportunities in the hospital management, particularly
Sure. I will collaborate with you.
Patients.
Please request Professor Tirupati Rao, who is his role model.
Yeah. Yes.
He wants to become multifaceted personality.
He has already become.
Yeah. Slowly and steadily coming up like that.
Thank you, sir, for your blessings.
God bless you.
Thank you.
So thank you, sir.
Thank you, sir.
Thank you all for your patient answering of the queries, and it's a privilege that you have been to us during this virtual conference and made your presentation. And thanks for all the participants. I think what I heard is that one more speaker who is supposed to give his talk due to some urgent. Yes, Professor. Yeah,
Professor Swain from Utkal University. He has some urgent medical urgency there, so therefore he is unable to attend the talk. It is a last moment development.
Okay.
So therefore, he apologized for the development.
Okay.
Anyway, that medical urgency we cannot make it. So therefore, there is no talk of him.
Okay.
We can cancel that talk.
So in that case, yeah, we had a very good evening. I suppose all the participants also will agree that we have got very good speakers for this session. And even though, yes, we have gone a bit, time limit has crossed, but I think on these academic events, when we have more food for thought,
we enjoyed the extended time.
Always enjoy. Yeah. So yeah. So with these few remarks, I thank all the speakers, and I thank Professor Tirupati Rao for giving me an opportunity to chair this session. Thank you, sir. Over to you.
It is all our responsibility of the department, sir, and we are proud to claim that all our colleagues are very effective in making the logistics during the COVID period. And I have a lot of tension. I am in a lot of tension. People, my colleagues particularly, they are assets of my department. And now their research scholars, all my colleagues, research scholars are working with us. And they are implementing now the logistics. Very interesting that I am having a very, very positive opinion on the COVID incidents. It has made us to convert the challenges as opportunities. And really, if it is physically happened, we cannot make different experts spreading over the globe. Physical presence of making them not only expensive, but also many constraints are there. The constraints like they have some issues. Okay, and for international travels, we have to do something. And there are so many issues, but all these issues with no, what we call it as no efforts, we are getting that. And Professor Sevaswamy from Botswana, Professor Samanthi from Sri Lanka, Professor Srinivas Rao from Tanzania. Okay, the yesterday speakers, 3 are from USA, 1 is from Georgia, 1 is from Washington, another is from Auckland University. And our Professor BLSP Rao, though he is in India, but he is far off now. But today's speakers are spreading all over the India. So this is a very interesting phenomenon. And moreover, the luckiest factor that the name of the conference, theme of the conference is coined with Professor C.R. Rao School of Thought. So that makes us a more strengthy. So all the research persons are very interested to incline towards our conference. It is another blessings. We have to be thankful to our great guru, Professor C.R. Rao Garu. And for all these things, and what all the things we are making is instrumental. We are just instrumental, what I understand, for which we are all have to congratulate each other. So, and particularly, I am very much grateful to the resource persons. They have given the finest of their output. This is what my belief today and yesterday's after listening. They have given the qualitative, the most qualitative and the finest part of their work, research works. Really, it is a bliss for us, and the budding students as well. Of course, research, everybody is a learner. So in that sense, we are also greatly benefited. First week and end with a very good note, with a fruitful deliberations. And we have 4 invited sessions in 2 sessions, out of which 4, 6, 24 people have participated. And around technical papers, in each session we accommodated around 15, 4, around 60 people have participated. Might be around 50 if there are some issues are there. So 25 invited speakers and 50 technical papers. That papers are also very qualitative, and very lucky that chairing persons have very keen observations, and they are not compromising on if the researchers are not having the clarity on it. And one more point I want to apprise you people that right now, among the resource persons, around 4 people are able to make our technical papers to be published. So I want to make use of this platform to request the invited speakers also. Actually, all these proceedings we are recording. And after that, with my help of my students, I would like to split each lecture of speakers, and these 24 speakers as well as technical papers also. We will make it as a files, 24 plus 20, 30, around 50 files, around 75 files we will create, and all these files will maintain as a digital conference proceedings, and in which if any resource person wish to make any research contributions, we would be happy to go for a special volume with the invited speakers papers. So
I want to just say that today's presentation was excellent. There were some technical problems yesterday, and Tirupati Rao corrected everything. Today's program is really first class. Virtual program is more than real. So we need not. We need not say virtually we have missed something. Virtually we got more than the real program. Sitting at our home, we were able to listen to many people, and there is no loss of information. It's sustainable. Now I should congratulate you for taking this up, and be assured that we all enjoyed the virtual session as much as a real session, and even say a little more than the real session.
Yes, exactly. It's also my opinion is also that one. You have a ample time to relax at your home. You will be feel like home, and you need not be under stress or strain when you are physically away from your home. You will have lots of stress. Okay, so that are all minimized, and we are actually as you said, sir. When we are in home, we cannot feel any tiredness. Okay, so therefore we are making our efforts. Morning 9 it was started. It is now 9 o'clock in the evening. Okay, so around 12 hours though we are working, we are blessed with great energy because of your moments, your encouragement, your support, moral support or physical support, whatever you call. So this type of things, as you are very, very correct, sir. Virtual mode has more advantages than the physical modes. And moreover, the people who are actually interested, they are on the dashboard. Okay, there is no compelling, no anybody. There is no forced way of keeping them in a conference room. There is no such. So therefore, in this aspect, everybody voluntarily, those who are interested, they are on the dashboard. Very interesting, sir. And very another thing is, I want to give a certificate as well as your CD or your video link to all the speakers, including technical papers. After conference, what I wish to say, I would like to make a video of all the speakers because technical papers are also very valuable papers they have presented. So that is the gift of the conference in the name of Professor C.R. Rao School of Thought. So that is our idea, sir. And today Samanthi is having 2 to 3 journals, and Professor Suresh Daman from UK, and right now he has many assignments with UNESCO level projects. He has 2 journals, and one person from Iran, and due to some connectivity problem he is unable to join. He had the 3 journals on optimization techniques. Okay, and further we are pursuing in our India. Professor Malik is having 1 journal. Around 4 to 5 people together they are having. There is no need of payment anything. What my understanding, without payment also we can publish our articles. So this is what I want to share with you people. And first week or 2 days sessions is very fruitful, and we have enough satisfaction on this productivity. And 1 more week is there, that will be on 28th and 29th. That is also very vibrant speakers are there, and in which Vaichanathan and our Vishnu and all my colleagues, department colleagues, you are overburdened that speakers are not 6 at that time. There are around 8 people are there in every session. You have to make fast without making any pains or something, without feeling bad with the speakers. We have to manage them. Okay, we have to request them. We have to say that is proceedings has to be in a time limit. So that will be a challenge to you people, Vishnu, Naveen Chandra, Sudesh Kundir, and 1 more, Ramakrishna. Ramakrishna is having the challenges. And anyway, our all resource persons are very wise people and elderly people. They are always trying to cooperate with us. There will be no issue. Okay, this is what I want to convey. I thank once again my computer science people. Professor Ganapati, I'm sorry, I'm taking professor, no problem. He is also professor in all the activities. Ganapati is a technical assistant which was provided by our university. And I have to thank my Vice Chancellor, my university computer science department, without which there will be no fulfillment of thanks. Okay, so my computer science HOD, Dr. Ashok, and the system analyst, Mr. Palanivel, and all the people, this Ganapati and Rasan, and some more people are there. So they are all coming forward, and what are Lakshman Rao's today's observations, they are coming to my rescue, and they minimized all these glitches, technical glitches. So you are able to witness a smooth functioning, and it is the front end you are visualizing. There are a lot of efforts. There are a lot of efforts that are being happened in the back end. Okay, for which Ganapati and team has made it. My students, particularly Hissam and Gulbadin and Siva and Saki, these are the male research scholars, and the female scholars also there on currently. These 6 people have made a lot of efforts in the back end work. So simply they made us our job simple, and simply we are sitting at desk. They are making all logistics. And
Professor,
yes, sir.
Professor, we have to thank lockdown and COVID also for this virtual opportunity. Real opportunity has to virtual things. We are very happy, and we have overburdened you with a lot of extra work, but it is worth. We are able to see you all sitting at home. So much economical and no physical strain at all. But knowledge is pouring in from all over the globe. We are so lucky and we are so fortunate.
Exactly. So this is what, once again, I would like to extend my sincere thanks to my students, and because they are the back end people. What we witnessed today on the front end is completely the efforts of the technical people and my students. So, and of course, without participants, we cannot have the liveliness. So participants are so vibrant and they make this event very lively. So this is what I would like to convey for first week, and we will have a gap of 5 days, and after that again we will have 2 more days, 2 more vibrant days. And I have a plan of valedictory also. So that valedictory right now, the Saturday and Sunday it was not there. If necessary, we have to create an exclusive 1 hour or 2 hour program for valedictory. I will inform you in the next week, or meanwhile through correspondence I will inform you. Thank you one and all for happy occasion. Then we will have a leave from you all people. Thank you one and all. Right, sir.
Yeah. Thank you, sir. Thank you.
Okay, thank you, sir. Thank you very much. Now, shall we leave?
Yes.
Yes, sir.
Okay. Thank you, sir.
Thank you.
Dr. Sivasam,
Thank you, sir. Thank you very much, sir.
Lakshman Rao, Rajagopal, and many, Madam
Thank you very much.
Nanjit Sarif, Madam Nanjit Sarif, and the people like many people are there. Yeah, Sundara and others, Suresh Rajamani, etc., etc. So very interesting. People are not wish to move from the dashboard.
Yeah.
So it is.
Professor
It gives
Tirupati Rao, know that
it gives so much of strength for us.
I am an alumni of Pondicherry University. Therefore, I have
Madam Nanjim Sharif, Madam Nanjim Sharif, Professor Nanjim Sharif, Nasreen Sharif. I think she is unable to listen. Always she is keeping her camera above the head only. We want to see your face, Madam Nasreen Sharif. Okay, I think we are unable to reach her. Right. Okay, now thank you all, sir. We will meet again on the next Saturday by 9:45 sharp. Right, sir? Thank you. Thank you, one and all. Thank you, one and all. Thank you. Now join now. Oh, Madam Samanti. Samanti is there. Samanti Konar Singh. Yes, yes. Thank you, one and all. So I would like to leave first, then only people may leave.
Hello.
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 Yes.
Can you hear me? I'm audible.
Yes.
Am I audible?
Yes.
I can't hear you. Hello. Am I audible?
Are you in the conference?
Yes.
Oh, the conference is just over.
Yes, I know. I was just during the conference. I had a question. I could not unmute. Now I'm able to
Okay.
unmute.
Yeah. See, I am Dr. Lakshman Rao. I did not make any presentation. Please tell me your doubt.
Sir, I wanted to ask a question to Salochana, one question to Salochana and one question to Jyoti.
Oh, but the time is over now.
Yeah. But at that time, I could not unmute for some reason, but now I'm able to unmute.
What's your name?
My name is Nazneen.
Where are you from?
Bangalore. I'm in Bangalore. I'm a biostats consultant. I'm an ex-alumni of Edinburgh University.
Oh, I see. Kannada ಮಾತಾಡ್ತೀರಾ?
ಮಾತಾಡ್ತೀನಿ ಸರ್.
ನಾನು ಡಾಕ್ಟರ್ ಲಕ್ಷ್ಮಣ್ ರಾವ್ ಅಂತ ಮಡ್ರಾಸ್ ಅಲ್ಲಿ ನಂದು ಪೇಪರು ನೆಕ್ಸ್ಟ್ ಸಾಟರ್ಡೆ ಇದೆ. ಓಕೆ. I also we had lot of discussion just now. It is over. ನಂದು ನೇಮ್ ನೋಟ್ ಇದು ಮಾಡ್ಕೊಳ್ಳಿ, hklraw@gmail.com ಅಂತ.
ಪರಿಚಯ ಇದೆ ಮುಂಚೆ. Survival advances in survival analysis, presidency college.
ಜ್ಞಾಪಕ ಇದೆಯಾ?
Delegate ಇತ್ತು.
Oh, yes.
I heard your comments, sir. Comments, detailed criticism and comments were very good.
ಇವತ್ತು ಅದು ಶಿವಸ್ವಾಮಿ was talking about control charts for waiting line theory.
Yes.
I don't know whether you attended it. We had a lot of discussion because the waiting time variable is generally non-normal. Therefore, control charts cannot be used. We had a lot of discussion now.
I heard that, sir. I heard that. I was there.
Because I am doing some hospital management here in Chennai.
Which hospital, sir?
ಇಲ್ಲಿ ಇದು ತಾಂಬರಮಲ್ಲಿ ಒಂದು AG ಹಾಸ್ಪಿಟಲ್ ಅಂತ ಇದೆ, ಗ್ರೂಪ್ ಆಫ್ 5 ಹಾಸ್ಪಿಟಲ್ಸ್.
Okay.
I am doing TQM for them, total quality management and 6 Sigma.
Oh, okay. Agli sir, ನೋಡಿ ಸರ್, ನಮ್ದು ಪರ್ಸನಲ್ ಒಪಿನಿಯನ್ ತುಂಬಾ ಕನ್ಫೌಂಡಿಂಗ್ ಫ್ಯಾಕ್ಟರ್ಸ್ ಅಡ್ರೆಸ್ ಮಾಡ್ತಾ ಇಲ್ಲ. ಕನ್ಫೌಂಡಿಂಗ್ ಇರುತ್ತೆ, ಇಂಟರ್ಪ್ರಿಟೇಷನ್ ತುಂಬಾ ಡಿಫಿಕಲ್ಟ್ ಆಗುತ್ತೆ ಸರ್. ಅಡ್ರೆಸ್ ಮಾಡಬೇಕು. ಅಂಡರ್ಲೈಯಿಂಗ್ all the underlying distributions, latent variable, concomitant variable, statistical tools to control variability in different ways, confounding factors.
ನಾನು I am basically a 6 Sigma person.
Oh, okay sir, very good. So
6 Sigma ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಇವಾಗ ಹಾಸ್ಪಿಟಲ್ ಮ್ಯಾನೇಜ್ಮೆಂಟ್ಗೆ.
ವೆರಿ ಗುಡ್.
ಆಮೇಲೆ ಇದಕ್ಕೆ ಕಾರ್ಪೊರೇಷನ್ಗೂ, ಚೆನ್ನೈ ಕಾರ್ಪೊರೇಷನ್ಗೂ ಐ ಆಮ್ ಅಪ್ಲೈಯಿಂಗ್ 6 Sigma ಫಾರ್ ಮೋರ್ ಎಫಿಷಿಯನ್ಸಿ ಅಂಡ್ ಎಫೆಕ್ಟಿವ್ನೆಸ್.
ತುಂಬಾ ಒಳ್ಳೆ ಸರ್. 29
ಆಮೇಲೆ ನೋಡಿ, ನಾನು ಆನ್ಲೈನ್ ಅಲ್ಲಿ ಐ ಆಮ್ ಟೀಚಿಂಗ್ ಬೇಸಿಕ್ ಸ್ಟಾಟಿಸ್ಟಿಕ್ಸ್ ಟು ನಾನ್ ಸ್ಟಾಟಿಸ್ಟಿಕ್ಸ್ ಪೀಪಲ್.
Very good.